Morning and welcome to the second day of ARCS. It's my pleasure to introduce the keynote speaker today, Neeraj Kayal, who I'm sure everybody here knows him from his first major contribution, which was he was a member of the team which proved that primality testing is in P. This was way back in 2002 when he was an undergraduate student at IIT Kanpur. He went on to do his PhD there. That work won him several laurels, the Gödel Prize, the Fulkerson Prize. So he's been doing his research in algebraic complexity, lower bounds, more recently in unsupervised learning. In algebraic complexity, people who work in that area, his name is extremely familiar because he has contributed many, many new techniques and paradigms, and his insights have been very valuable for subsequent work. He's been recognized with the Infosys Prize in Mathematical Sciences in 2021. He's a recipient of the Shanti Swarup Bhatnagar Award for 2022. So today we are looking forward to hearing him tell us more about algebraic complexity theory and unsupervised learning. So before Neeraj starts, maybe I should remind everybody to silence your phones. And perhaps it's a good idea, those who are sitting very far away, if you move in close by, this auditorium is way too big for the size of the group that we are, but it's up to you. Over to you.
clustering and Gaussian mixture, they have see there's an enormous amount of work which has happened on both these problems. And I won't be able to even begin to summarize that work. Uh, so sorry for that. I will be skipping references, but there has been a very significant development building on our work just like a couple of months ago. Aditya Bhaskara, Eric Evert, Srinivas Vedehi, and Vijay Raghavan, they proved some conjecture that we had turned out. And the correctness of the algorithm depended on some conjectures about singular values of certain matrices. So they proved that conjecture, and also building on work by Mitali Bafna and a bunch of people. So this almost resolves this mixture of work. Whose origins go back a long time ago. So let me give some more examples where you have some sort of combination of structure and randomness. So there's this problem called let's say in this case 7 sources of sound or and 7 receivers. So 7 sources and 7 receivers, and what each receiver receives, the audio signal that it receives, is some linear combination of the audio signal emitted by each of the sources. So what we want to do is to untangle these sources. So we want to decompose it back into the original sources, the audio signal, the mixed signal, into the signal for each source. And yeah, the first time I saw this problem, it seemed very surprising to me that it can be solved. And the key here is that we assume that these sources are independent sources. And that's an extremely powerful natural that to separate out the source. So more formally, we have, again, you can think of it as a set of points. But the sources are each time step uh, generated by the source. You can think of it as a point in 7-dimensional space. And the receiver, it receives again a point in 7-dimensional space at each time. So then we are sampling this sources at various times. So we have a point in 7-dimensional space, and assuming that the sources are how to recover this mixing matrix. And there's a generalization of this to polynomial. Now, the sources are, again, independent random sources, but the receivers that they receive are polynomial functions of source. And can you find these polynomials? So each received coordinate is a low degree polynomial. And in terms of the from even discrete data. So, for example, there's this problem called topic modeling that we have given sequences of words. So, for example, like think of code sequences of these words here like this, and what we want to, what we have stored is that these sequences correspond to one specific topic. We want to find out. In this case, the first and the third set of words correspond to, let's say, cricket. The first and the third correspond to vaccination and medicine, and second and fourth to cricket. And you want to be able to automatically identify for these topics. So, yeah, before I go on, any questions about this problem? So, we have section to algebraic complexity comes. We are going to take this moment and put them. So yeah, this part will have quite a bit of intersection with Newton's talk yesterday. So I want to remind you a little bit about polynomials and formulas for polynomials. Uh, yeah, this is overlapping with Newton's talk yesterday. So we have polynomials, which are objects like this, and we want to find small formulas for it. So formulas are like a more precise way of saying mathematical expressions. So, and as computer scientists, we think of mathematical expressions as trees. So this particular expression for this polynomial, I can think of it as a tree like this. It's a natural way of doing it. The nodes are addition and multiplication. Addition compute arbitrary linear combinations, which we sort of capture via weights on the edges, and the final output node outputs a polynomial. So in algebraic complexity, the main question is how many operations are needed to compute a given polynomial f. And yeah, I will give a slightly different example to motivate this problem than what Newton gave yesterday. So consider a graph, and we want to find Hamiltonian cycles in the graph. So the reason that I'm giving this example is you might remember that finding Hamiltonian cycles in graphs is an NP-complete problem. And there's a natural way to capture this as a polynomial, as computation of a polynomial. So here's what you can do. Yeah, the Hamiltonian cycles essentially capture all of NP. So imagine a graph with a complete graph on n vertices where the edges are labeled by variables xij, and xij is, think of it as being either 0 or 1. 0 if that edge is absent in a given input graph, and 1 if that edge is present. So you can write down a polynomial which goes over, you sum over all possible Hamiltonian cycles in the complete graph. And for each such cycle, you can have a monomial, which is, in this case, the product of the variables on the edges of the cycle. So one command here is 1 if that cycle is present and 0 otherwise. Yeah, the exact expression is not important. This property is important. And then when you sum up over all possible Hamiltonian cycles, it means that this polynomial has this property that if you give it an actual graph with so xij's are zeros or ones, then the value of this polynomial on the given input graph is precisely the number of Hamiltonian cycles in that graph. So this polynomial for the Hamiltonian polynomial has this property, and it turns out that this was the insight of gradient which Newton mentioned yesterday, that if this particular polynomial can be computed efficiently, then in some sense all combinatorial problems, all combinatorial counting problems can be solved efficiently. And yeah, there are stars here, and in this talk I will often make informal statements which will, yeah, I won't specify all the technical things or the caveats. I will hide them under stars like this, just to give you a flavor of the result. So this is really remarkable, right? You solve this or you compute this one single polynomial, and essentially all combinatorial counting problems you would have found algorithms for. And so arithmetic complexity, people have always wondered, does this polynomial, or there are several such sort of what are called complete polynomials, do they have small formulas or not? And we still don't know the answer. This problem is called the VP versus VNP problem. And we conjecture no, almost nobody thinks the answer is the other way around. But if it were the other way around, we don't even consider that possibility among us. But if that were true, in particular, it would imply that P would be equal to NP, but not the other way around, like looking at it. So some years ago, again, I'm cheating here, but some years ago, essentially, we could prove lower bounds on formulas for Hamiltonian under some restriction that we were calling regularity, that the formula should essentially roughly be a balanced tree. And small here is, as usual, polynomial type. And recently, Newton, Srikanth Srinivasan, and Sebastian Tavenas, they had this wonderful result, which was stunning breakthrough in this area, that Hamiltonian does not have constant depth polynomial size formula. And that was one of the main results in Newton's talk yesterday. So, so we have made some progress, and yeah, sometimes it seems we are quite close, but not yet there to resolving VP versus VNP. So yeah, it's much stronger in many different ways than our result. So what I want to tell you today is that you can use these lower bound proofs. There's some sort of template to use these lower bound proofs to get learning algorithms for some of the problems that I mentioned in the beginning. So I want to talk about that. Any questions? So in order to do that, I'll have to give you a quick overview of these lower bound proofs, how they go. So yeah, but sort of let me first mention some informal versions of the results that we'll see. So what we showed was this, that you can use these lower bound proofs. In particular, these lower bound proofs use some linear maps, and those linear maps you can use to design efficient algorithms that, given a polynomial f, reconstructs small formulas for f, if they exist. Okay. But under mild non-degeneracy condition. I forgot to mention one thing. So the problems that I mentioned in the beginning, in the worst case, all of them are NP hard. So there is no realistic hope of solving any of them in the worst case. If you give me adversarially chosen inputs, I cannot hope to solve any of those problems. So, so all these results, all the algorithmic results will assume some non-degeneracy condition. But the non-degeneracy condition, or some conditions which will hold if you were to choose the input in some sense randomly. And in fact, we would want to prove even stronger thing, that even if you choose the input in the worst case fashion and perturb it slightly, even then these algorithms work and they give the correct output. So that's called smoothed complexity. And yeah, and that's what the most recent result was about. It proved the smoothed complexity of some of these problems. So in a follow-up work, what we showed was that even if you are given the polynomial approximately, uh, so we are not, or think of it this way, that we are given a polynomial which is close in some sense to a polynomial which has a small formula. And then we want to recover that small formula. So close here would, you can think of it like this. Now think of the polynomial as a vector. So for example, if you have a quadratic polynomial in n variables, it's a vector in roughly n square by 2-dimensional space. So if you are given some polynomial which is close in the sense of Euclidean distance between polynomials, then can we recover the small formula for the polynomial if there's some polynomial in the neighborhood which has a small formula? That's the question. And again, there are caveats to this, but essentially we have a general sort of meta algorithm that will take a lower bound proof of the kind that we discovered or Newton discovered and turn it into a reconstruction algorithm for formulas. And it can also tolerate this noise or this approximation. And yeah, there's substantial cheating going on here, but in this slide. But essentially, this implies that as a corollary, you get a single algorithm which will solve all these different, seemingly very different problems in unsupervised learning. The cheating that is going on here is that there are non-degeneracy conditions involved, and we don't know in all these cases how to rigorously prove that those non-degeneracy conditions hold if you choose your input randomly. But yeah, so there are technical challenges to doing that. But roughly, any questions about this? So let me just hint what those technical challenges are. In trying to prove lower bounds, like Newton was saying yesterday, it boils down ultimately to proving ranks of certain matrices. And for proving bounds, you only need bounds on the ranks of certain matrices, upper and lower bounds on the ranks of certain matrices. But when you're trying to do reconstruction or learn a formula, in particular, you'll have to be able to distinguish a polynomial which has a formula of size 100 from a polynomial which has a formula of size 101. Like even a slight change of size, at the very least, your algorithm should be able to detect that. So what this implies is that in terms of those ranks of those matrices is that you need to prove very precise on the nose rank bounds for those matrices. Essentially, there's essentially no room for error. You have to get those ranks on the nose. And that turns out to be challenging in many of these situations. And then this recent result essentially is the following. Not only are they able to prove these rank bounds, but they are able to go even one step further. These matrices, so rank corresponds to how many singular values of a matrix are non-zero. Yeah. So this most recent result, they show only not that these many singular values are non-zero. They can prove bounds on how small the smallest singular value will be. So yeah, it's amazing that they can do that, and that's why you get as a corollary also combined with uh, those singular value bounds, uh, smoothed algorithms for these problems. So I want to now give you some flavor of this connection between lower bounds and learning. How how can you learn formulas using lower bound techniques? So here's a sort of an abstract problem. Suppose we are given a multivariate polynomial f, and suppose that it is approximately equal to a sum of simple polynomials. So here's an example to keep in mind. So by simple will mean low circuit complexity polynomials. So for example, each summand could be a power of a quadratic polynomial. So, uh, so in this case, the problem would be if you are given a polynomial f, which is approximately equal to a sum of powers of quadratics, can we recover each of those summands? And in it turns out that this is the scenario which is applicable to learning mixtures of Gaussians, because the summands sort of capture the true moments of one component uh, of a Gaussian mixture, and the sum is because you have several components in our mixture distribution, and there is noise, or we know the polynomial uh, the, the polynomial with the small formula only approximately, because the empirical moments is that is what we compute from the sample. They are only approximately equal to the true moments of the distribution. So this uh, P, which is, we call it the perturbation or the noise, this is because there's a gap between the sample moment and the true moment of the distribution. So here's our problem. Given a multivariate polynomial which is approximately equal, or it's equal to a sum of simple polynomials plus a small perturbation P, we want to recover the summands SI approximate. And P is small, again in the sense that if you have to think of P as a vector, then it has small norm. Yeah. So now, uh, as I've indicated already, I've changed my viewpoint about polynomials. Earlier, I started out thinking of polynomials as just bookkeeping devices for keeping track of the moments of a distribution. Then in the second part, I changed my viewpoint about polynomials as functions, which given an input produces an output. Now I will change my viewpoint about polynomials yet again. I'll start thinking of them as vectors here. And so let me give you a quick overview of lower bounds. Uh, so the lower bound problem is the following. We want to find explicit polynomials f such that if you write it as a sum of simple polynomials, the number of summands r has to be very large. So, for example, I want to say that if I write a Hamiltonian polynomial as a sum of powers of quadratics, then the number of quadratics that I will have to pick is going to be extremely large. So that's the nature of the problem. So it turns out that pretty much all the lower bound proofs, they follow this template. We construct somehow a space of linear maps. So these linear maps, each of these linear maps L, they act on the vector space of polynomials. Usually we want to look at the vector space of polynomials of a specific degree, D. Let's say degree 10. Right? And then these linear maps, they will take as input a polynomial thought of as a vector and output another vector. And typically this other vector space where you map them to, typically this will also be some vector space of polynomials, maybe of a different degree. Maybe let's say degree 8. So we want this collection of maps to have the following two properties. That if you take a simple polynomial, like again, for example, a power of a quadratic, and hit this simple polynomial with this collection of maps, so you get a collection of points in the space, vector space W. So you take these points in W, look at the subspace in W spanned by all these points. And we want that the dimension of this subspace spanned by the image of Si, of any summand Si, under this collection, it should be small. And what I also want is that if you take the polynomial f, the hard polynomial f, and hit it with this collection of linear maps, the dimension of the space spanned by the output point should be large. And this is the sort of the complexity measure which Newton was referring to yesterday, which given this collection of linear maps, if this collection has this property, then this dimension of the space spanned by the outputs, this is some measure of the complexity or the hardness of this polynomial. So, what I want, okay, here's a exercise which I leave it to you. That suppose that if I could construct some such collection of maps, let's say for, again, the commands being, let's say, powers of quadratic polynomials, then you can verify that this will give you a way to lower bound the number of commands. In fact, the ratio of the second quantity, the second dimension to the first dimension, that ratio will be a lower bound on the number of commands. And that's just essentially because of linearity. So yeah, we in the algebraic complexity community have spent a lot of time trying to discover such collections of maps, and proving bounds on these dimensions, which will give us a lower bound. So now let me tell you that assuming we have such a collection of linear maps, how you can use it to do the reconstruction problem or the learning problem. So let me state the learning problem first. We are given as input a polynomial of degree D, and suppose that, for simplicity now, there's no noise, and suppose that it's a sum of a small number of simple polynomials. We want to output these commands, right? And yeah, in applications in unsupervised learning, these commands sort of capture the components of some distribution. So, so we take this collection of linear maps L given to us by the lower bound proof, and we will use another collection of linear maps. Typically, this other collection M is also inspired by the the collections which occur in lower bound proof. So, so what we'll do is we'll hit, uh, yeah, and the example to keep in mind throughout this part of the talk is the example where the summands are powers of quadratics. And in this case, the output space will be polynomials of somewhat smaller degree, d minus k, and the collection of linear maps will be essentially kth order partial derivatives. So you can take a polynomial and take its derivative along any particular direction. And yeah, partial derivatives with one additional operation that you restrict, after taking partial derivatives, you restrict my collection of polynomials to a low dimensional subspace. Let me not go into the details, and M will be what are we call partials composed with multiplications, degree 1 multiplication. So it's not very important at this point what exactly these maps are. I just wanted to give you a flavor of the kind of maps that we use. So we take such a collection of linear maps and hit my given polynomial f with it, and I look at the space spanned by the output points. So let's call this space U. And then something like typically something interesting happens, that this space U is a direct sum of the spaces that you would get if you were to hit each summand with this collection of linear maps. Yeah, so direct sum for vector spaces is sort of the vector space analog of saying that some set is a disjoint union of subsets. So that's sort of the vector space analog, that this space U is in some sense a disjoint union. Formally, we call it a direct sum of these subspaces corresponding to each summand. So, like the containment in the of the left hand side for the first property. The containment of the left hand side in the sum of the right hand side vector spaces, that's clear from linearity. What is interesting is that these sums are in fact direct sums, and this containment is in fact an equality. And yeah, I'm slightly simplifying here. So the other collection of linear maps will have this property that each of these subspaces will be invariant under the action of this other collection. So every map in this other collection M will map one of these subspaces, any of these subspaces LSI to itself. So, so we call this phenomena the blessing of dimensionality, because it tends to be true when you have points or polynomials in large dimensional space. And it is also, somewhat counterintuitive. Typically, dimensionality tends to hurt us algorithmically. As the dimensional increases, the dimensionality of the input increases, it becomes more and more difficult to design algorithms, but here it's just the opposite. The dimensionality actually helps us under certain non-degeneracy conditions. So then I use these, so we sort of find the common eigenspaces of U under this collection of maps M. And these eigenspaces are precisely the image of every summand. So U1 will be the image of S1 under the operator cell. And then there's some simple, relatively straightforward linear algebra you can do to say that given the image of S1 under L, you can recover S1 itself. And similarly, you can recover S2 and SR. Yeah, so that's all that I will say about this learning algorithm. So initially we did this when there was no noise, and then we looked at the same problem and essentially made this algorithm robust to the presence of noise. So the noise is captured in this vector P, the perturbation vector P, and the bound that we got for how far away. So when there is noise, you cannot hope your outputs to be exactly equal to the unknown Si. What you can hope is that the output will be close. The S1, S2, SR that you will output will be close to the true Si. So we want to bound how far away the output can be from the true answer. And this bound that we get involves is in terms of singular values of certain matrices. And you can imagine that these collections of operators will correspond to some matrices, and so the bounds are in terms of singular values, or more specifically the minimum singular values of certain matrices. And we had no clue how to prove these singular value bounds. But we made this optimistic conjecture that the singular values are, if you take even a worst case instance and you slightly perturb that worst case instance, then these singular values are not too small. Yeah, so if this conjecture was true, it would imply efficient, what we call smoothed algorithms for many of these problems, including mixtures of Gaussians. And yeah, as I mentioned in the beginning, very recently, this was proved. Again, there's a slight gap here, but essentially it was proved by these folks. And there was also some important work in between by Bafna, Kothari, Zhu, and the other authors. But there was a sequence of works, and yeah, this latest work essentially proves this conjecture. So that gives us algorithms with some provable guarantees about some of these problems. Yeah, so let me just, any questions? So let me just end with, again, this problem that I started out with. So, unfortunately, yeah. So essentially, can we build a system which can understand our world, in the sense that it gets as input humongous amounts of images, videos, maybe audio and language data, and can it use that to essentially understand our world? Yeah, we don't know. We feel we have some approach, some way to approach this problem. That's what I've been working on. Thank you.
Thank you. Are there questions?
Hi, sir.
Yeah. So the gap. So take this example. Suppose you have. Um, so think of the heights of people in India, right? So roughly the heights of people in a region, they will follow, let's say, approximately a Gaussian distribution. But you have like a billion people in India. You can't measure all their heights. You take a sample of, let's say, 1,000 people, and you want to. So if this assumption was correct, that for all the billion people, the distribution of heights of the billion people is a mixture, is a Gaussian, or is a mixture of a small number of Gaussians, then using a relatively small sample of size 1,000, you could hope to recover what is the average height, the mean of the distribution, and what is the variance, like roughly what what is the height, the bounds, such that let's say 65% of the people in India are within this bound. Right? So when you sample, let's say, the heights of 1,000 people, the average height that you take of these 1,000 people, that will be close to, but not exactly equal to, the true average height of the billion people, right? So that's why this error comes. What we are calling error or noise. That's the source of it. Right.
What is that?
So yeah, that what we know is that our bounds on that gap. So I'm not sure is that like what we know is that the the magnitude of this gap will depend on how many samples that you pick. If you pick 1,000 samples, you'll get a larger gap. If you pick 10,000 samples, the gap between the true average and the sample average will be smaller. And what we also know is typically this will fall off as square root of the number of samples, the gap. So the larger, the better, but the way it falls off is the square root of the number.
Thanks for the talk. I did not understand all the math, but the broader connection was very interesting to me. So I just wanted to ask you, that is, we are talking a lot about this explainability in the decision. So will this kind of, if your conjecture and all this is working, so can we believe our decisions much more, will it be more robust in that angle? Can you comment on?
Yeah. So yes, like so let me just give the context for this question. So there has already been tremendous progress in doing unsupervised learning on languages you must have heard of, GPT-4, and on other modalities like vision and video also. So there are these what are called diffusion models for understanding images, and yeah, some of those outputs are incredible, and but still, in some sense, or kind of we have trained these models, and they kind of understand, let's say, our corpus of real-world images, but we train them using what are these called these transformer networks. So they understand the real world to some extent, but we don't understand what they understand. And if we with this, we will be a much better situation. So in particular, we will be able to interpret what we have learned.
Thank you.
Any other question?
Thank you, sir, for the talk. Um, I was wondering if you could just re-explain the exact, or rather the maps that were used for the mixing of Gaussian example we discussed.
Yeah. So, yeah. So, in this case, think of K, let's say 2, to be like, to be concrete. So, here are what to do. On polynomials, you take derivatives. So, derivatives are linear operators on polynomials. So, if you take a polynomial of degree d and take its derivative with respect to, let's say, x1, the variable x1, you get a polynomial of degree d minus 1. And also, it has this property that the derivative of a linear combination, let's say, f1 plus f2, is that linear combination of the derivative. So, the derivative of f1 plus f2 is derivative of f1 plus derivative of f2. So, you use derivatives, higher order derivatives, let's kth order derivatives, and think of ks2, for example. And then you do one more linear map. You take some of the variables, let's say the last 20 variables, and you set them to the value 0. We call it projection. And essentially, this is also a linear map. So, if you take a sum of two polynomials f1 and f2, and in the sum, if you put, let's say, the last 20 variables to 0, that's the same as taking each of those polynomials, putting the last 20 variables to 0, and then adding them up. So, this is also a linear map. And the first collection of linear maps, L, is a composition of these two things. And the second collection of linear maps that we use, you can use other collections also, but yeah, this has the cleanest sort of proof. So we take derivatives again, this time only first order derivative, and then you have another collection which corresponds to multiplying a polynomial with a fixed polynomial, say y1. So does that answer your question?
Yes, sir.
We'll take one last question.
Hi, I'm Dhanajit from IIT Kanpur. So I have a question about that in unsupervised learning, we have this assumption about the inputs coming from a distribution. So will these results still hold in the case that the input distributions are changing over time?
Yeah. So these particular results, no, or okay. Let me put it this way, that in the very beginning, I roughly said that sort of real world data sets have some structural parts to it and some random parts to it. So the random part corresponds to distributions, and if the distribution changes and we train our model on a particular data from a particular distribution, and the distribution changes, our model often runs into trouble, right? So, like the results here, so which pertain to some of the results here also which pertain to distributions, that will not hold. And in general, in unsupervised learning and machine learning, that's a problem, but not in some sense not the structural parts of it. So, uh, so, so again, take this just to sort of give you some sort of flavor of what I mean by that. So imagine your data is like this, right? So there are structurally there are these three lines on which my data points lie, and on these lines themselves there is some unknown distribution of points. Now, typically, like in real world, we don't expect the structural things to change. So it like even if you take images from some other distribution, like imagine taking images. Earlier, you were taking images, mostly outdoor images, let's say, right? And you gave me a bunch of like images of outdoor things, trees, mountains, clouds, and things like that. And I see that, and I understand something about the world from it. And now you come and give me a data set of indoor photos, like auditorium and offices and things like that. So a large part of what I have understood about the world from those outdoor photos will no longer hold. But if I have discovered structural things like what are interiors of objects, what are boundaries of objects, what kind of boundaries occur, what kind of shapes occur, maybe some of what kind of textures also occur, maybe so those kind of things might still continue to hold.
So I think in the interest of time, we should stop now, but there will be time later on also for discussion. Let's join me in thanking Neeraj once again.
Thank you.
And as a token of appreciation from the ARCS organizers, there is a memento to be given, which is not a physical object. I call upon Venkatesh Raman to present it. Yeah. This is the ACM India initiative to plant trees in the names of. So this is a tree which has been planted, and Neeraj now has the code so he can track the growth of this tree.
Yeah, awesome. Thank you.
Cooperation with 14 trees, and the trees planted in Pune. Thank you. Thank you.
Yeah, we have the coffee break, and let's gather back in 15-20 minutes here. We'll start the lightning talks part 2. was the lightning. Yeah. So that.
So welcome back. And now we are going to have the lightning session, part two. So all those who have presented yesterday, well and good. So we are going to host the remaining people now. And you know the motto already in 1 minute. And we're going to give you some noise if you are going beyond that time. And as usual, you have already gathered close to the dais. So good. I'm going to announce the names, right? And you come one by one. Okay, so the first presenter is Pratik.
Hello everyone. Uh, Today I am going to present our work attaining God beyond honest majority with friends and foes. In standard distributed computation, malicious behavior of a party is uh, captured in two scenarios, either in the honest majority or dishonest majority. However, in the honest majority, it is vulnerable to view leakage attack, and in dishonest majority protocols, it lacks security in the sense that it does not offer fairness or robustness guarantee. So we considered a different model that is called friends and foes, and which surpasses this vulnerabilities. And in this work, we to give a theoretical result that necessity of oblivious transfer is required if the number of parties is less than 2t plus 2h star. Also, we design a protocol quadspot that is four-party protocol, and we show its applicability in privacy-preserving machine learning and for liquidity matching. So to know about this mode, please visit my booth. Thank you.
Trishi.
I'm Srishi from IIT Kanpur. So this is the type of crypto scam, particularly in which creators create communities, they high crowds worldwide, the funds and run. So to know more about such type of scams and particularly the drug pools, we have very interesting insights on it. How creators collaborate. You might have seen such images of apes and punks. So to know more about these creator collaborations and about rug pulls, I would like to invite you to my poster. Thank you.
Abhishek.
Hello everyone, my name is Abhishek. I'm doing PhD in IIT Kanpur. So we started with a problem of in gym setting that the training regimes are very much focused in gym, like they are not translated to the home setting. To solve this problem, we came up with a real-time pipeline that can correct postures and it can provide recommend exercise specific recommendations to the exerciser. So in summary, we take an input video of an exerciser doing an exercise, and then we run that video to our pipeline. Then it classifies the exercise done into the correct form or in one of the many incorrect forms. And based on that, we provide a recommendation to the exerciser so that he or she can correct their exercise in real time such that it can prevent any future mishap. So if you want to know more details, please visit us at our poster. Thank you.
Ankit.
Good morning, everyone. I'm Ankit Avinav. I'm from your host institute, NISER. So today I'll tell you a coffee story in a very brief manner. Let's say that after the event, you guys want to have coffee anywhere that you go, right? So what we as a host institute, we decided to put up a coffee stall at least at every one end point of the road. Moreover, the management decided that they don't have to move much, so they want a solution that is connected. And moreover, we are looking for a solution that is highly connected. So here we say n minus k is connected. So I'm talking about classical vertex deletion problem, which is NP hard problem. So you don't expect to have polynomial time solution for that. So to solve this problem, we have taken a parameterized algorithm approach. So this approach says that take a line, okay, sorry. Okay, so for most of the problem, we have shown FPT result, except for one problem, SC vertex multi-cut problem, where we could not give an FPT algorithm. Thank you.
Ashutosh?
Hi everyone, I'm Ashutosh from TIFR. So many of you would have heard of at least the code on the top left, that's the Reed-Solomon code. And in many ways, it is actually the perfect code. So it is based on the idea that a degree D polynomial can be zero on at most D places, otherwise it is identically zero. And if you think about it, if you find and prove the correctness of a unique decoding algorithm for Reed-Solomon codes, then you also are proving the degree maximum, even which seems, I mean, we knew the degree statement for many years, but it's a way of proving. It turns out even perfection can be extended in a couple of ways. You can add variables to get Reed-Muller codes. You can add multiplicities to get multiplicity codes. So what we do is we do this algorithm task for what happens when you extend it in both ways, add variables as well as multiplicities. So if you want to see how, stop by my poster. Thanks.
Next is Nidhi.
Hello, everyone. So imagine that you are a job seeker and you came across a job description which says that seeking relevant office handling boy and you need to do some administrative tasks. So how annoying it is to see this job description. So we all are on professional platforms and on regular basis, we see such job descriptions where we don't know what exactly you are looking for. So it's as simple as moment of कहना क्या चाहते हो. So in this, it is evident that we have around 65% of such job descriptions which miss mentioning job skills, which are actually relevant. So I am Nidhi and I am a PhD student at IIIT Delhi and faculty at Mahindra University. So in this work, we have provided a solution to this problem. So for more details, please visit my poster. Thank you.
Next is Anisha.
Hello everyone, my name is Anisha and this work has been done in collaboration with the AI/ML NLP lab at IIT Patna. So the poster that I have put up today mainly illustrates our work on multimodal clinical conversation summarization. And the social motivation behind this work was the increasing deficit in the number of healthcare workers and also the increasing use of internet for healthcare activities as we observed during the COVID-19 pandemic. The main contribution our work does is create a framework which diagnoses a disease and then summarizes a patient's self-report and initial symptoms and then forwards it to a doctor for primary investigation. We have also built a data set to this cause and used external knowledge for improving the quality of our summaries. So please do visit my poster so that we can discuss in details about this. Thank you.
Thank you. Next is Subin. No, Subin. No. All right. Annapurna.
So we two actually came together to submit the poster.
Hi.
Do you know?
Hi, I'm Anju.
I'm Annapurna Valiveti from IIIT Bangalore. So do you know that if a cryptography protocol is implemented on the hardware, we can extract the secret key without while still respecting the underlying assumptions of the cryptographic protocol. These attacks are known as side channel attacks. So it will be using the characteristics of the underlying hardware to break the cryptography protocol. But there are countermeasures to defend the side channel attacks. Always the question is how efficient they are. So we came up with an approach where we will be implementing our countermeasure with 80% improvement in the execution speeds. So if you want to know more about the optimization techniques, please visit our poster. We can discuss in detail. Thank you so much.
Asif?
Morning, everyone. So graphs which can be drawn on the plane without edges crossing are called planar graphs. Planar embedding problem is that you're given a graph and you have to decide whether the graph is planar, and if so, give a embedding of the graph. So we know that there are linear time algorithms in the sequential setting and log n time algorithm in the parallel setting. These are well known. We study this problem in the dynamic setting where the graph is ever evolving. Edges are being inserted and deleted, and we are expected to update the embedding after every such operation, which is deletion and insertion of edges. So there has been extensive work on this in the sequential setting in the dynamic model. We studied this in parallel setting, and we show that after edge insertion and deletion, we can recompute the embedding in constant time given polynomially many processes. So please visit our poster to know more. Thank you.
Thank you. Next is Debadrita.
Hi everyone, I'm Debadrita from IT Kharagpur. I'm here to present our work Twin SSE, which is a disjunctive SSE scheme with linear storage. So basically with the advent of cloud computing, big data, now the problem of encrypted outsourced computation is the holy grail of modern cryptography. So we look into a class of crypto primitives called searchable symmetric encryption that provisions a client with search capabilities over encrypted data that has been outsourced to a third-party cloud server. So in this work, we try to provision the client with disjunctive query capability over encrypted data with very efficient search time complexity and very low storage overheads. So to know more about this work, please do drop by my poster. I'll be happy to discuss. So this is another work that has been done on the same topic on searchable symmetric encryption. So basically, the existing searchable symmetric encryption schemes in literature that supports conjunctive queries typically on encrypted data are classically secure. Like the security assumptions are mainly based on discrete log hard groups. So, but these discrete log hard groups are quantum broken, basically in the presence of a quantum adversary. So in this work, we try to find a solution to this, and we devise the first lattice-based SSE scheme that supports conjunctive queries over encrypted data. Our hardness assumptions are based on hard lattice problems like learning rounding problems or short integer solution problems. We got some interesting results. If you want to know more about this work, please drop by my poster. I'll be happy to discuss. Thank you.
Thank you. Next is Utkalika.
Hello everyone, I'm Utkalika from IT Kharagpur. Today I am going to present on the paper titled ProTrack, Distributed Provenance Tracking over Serverless Application. So basically we have tried to fuse both application logs and system logs to trace back the provenance of some process. So basically provenance means the origin or history of some process, and using those data, the universal log, which is created by fusing application log and system logs, we try to generate a universal provenance graph. So basically a universal provenance graph has the nodes which depicts the process or the objects of system, and the ages are depicts the system calls or the timestamps or the causal order between the events. So to know more details about our work, please drop by my poster. Thank you.
Thank you. Next is Manoj.
Good morning, everyone. I am Manoj Kumar from IIT Delhi, and I have worked on graph portioning. So in this work, we have developed a unique and generic optimization-based graph portioning algorithm. So this is the graph portioning algorithm. It considers both graph metrics as well as feature metrics to do the portioning. And for more details, you can visit my poster. Thank you.
Thank you, Manoj. Next is Nitesh.
Hello everyone, I'm Nitesh from IIT Kanpur. On the screen is our tool exist that synthesizes invariant for probabilistic programs. And so you can basically, so for deterministic imperative programs, synthesizing invariants is hard. For probabilistic programs, it is even more harder. So if you want to unfold the mystery of probabilistic programs, what are probabilistic programs, why is it hard, and what are invariants, do drop by my poster and I'll be happy to discuss. Thank you.
Thank you, Nitesh. Next is Shravani.
Hello everyone, I'm Shravani from ISC Bangalore, and today I'll be talking about our work on secure multi-party computation, which got accepted to Eurocrypt 23. So our work focuses on a setting called as perfect security, wherein broadly there are two categories of protocols. The first one, where the round complexity is dependent on the number of parties n, and the second where it's not. So in the first category, linear communication protocols were known from way back in 2008, but the second category lagged significantly behind at n power 4. So in our work, we close this gap with an improvement of NQ and give a linear communication complexity protocols with expected constant round. This brings in significant improvements in terms of the amount of communication and time, and which is what is visible on the slide. So do visit the poster to know more details. Thank you.
Thank you, Shravani. Shyam.
Hello everyone, my name is Sham. This is the joint work with my guide, Professor Srinivas Vivek. So we provide, in this work, we give an attack on the, to derive locations of drivers in a ride-hailing setting using triangulation by colluding adversary riders. If you want to know more about what this is all about, please come talk to me. I'll be very happy to answer the question. Thank you very much.
Thank you, Shyam. Next is Mohit.
Hello, everyone. I'm Mohit Sharma from IISc Bangalore. My work is focused on bivariate analysis of electronic transitions using topological structures. In this image, on the top left, two fields are shown which are used to characterize an electronic transition. On a very high level, they mean amount of charge lost and amount of charge gained at every point of the molecule. And our goal was to identify those regions in red and green, which represent donor and acceptor regions, and to analyze them further. For this purpose, we utilized a variant of discrete scatter plot called continuous scatter plot and suggested two operators based on that. On bottom left, we have CSP lens operator. It takes the complete CSP as input and queries which we want to run. And based on those queries, it segments the CSPs in the desired output. The horizontal one represents donor regions, and the vertical one represents the acceptor regions. On the bottom right, we have CSP peel operator that takes extra information to segment the domain and further extract some layers of the CSP. Based on these two operators, we present interesting insights which were useful to the chemists. If you want to know that, do visit the poster. Thank you.
Thanks, Mohit. Next is Bhavish.
So hello everyone. I'm Bhavish from Indian Institute of Science. I'm here to present our work, Shield Secure Allegation System with Stronger Security Guarantees. So allegation escrows are systems put forth in organization to curb malpractices, harassment, abuse, etc. It requires appointing a chief vigilance officer, and the victims are expected to submit their allegation to the CVO, and the CVO is expected to notify it to the higher-ups. However, when the perpetrator is close to the CVO, there is a threat of retribution when the CVO leaks it to the perpetrator. To address these privacy concerns, we propose secure allegation escrow system where multiple distributed servers effectuate the role of CVO such that no individual servers learn any information about the allegation. And we rely on the technique of secure multi-party computation to achieve this. To know more about secure multi-party computation and my work, please visit my page. Thank you.
Thank you, Bhavish. We have Praveen next.
Hello everyone, I am Praveen Kumar Sunsare from RCOM Nagpur. This work is done with my guide from PIT Vellore. So this work is based on to detect protein secondary structure prediction. For that, the input is amino acid sequence. So in our work, we find out the local pattern of the amino acid sequence as well as long range interdependency between amino acid sequence which affect the structure of the protein. For that, we design this hybrid model in which we tune the hyperparameter with some optimizer. To know more about this, kindly visit my poster. Thank you.
Thank you, Praveen. Satyam.
Hello everyone, I am Satyam Singh, PhD student from IIT Delhi. The title of my poster is Online Piercing of Geometric Objects. This work was presented in FSCTCS 2022. In the online piercing set problem, the whole object set is not known in advance. The objects are going to come one by one, and upon arrival of the object, you have to maintain a valid piercing set by taking irrevocable decision. Surprisingly, there was a lack of study in the literature for the online piercing set problem, and we have obtained some general results for d-dimensional flat objects. To see the relation between the covering problem with the piercing set problem, the applications of the problem, and the results obtained by us, please do visit our course. Thank you.
Thank you, Satyam. Suhi is next.
Hello everyone, I'm Shubhi from IIT Kharagpur. And in this work, we have found the timing vulnerability in PyTorch's max pool operation caused by a simple branching statement. And we found that using this or exploiting this vulnerability, we can basically determine the class influenced by a target CNN model. Further, once we know these classes, we can also exploit this classifier to bypass PyTorch differential privacy and leak information about the training data being used by the target model. So we also proposed the countermeasure for this by proposing a constant time max pool operation. And we reported this to Meta as well, and they validated this leakage. So this work was presented in CHESS 2023. And for any further questions, you can drop by my poster. Thank you.
Thank you, Suhi. Vidyasagar is next.
Hello everyone, I am Vidyasagar Sharma from TFR Mumbai. This work is from UAI 2023, and in this work we work on acyclic directed graphical model where we use DAG to represent conditional independence relation between random variables. There can be more than one DAG that represents the same set, same conditional independence relation, and such DAGs belong to a class called Markov equivalence class, which is graphically represented by union of such DAGs. There's an interesting combinatorial problem that we have given a graphical representation of an MSC, and we have to answer how many DAGs belong to this one. This problem becomes number hard when we add an additional constraint called background knowledge. We solve this problem. We give an FPT algorithm, fixed parameter tractable algorithm to solve this problem. For more detail, please visit my poster. Thanks.
Thank you. I'll just request all of you to speak closer to the microphone so that you are audible. Next is Utsav.
Morning, everyone. I'm Utsav from CMI. So this work is jointly done by with Orkodev Chattopadhyay from TFN and Partho from CMI. So far now, after NIRA's talk, you guys all know what is algebraic complexity is. So it deals with computing polynomials using algebraic operation. And the notion of hardness, which is easy or hardness, it is also there in the algebraic complexity model. And these are called VF, VP, VP, and VNP. And the inclusion in the same order, but the strict inclusion is wide open. So we come to a restricted model, which is called monotone model, where cancellation is not allowed. Thankfully, in this model, this inclusion is strictly known. But in this work, what we did is we gave sort of a unified approach to prove all these results using a single polynomial, which is called graph inner product polynomial. We're changing the graph topology, which give you different results. So, to know more, please visit the poster. Thank you.
Thank you, Utsav. Next is Yashwant.
Hi, I'm Yashwant from IIIT Bangalore. Today, I'll be presenting our work, which is on multidimensional persistence diagrams. So what is a persistence diagram? It is a descriptor which represents features as a sets of points in the plane. Consider this example of the mountain range. Actually, here there are like multiple mountains. In the persistence diagram, actually, if you look at it, each of these mountains or peaks will be represented as a point, and the coordinates will depend on the height of the peak. However, to analyze, say, the temperature across the mountains, it actually varies on multiple parameters such as latitude and altitude. Therefore, we would like to develop a descriptor which captures features based on multiple parameters and not a single parameter. For this, we developed the multidimensional persistence diagram, MDPD in short. To compare two MDPDs, we also developed a distance measure and show two applications. The first is in the problem of shape matching. The second is the problem of detecting bond formation between platinum and carbon monoxide molecules. If you find this interesting, please visit our poster for further details. Thank you.
Thank you, Yash. Next is Prashant.
Good morning, everyone. My name is Prashant. I'm from IIIT Hyderabad. My research work primarily revolves around code mixing. Code mixing is where people mix two or more languages. And this is problem of relevance, especially in multilingual societies like India, where phenomena like English, Tanglish are quite common. So, and it so turns out that this mixing of two or more languages is not really random. There are some patterns which are more preferable than others. So what we propose is a metric called SIMCOM, which sort of encodes this notion. But what is the utility of this metric? What we want to do is we want to understand if these metrics are capable enough of differentiating between a acceptable versus an unacceptable sentence. I will point you to those 4 examples. And if I ask you which sentence is okay, which sentence is not okay, I'm sure I'm going to get various opinions. So that's what we did. We crowdsourced this data, created a data set out of it, and then we tested whether these models are good enough, multilingual models or models like ChatGPT are good enough at this task. So for getting to know about more of the research, please visit my poster. Thank you.
Thank you, Prashant. Shreyansh is the next.
Good morning, everyone. I'm Shreyans, PhD student in IIT Jodhpur. So we published a survey on biometric crypto system and their application in Computer and Security Journal. So in this particular survey, we actually present more detailed explanations about different techniques that we need to implement biometric crypto system. And we have also introduce a new domain that is decentralized biometric crypto system, and we also define some potential applications in open problems. So if you want to discuss more about these potential applications and open problems, please visit my poster. Thank you.
Okay, thank you, Shreyansh. Next is Sahiba.
Hello everyone, I'm crypto enthusiast and also a TCS sponsored research scholar. So our lab actually works in cryptography field, in applied cryptography with some ongoing works, and also we are exploring the post-quantum and quantum era. Not only that, we are also work in the core cryptanalysis, and this poster actually is in this core cryptanalysis field, in which I have analyzed the hash function. So if you are curious how this hash function works and how is it secure, so you can stop by my booth. And by the way, my name is Sahiba. Thank you.
Thank you, Sahiba. Preetam comes next.
Hi all. So this is joint work done with my advisor, Professor Mayank Singh. So let's say we have this unlabeled test classification data set and we want to annotate it. So ideally what generally people do is like they utilize all the annotation budget. So what if we can do the annotation with much lesser annotation budget on a condition that the performance would be the same as the maximum annotation budget. So apart from this, we have done another study like how this model performance varies as we add on more and more annotations. So to find out more, please come visit my poster. Thank you.
Thank you, Preetam. Shivani, you are the next person.
Hello everyone, I'm Shivani from IIIT Delhi, and today my poster will be about our AAAI work. So basically, in a dialogue, just detecting which utterance is sarcastic might not be enough for a chatbot to understand the underlying meaning of the dialogue. So in this work, we propose a task of sarcasm explanation, where we try to generate natural language explanation for the sarcasm that is present in a dialogue. While doing so, we handle multiple challenges like code mixing, multimodality, and fusing of multiple information. To see how we handle these challenges and how these generated explanation help in the understanding of other affects, do visit my poster in the evening. Thanks.
Thank you, Shivani. Aditi.
Hello everyone, I'm Aditi. I'm a grad student at IIT Gandhinagar, and my work primarily revolves around resource allocation, wherein there is a set of items which is to be divided among a set of rational agents in a way that everyone is happy, where people do not kind of envy other people. Applications of this work range from being as casual as dividing a dinner bill among a group of friends, or as crucial as dividing a set of scarce resources like vaccines among different states. In this work, which was accepted at SAGT last year, what we do is when we achieve fairness, we might have to suffer loss in the sense of collective welfare of the entire system. In this work, we quantify that loss by giving tight bounds across a range of welfare notions. I'll be happy to talk more about that poster. Thank you.
Thank you, Aditi. Sunil, you are the next.
Hello everyone, I'm Sunil Saraswat from TIFR. In this work, which was presented last year at FSTTPS, we talk about design and regulation of exchanges. Recently, there have been several instances of stock exchanges violating trading rules. The potential reasons for these violations are ambiguous regulatory guidelines, inadequate implementation of guidelines, or undetected bugs in the matching program used by the exchanges. To solve this, we provide a robust framework to effectively and provably tackle these challenges. We provide a formal framework to specify, design, and monitor continuous double auctions, which are widely used by the exchanges. We develop a checker backed by our uniqueness theorem to detect these violations. To know more about this work, please visit my poster. Thank you.
Thank you, Sunil. Let me now invite Ranjana.
Hello, everyone. This is Ranjana. So I'm from IIT Ropar. So my current PhD domain is on few shot learning for medical image analysis, and this is one of the work that got accepted in SB 2022. So as we know that in medical imaging, we do not have such a luxury of a big domain space. So that's why many techniques have come up, among which meta learning is one. So if you want to know more about my domain, then please visit my poster. I'll be happy to assist you. Thank you.
Thank you, Ranjana. Let me now invite Dhanajit.
Hello, everyone. I'm Dhanajit, and I'm excited to present our CPR 23 paper, a probabilistic framework for lifelong test time adaptation. In TTA, we are flipping the traditional domain adaptation way of doing things. So we take a model trained in the source domain and adapt it in the test domain without the labeled data. We propose PETAL, a principled approach for online lifelong TTA. We provide a Bayesian formulation which naturally leads to the student-teacher loss plus a regularizer that captures the posterior of the source domain data. So swing by our poster to ignite some epic discussions. Just like petals in the breeze, let your learning model soar with lifelong TT on the fly. Thanks.
Thank you, Dhanajit. Let us now welcome Prashanjit. Okay, so next is Sahil.
Hello everyone, I'm Sahil from IIT Delhi. I'm going to present my work on lifelong learning to solve mixed integer programs. So in this work, we focus on learning to solve NP-hard problems using the instances of those problems. And we show how learning to solve these problems can actually help reduce the running time of ILP solvers for a variety of NP-hard problems. And then we focus on a streaming scenario where the training data to train these models appears in a sequential fashion over time. And the training also happens sequentially. And then we develop a model which can help us in reducing the catastrophic forgetting. So hope to see you at my poster. Thank you.
Thank you, Sahil. Okay, let us now welcome Avinav.
Hi, I'm Abhinav from IIT Kanpur. So in this work, we specifically study the common sense aspect of natural language, which is some implicit knowledge that you have inherently to understand language. So in example shown above, you can see if a person says, I took a flight on Thursday, you immediately understand what might have happened on Thursday. Things like he might have booked tickets, went to the airport, getting your boarding pass, and then boarded the plane. So all this implicit knowledge turns out is not learned in a supervised manner, and humans learn it via experiencing this thing multiple times. So in this work, we show whether this thing can be learned by algorithms as well via reinforcement learning. So we develop a framework for that. Thank you.
Thank you, Avinav. Next is Shweta.
Hello all, I'm Shweta from IISc, and today I'll be discussing our work called Scope Buffered Persistency Model for GPUs, published in ARCS 2023. Prior work shows that multiple applications can benefit from both the persistence provided by persistent memories and the parallelism provided by GPUs. These include applications like GPU-accelerated persistent key value stores and checkpointing for long-running DNN kernel. However, these works do not define a persistency model. A persistency model describes the order in which writes to the persistent memory become durable. While a plethora of work has been done in defining and describing persistency model for CPUs, these often do not scale well for the highly parallel GPU architecture. To this end, we propose scoped buffered release persistency model for GPUs. To learn more about this, please visit my poster. Thank you.
Thank you, Sweta. Let us now welcome Simran.
Hello all, this is Simran from IIT Madras. So my poster is about a work on broadcast trace and revoke, which appeared last year at Eurocrypt. So to give you a brief idea about the primitive, so imagine a content provider who wants to share some data with its subscribed users. To do so, what it does is issues a user-specific secret key using which the users can access the data. Now, imagine that one of these users turn out to be malicious and sells these keys for their personal gains. Then the guarantee is that the content provider can trace back to such users and revoke their functionality. To more about this, please visit my poster.
Thank you, Simran. So we are almost done. Dilay, Vivek, and Yash, just come closer, and we are going to start with Dilay.
Okay. Good morning, everyone. This is Dilay Parmar, currently a final year PhD student and a scientific officer at SNIT Surat. I primarily work on designing novel location privacy enhancement techniques for the edge and vision environment. What do we mean by location-based services? Location-based services are type of applications which requires location information of users in providing services. Google Maps, Strava are some of the examples of location-based services. But if you provide your location information, at that time your privacy can be breached. Okay, because location information can act as a quasi-identifier for the user. So in order to preserve the privacy, dummy generation-based technique is one of the techniques. However, this state-of-art location privacy technique suffers from certain issues, and there are certain attacks. So we overcome these attacks in our work. And if you are interested to know more, please visit at our poster. Thank you.
Thank you. Okay, we have next Vivek.
Yeah, hello all. I'm Vivek Shahare from IIT Dharwad. So this work was presented in SPA 23, and it will be talk about the unbalanced unlock situation in the popular lock. So we have to remedize that, analyze that, and then we come up with the performance measurement for that. So we found out that there were no performance penalty in the remedies that we propose for the popular lock over here. Yeah, thank you. For more detail, you can drop by my poster, and I'll happy to take your questions. Thank you.
Thank you, Vivek. Then Yash.
Hi everyone. So my name is Yash and I'm from IIT Delhi. So coming on to the problem statement, so if you can see, Archive combinedly receives like 15,000 submissions monthly, and videolectures.net and underline kind of receives 5,000 submissions monthly. So it's kind of tedious to go through all the submission, and you have to figure out which ones to read and which ones to ignore. So well, for that you can always go through the abstract or the video synopsis, but sometimes it's very long, too informative, or it's time consuming. So how about we generate TLDRs, like a 2-line summary which can give you an overview of what the video or what the paper is talking about. So now how to generate those TLDRs? Let's discuss that over post break. Thank you.
Okay, so this brings us to the end of the lightning talk session. And thank you for bringing up this beautiful collection of works. And next up is the ECR talk. So we're going to start with that. Thank you once again, and continue to enjoy ARCS.
So while we are setting this up, let me also take this opportunity to thank Karthik and Arpita for doing a great job of filtering through all the submissions, and all of you again for sticking to the time. I mean, I was wondering how you're going to do it in 1 minute, and fantastic. And nice to see a variety of talks and the diversity in terms of areas as well as the geographical regions. So Okay. So after a series of lightning talks, now I will get to the thunderous talk. ACM India instituted 3 awards about 4 years ago to celebrate and award excellence in computing. The award for outstanding contribution to computer science education was won by Professor Sudeep Mishra, who's being there from IIT Kharagpur. And he gave a keynote talk in the annual flagship education conference, Compute, that happened about a couple of months. And the outstanding contribution for computing by a women award was won by Nutan Limaye, and you heard her yesterday. And Siddharth Burman has received last year's ACM India Early Career Researcher Award. And his jury citation says, for pioneering contributions to important problems at the intersection of computer science and microeconomics, in particular to algorithmic game theory and to the theory of fair and efficient resource allocation. So Siddharth is an associate professor at the Department of Computer Science and Automation at IISc Bangalore. He obtained his bachelor's from IIT Varanasi and received his PhD from University of Wisconsin-Madison. And after a postdoc at Caltech, he's been at IISc. So Siddharth has been a recipient of several awards, including Young Engineer Award from Indian National Academy of Engineering, Associateship from Indian Academy of Sciences, Ramanujan Fellowship from Science and Engineering Research Board, and Pratiksha Trust Young Investigator Award from IISc. And today he's going to be talking about algorithms for collective welfare and individual fairness. Please join me in congratulating him and welcoming Siddharth.
Thanks for the introduction. I trust I'm audible. Let me take this opportunity and start by thanking ACM India for this honor and also Persistent Foundation for their generosity. I am going to take the word early career to heart and work like a naive, optimistic graduate student for the coming year. Also would want at this time to thank my mentors and endorsers, in particular, Yanis, Federico, Ariel, Prasakkana, and Professor Narhari. I feel lucky to be surrounded by wonderful colleagues at the Department of Computer Science and Automation at IISc. In particular, I'd like to acknowledge Arindam, Anand, and Rahul. It's great to have colleagues with whom you can not only share credit of your work, but the joy of such events. And thanks to the algorithms group for that. Also, I've been privileged in the last few years to have had the opportunity of working with spectacularly wonderful graduate students, interns. All of the results I'll talk about today is in collaboration with them, and I'll give due citation when I talk about the particular results. So with this important note out of the way, let's get to the technical part of the talk. My vision for this presentation is that it is an invitation. It's my invitation for you to fair division. I want to articulate in the next 55 minutes, an hour, why I'm so fascinated by this field, why I feel a great sense of joy when working on these problems. And this is a field, fair division is a field which is sort of filled with beautiful dichotomies. It's a field that is extremely deep. It has connections to mathematical topics such as topology, extremal combinatorics, matroid theory. And at the same time, it has scope for very simple ideas. I'll tell you a very important, a very fundamental result that was obtained in the last few years. And they're extremely simple enough that if you give me 15 minutes and a keen undergraduate student, I will be able to explain that result in its complete generality. Like end-to-end proof can be explained that simply. So sort of, yeah, goes through this entire spectrum of techniques, tools. Also, it's an area that's both very modern, like we are using a lot of machine learning tools, AI tools for making socially sensitive decisions, for making financial decisions, using algorithms for deciding resource allocation. And in that sense, these problems are very modern. We have to look at these large settings of where ML and AI is used and talk about fairness in a principled manner. So it's a very modern field. At the same time, it's a very classic field. The mathematical study of fair division actually dates back to the 1940s with the seminal works of Steinhaus, Banach, and NISER. In fact, there are biblical references to fair division. I'll give you an example. This is a story from the Bible, but Abraham and Lot want to fairly divide a piece of land. What do they do? So Abraham starts, considers this entire land and partitions it, marks a division such that he is indifferent between the two people. So there's a virtual line drawn. Abraham says, I'm happy with either of these two pieces. Give me the left, give me the right piece of land. I don't care. I am indifferent. So with respect to Abraham's preferences, with respect to his valuations, these are two equal pieces. Now, the second party, Lot, comes and picks his favorite among the two. This is called the cut and choose protocol. It's used to divide cakes or sweets between kids, but the story is actually from the Bible. And this is indeed a fair division. Like from Abraham's perspective, the cutter, he's indifferent between the two pieces. So it doesn't matter what Lot picks, he will not covet his neighbor, he will not envy Lot. And Lot, among the two pieces, got to pick his more preferred piece based on his choices. So he will also not, at the end of it, envy Abraham. But that's a very classic reference to, in fact, a method and algorithm for fair division. I mean, in fact, if you trace back the genealogy of this cut and choose protocol, it in fact goes back even more to a 7th century Greek epic poem, Theogony. So this field is in fact classic in a Greek sense of the word. Right, and more importantly, it has a lot of potential for impact. It's a field at the interface of algorithms and computer science, where you do see a lot of applications very immediately. In a few minutes, I'll talk about mathematical formulations, I'll talk about technical results, I'll talk about models and frameworks. Nonetheless, I do want you to keep these applications, keep these examples that I'm about to mention at the back of your mind. Everything I'll talk about, the theory I'll talk about, aims at addressing such applications. And this is something which I think should be an active frontier for research. Data-driven approaches, prototypes, actual tools based on what I'm talking about should be developed even. So here are some applications, and the first domain I want to talk about is very natural. So anytime we are doing a resource allocation, a scarce resource allocation, fairness is an important objective. It's a central desire. For example, and I'm going to give references. This is not for technical exposition, but what I want to highlight is that these problems I'm mentioning, these examples, are in fact being studied. They have been faced in the real world. So these are real world applications. And one is this public housing unit where you have resources, in this case, government housing, and this has to be distributed fairly among a group of families. So it's a limited resource. It's an indivisible, discrete resource. And you have to account for families' preferences, and you have to be fair across, say, different ethnic groups, and so on. So that's one important application. You can think of food donation. Again, imagine like a food center, a central place where food donations are coming in, and what you want to do is distribute it among different soup kitchens, different outlets, different cafeterias, but you have to also account for the fact that this food is a limited resource, and different outlets have different demands, there are different preferences, and you have to now formalize or be systematic or principled in how you go about doing this. Courses, again, a problem that we face enough in academic circles. You have limited seats in a class, you have limited seats at an institute, and you want to be, again, fair. You want to have some system of ensuring there's enough representations, and at the same time take into account preferences of students, their liking for certain subjects, so on. And finally, like more common resource allocation settings like load shedding and when, say, electricity is limited. How do you now divide this limited resource, which in this example is electricity, among different individuals, which could be different regions of the city or different cities themselves? And not just resource allocation settings, things like rent division and all have to be done fairly. There's this very widely used website called splitit.org. In fact, a bunch of notions I'm going to talk about today are implemented here, and there's this useful like data to sort of back up how popular these are. finally, not just resource allocation, but this goes back to more how ML or AI tools are used in decision making. And there again, fairness is a very central objective. It's an objective that has to be done in a principled manner. You cannot be a bit lackluster about it. So here are three examples again where in some sense you are forced to talk about fairness. One actually goes back to this seminal work of Thompson that really kickstarted this entire field of bandit learning, this regret minimization, online learning. So it's a very important piece of work where you have to you have K drugs at your disposal. You do not know the efficacies of these drugs upfront. Individuals are walking in and you still have to administer them. Find out a better drug while being fair across the population as you administer these drugs in sort of a sequential manner. Display ads, again, you have different possible ad configurations. You can show them to a bunch of users and still you want good user engagement. So we learn as you go along online. Fairness, again, is an important consideration. Gig economies, you have these online requests coming in. You have to assign workload to different travel agents. You want to compensate them fairly. You want to ensure that you're not overworking certain small subset of individuals. And fairness has to be baked into such systems. And what I'll do is, with this backdrop of applications, I will talk about the theory for fair division. I'll talk about a systematic, rigorous way where you can develop ideas, notion, constructs, algorithms, and connections for such applications. What I'll do for organizational purposes is to partition the talk into two pieces. The first part will talk about welfare, and the second part will talk about individual fairness. Roughly, the point is welfare looks at the collective as a whole and tries to do well for this entire group at a time. Individual fairness, on the other hand, ensures intrapersonal guarantees, where you want to look at individuals and say that as an individual by individual, I am achieving some fairness guarantee. By no means am I saying that these are orthogonal directions. They are richly connected. My sort of partitioning along these two parts is more organizational. It's just for ease of exposition and to highlight the lay of the land. And it gives me a way to talk about my results in this space, my joint works in this space. So let's start with welfare and why is it important for an algorithm design? So to understand the significance of welfare, all one has to do is to go back and look at how important metrics are in our academic pursuits. A vast body of work in computer science is dedicated to chasing after metrics. The latest and greatest models in machine learning are defined using metrics like accuracy. In fact, they're crowned the king, sometimes based on a second decimal improvement. Things like average rating, right, really determines exposure of products on e-commerce websites, which directly translates into revenue. Other more formal metrics like regret are actively studied in fields like reinforcement learning, online learning, where you do want to develop better and better algorithms that perform on such metrics. And fixation with metrics is by no means academic pursuit. I can look at that corner of the room and talk about CGPA, CTC, and look at this side of the podium and talk about citation count. The list is long and sometimes painful, but it's there. Institute rankings, so on and so forth. What I want to point out is a very serious observation, but it should hit me. The fact is that typically, and for no fundamentally justified reason, these metrics turn out to be arithmetic means. They are natural averages. You look at a list of numbers and you want to assess the quality of this list. Now, what you do is just take the mean, you take the average. CGPA, it actually says, how did you perform on average in your courses? And you should be able to say that, okay, there are better ways to assess my transcript than just a single average. It's still a good metric. It has utilitarian benefits, but it's certainly not following from some axiomatic or principled foundation in many of the cases. Let me give another example to sort of hit this point home. Imagine you have it's been 2 minutes since someone talked about LLM, so I should rectify that. So imagine you have a large multilingual large model, and it's running on different languages. It's running English, Hindi, and so on. So it does well on a collection of languages. It does it say impressively well, but there are also languages on which it performs rather poorly. The average would be high, right? Like, I mean, the average accuracy would be good, but would you still rate it as a fair or as a universally good model? No. You can look at income inequality, and this fact will be even more clear. You can look at average incomes, but you could have a significant wealth gap. So ultimately, while good, while utilitarian, while good for engineering exercises, is certainly not a silver bullet. And this is also highlighted by the paradigm shift that I mentioned, that now algorithms are used for socially sensitive contexts. You need to be aware of it. And here is my viewpoint. Here's the perspective. It's a very sort of simple observation, but it drastically impacts one's worldview. And the point is that in many such cases, you can look at algorithms as actually policy, economic or social policy, and you can consider the output of these algorithms as something that's directly inducing welfare. So imagine an application, imagine an algorithm that's deciding on loan applications. Which individual gets which drug, it's affecting the efficacy of the drug that you receive. So certainly something that's inducing the rewards environment. And I do want you to be imaginative about this word reward. It's not always in a monetary sense. It could be even more general. Like for the large language model I mentioned, it's the accuracy, and the reward is the accuracy of the model on a particular language. So now with this perspective, I want to view algorithms as an economic, social policy. I can now stand at the shoulders of giants from mathematical economics, from welfare economics, and use metrics that have been developed over the years in that field to assess the performance of algorithms, to sort of walk away a bit to complement, let's say, the standard metrics of arithmetic mean. And that is it. That is what I want to do. I want to develop a systematic, formal framework for assessing quality of algorithms using metrics and performance welfare functions that do have a lot of underpinning, that do have a lot of principle in. Okay, and in particular, I'll focus on a welfare function which is called Nash social welfare. I'll just define it in a few minutes. And furthermore, I will talk about regret in online algorithms. Think of it this as my instantiation for this worldview, but the takeaway should be much more broader. The takeaway should be that whenever you now run into a metric, you should ask why before chasing it. Is this relevant, especially if the algorithm is doing something socially important? And so this is like the formal version of the viewpoint. I want to quantify online learning. I want to quantify bandit algorithms using this idea called social welfare. So quickly, I will describe to you both parts. So the Nash welfare comes from math econ. The bandit algorithms comes from online learning. I will detail to you both the models, and I'll quickly join. Okay. And even before I go to the model, I can just tell you the main result. This joint work with, I'll cite the reference, but the idea is that we are able to achieve like interesting bounds, in fact, tight bounds, even for this new definition of regret, even for this tendering of it. Okay, so first part, bandit, second part, Nash social welfare. So let me do the first thing, bandit. Extremely well-studied area. Books have been written on it. It's a very active field of research. It dominates many premier theoretical ML conferences and has been there for decades. What the model is what the framework is, it tries to capture sequential decision-making in uncertain environments. So here's a very simple instantiation of it. There are many generalizations, including things in reinforcement learning and so on. But let's start with the most basic version of the framework, which is that you have sample access to K distribution. You do not, in particular, know the properties of these probability distributions. So you can go to the first distribution, draw a sample from it, or you can go to the third distribution, draw a sample from it. But a priori, you do not know what the means of these distributions are or what the variances are. You only have sample access to them, and you want to fill through large reward. You want to still draw samples that are high. And you want to do this, let's say, for some number of T rounds. And in particular, if you at any round T, in any one of these rounds, if you go to, let's say, the ith arm, the seventh arm, you draw a sample from it, you'll get an arm-specific reward. So it's like, think of these like K black boxes sitting in front of you, K probability distributions. You can pull an arm of any one of them, and it will pop out a reward, and the reward will follow a probability distributions that's hidden under this black box. Okay, and as I said, what if you pull the ith round, if you pull the seventh round R probability distribution, this is the reward you'll get in expectation. You want to get as high number as possible. And notice that in this case, the best thing you could have done, if you knew the statistical properties of the distributions, was to look at the distribution that has the highest mean, the highest expected value, and just keep drawing rewards from that. But you don't know this. This is a benchmark you want to achieve, but a priori, having not seen the distributions or having no knowledge about the statistical properties of the distributions, you do not know mu star. It's the benchmark you want to achieve, but with samples. And the notion of regret, a very well studied notion in multiple fields, once quantifies the performance of an algorithm or says that your objective should be to minimize regret. As in life, here the goal is to minimize regret, which is that you want this average expected values that you have accrued across T rounds to be as close to this optimal mu star as possible. So in every round, you get this expected value based on the ith round you pull. You look at the average, look at the arithmetic mean, and you want this arithmetic mean to be as close to mu star as possible. So as I said, regret initially has an arithmetic mean in it. It's this. You are quantifying the performance of the algorithm by taking an average, but the actual output of the algorithm is this list of T numbers, one for every round. So to hammer this in, let me go back to the drug trials application and connect this model to the application. In fact, this is one of the seed applications that really started this entire field of online learning, this field of regret minimization. So here what you can do is think of the K drugs you have as the K unknown probability distributions. The reward is the efficacy. So if you administer the third drug, the efficacy would follow the distribution based on that. And you have a population of T agents that arrive one after the other in T rounds. And what regret is saying is that, look, there is a drug that has efficacy mu star, that's the best drug in expectation. I want an algorithm where the average efficacy is as close to the best possible efficacy. And you see the problem already. If I could, in principle, develop an algorithm that treats an initial part of the population as lab rats, do a lot of exploration, and then exploit that knowledge to administer a high efficacy drug. This average will be high, even if for an initial part of the population, the efficacy is rather low. It's just the nature of the arithmetic mean. It will balance out if on a large chunk of rounds or for most of these individuals in this population size C, you are doing well. So, and the same thing can be said about user experience and ad displays. I'll not belabor this example. As I said, this has been studied for quite a while, this standard notion of regret, and there are tight bounds known which show that as T increases, this regret decreases, it goes to zero as 1 over square root T. So these are sort of celebrated results and many other low regret algorithms. Now that I've covered multi-arm bandit, let me go to the second vertical, which is welfare. So I'm switching from online learning to mathematical economics and talk about how welfare comes in. And so here the idea is the following. Consider any policy, consider any resource allocations. We have a bunch of resources. I divide it among the audience in the room, or I pick a taxation policy which induces values for a population of size T, or I pick a drug trial algorithm and it look at these as the T efficacies that are induced. So if I change the allocation, if I give different subsets to different individuals, this T tuple will change. If I change my algorithm, these T numbers will change. But the point is, and welfare functions abstractly are quite simply a way to compress this T tuple into a single number. So what you want is a function that takes a T-dimensional vector, a T tuple, and gives you a single number. And using this number, you can decide which tuple is better? Which is this policy better? Is this distribution of values across a population of t individual better, or is some other tuple better? And the way you do it is by applying a welfare function. So you have implicitly or explicitly used arithmetic mean to assess quality of t numbers. If you used accuracy, certainly done that. But as we have discussed now at length, that this might not be a good way to combine numbers to assess the quality of this tuple of t evaluations. You can go to the other extreme and look at what is called egalitarian welfare, wherein you say, I prefer a t tuple of valuations when the minimum is as large as possible. So you want to now focus on policies, algorithms, decisions where the least of individuals in this population is doing as good as possible. But this is completely opposite to the utilitarian perspective of social welfare, arithmetic mean. But right in the middle, beautifully right in the middle, is the arithmetic mean, and this is called the NAS social welfare. Why is it here? Well, it's here because the AMGM inequality tells me that it will be upper bounded by the arithmetic mean, and it's a mean, so it will at least be the min value. And this is the focus. This will be the welfare function I'll apply. I'll use geometric mean to assess the quality of t tuples. I'll prefer a t tuple of distribution of these values v1 to vt if the higher its geometric mean is. And this is not merely a aesthetic exercise. It's coming from a much more principled way. In this talk, in this presentation, I gave you geometric mean, and then I'm trying to justify it. The way it was identified in Math Econ was actually in the following direction. You start with principles. You start with axioms that your welfare function you would like to satisfy, and then see what are the welfare functions here. So you start with axioms, the ones mentioned on slide, and then you move towards figuring out what is the welfare function, and Nash welfare function is one such criteria. It's one such metric that satisfies these important axioms mentioned on the screen. So I'll not have time to detail these, but these are important axioms behind in welfare econ. And just before I complete this thread of thought, let me just give you a quick example to highlight what I'm effectively saying. So if I look at a tuple of valuations where half the population gets 0 and half the population gets 1, and try to compare with another t tuple of values where everyone gets 4, arguably the second one is much fairer. But the social welfare in both cases, the arithmetic mean in both cases is the same, it's 1/4. However, the geometric mean, the Nash social welfare is 0 for the left-hand side one because the 0 and the product gets killed, whereas the Nash social welfare of the all 1/4 is still. So I want to use geometric mean to say which tuples are better. Okay, now that I've given you the two pieces and this conceptual idea, mathematically what we do, at least the formulation part, is rather obvious. We start with regret. It was looking at the performance of the algorithm as the arithmetic mean, as the social welfare it induces. In contrast, what we do is define this notion called Nash regret, where we quantify the performance of the algorithm based on the geometric mean of the rewards or the values it induces. In the case of bandits, it's these expected values of the rewards. So do note that I have not made my life easier in any way. The AMGM inequality tells me that Nash regret is in fact a harder metric to optimize than the standard regret. And as I mentioned, that the classic results that show that you can get tight guarantees for standard regret, average regret. This is joint work with Arindam Khan, Arnab Mehti, and Ayush Savarni, where we show that you can in fact match those upper bounds up to cons. So we're looking at a harder objective. Note that this can be 0, even if a single expected value is 0. Nonetheless, even to our surprise, we get regret guarantees that matches the best known for average. So that's, and uses interesting multiplicative versions of concentration bound and so on. So I will not go into technical details, but again, always happy to talk. So I've talked about now welfare for online decision making, welfare for bandit settings, but I can also talk about welfare in resource allocation. So for the rest of the talk, I'm now going to focus on resource allocation problems where you have a set of resources, you have a population of agents and entities, individuals who want to partition the resource. These individuals have their own preferences, they have their own liking. And your goal is to divide it in such a way that the geometric mean, the Nash welfare is met. So that is your welfare criterion. And you are trying to solve this optimization problem. And the significance of it, I hope, is very clear by. So the same picture, the same set of valuations, and I can repeat the same story as to why Nash is important. I was doing it for bandits. I can certainly do it for resource allocation. Here, in fact, it's conceptually even more immediate. The values are, so if I give the first individual some subset of resources, she accrues some value. If I give another subset of resources to the second individual, she accrues some set of values, and so on. So how do I assess how good this division is? I assess it by computing its geometric mean, its Nash welfare, and I want to find a resource division where this geometric mean is as large as that. And this problem has been studied extensively in the past 5-7 years. Lots of interesting work, starting with the results of Cole and Gatzelis that use convex programs with like market constraints, to like even like interesting heavy hammers like real stable polynomials. And the state of the art is this for this problem. It's an NP-hard problem, so we develop approximation algorithms. But in joint work with Sanat Krishnamurthy and Rohit Pesh, we obtained something like a 1.45 approximation algorithm. So we're looking at indivisible goods. So we're looking at resources that are discrete and cannot be fractionally assigned. So if you recall my Abraham Lot story, land was a divisible resource. I could cut it 2/3, 1/3, or 1/10, 9/10. If instead, if I'm looking at discrete objects like public housing units or course seats, it has to be integrally assigned to individuals. And this does make a lot of difference. Nonetheless, for this combinatorial discrete problems under agents with additive valuations, this is the approximation guarantee we obtained, and this still stands as the best known approximation guarantee for this problem. This 1.45 is interestingly e to the power 1/9, Taylor's number e. So interesting, very natural problem. Suddenly e appears, and I can tell you why. Okay, so that was my part. That was my half an hour dedicated to welfare, and in particular in the context of decision making and in the context of resource allocation. I would now like to move to the second part of the talk, which is going to be individual fairness. And here, earlier I was making collective decisions for the betterment of the whole. Now, individual fairness, think of it as notions or constructs that talk about interpersonal guarantees. And the quintessential notion, the quintessential construct in this case is what is called envy-freeness. I already gave you an example of an envy-free algorithm, the Abraham Lot. In fact, described to you that because Abraham was indifferent between the two pieces and Lot picked the better of the two, this was an envy-free division. More formally, and there are again many notions here like proportionality, maxi-min share, so on. And for the purpose of this talk, I am focusing on envy-freeness, but it is one of the most prominent fairness guarantees that you can aim for in resource allocation. So more formally, what is an envy-free division? You have n individuals. You partition the resources among them. So A1 is the subset of resources or the fraction of the resources that the first individual, the first agent receives. A2 is the subset of resources that the second agent receives, and so on. AN is the bundle or the subset for the last agent. And you'll say that this is an envy-free division if no agent values, covets anyone else's bundle more than her own. In particular, what this equation says is that you pick any two individuals in your population, I and J. Now look at what I values her own subset bundle at. It's DIAI, that's just notation, simple notation. And what the inequality demands is that I's value for any other bundle AJ should be at least as high. So do note that I'm equating both sides of the inequality with I's valuation with I's preference. So I looks at what she has received. He then looks at what someone else has received and still does not want to exchange. He is happy with what has been given to him. This is NV3. And this is a beautiful result by Su. If I give you a heterogeneous divisible resource like land or a piece of cake, technically it's called cake division. So I give you any heterogeneous resource and I give you any number of agents. So I gave you a very simple protocol for 2 agents, Abraham and Lot. But you can have any number of n agents, and under very mild conditions, such a strong fairness guarantee can always be achieved. There's always an NV-free cake division. Any piece of land, any number of agents, as long as their valuations are reasonable, mild assumptions like continuous, you will have an NV-free division. And this result should surprise you. It's extremely general. It has an extremely, I very strongly encourage you to look at Su's proof. It follows from Sperner's lemma, which is a combinatorial analog of fixed point theorem. So when I said it has deep connections, there you go. It has deep connections. And it's a very surprising result. And the result comes with a lot of interesting follow-up work. The fact is that while Stu and Stromquist showed that such a thing always exists, there is a Sanjeevani out there, but Stromquist actually proved much later that in fact there is no finite time algorithm to find such a cake division. So while it exists, forget inefficient, forget exponential time, there is no finite time algorithm to find such NV phases. So now, as like with your hat as a computer scientist, you should be asking, okay, it exists, but if I can't find it, what's the use? So you do search for approximation guarantees, and our group has some interesting works on that. But again, in the interest of time, let me sort of shift focus and not talk about the divisible one, which is more classic, but the more but the thread that has received much more attention in the past few years, which is that of indivisible goods. So land, water, electricity, a divisible resource, public housing, course seats, these are indivisible resources. And here the script is completely different. Forget n agents, even with 2 agents and a single indivisible good, an NV-free allocation might not exist. It's an indivisible good. Either it goes to the first agent or the second agent. The loser will be envious. There's one World Cup, there are 2 teams, and you know what happened. So too soon. Okay. But yeah, NV-free allocations do not necessarily exist when you have discrete indivisible good. However, what has been done is to look at relaxations, and in particular, this is a very important relaxation that has come out of literature in the past 10 odd years, and this is called NV freeness up to 1 good. The idea is you cannot, in the case of indivisible goods, so you cannot, in the case of discrete fair division, guarantee perfect NV freeness. Nonetheless, what you can do is aim to find a partition where the NV can be eliminated by the removal of 1 good. Let me pass through this definition. What it says, it defines a partition to be fair in the sense of EF1, NV3 up to 1 good. If you can look at any pair of agents, I and J, I might NVJ because you are in the discrete world, you are in the indivisible world, but that NV would go away by the removal of some chosen good in J's bund. So if you were to do the following thought experiment, you look at I, and I is envying some other agent J as a thought experiment. You're not literally removing the good, but as a thought experiment, you then judiciously choose a good in J's bund, hide it behind the back, the NV is hello. And the question is, okay, does this relaxation exist? And here's again, I told you there are simple results that are sort of important. Here is one. There's a very nice work by Lipton et al. That shows that such a fairness guarantee, EF1, always exists, and it exists even under monotone set functions. So I can give you valuations VI that only have to be monotone in the sense that bigger subsets have higher values. So give me any set of n agents, and all they need to do is they're happier if they're getting more, a very natural assumption in the case of good. And in that case, you can. EF1 exists. Not only does it exist, you can find it very efficiently, almost quadratic time. So a very strong existence and algorithmic guarantee. And in fact, the algorithm is completely combinatorial. It uses like a very simple graph idea called NV cycle elimination, and given 15 minutes of your time, I can completely explain it end to end without any mistake. That was a very inspiring paper that has spawned a lot of work. And in particular, an important direction now is to understand that, okay, I can get fairness. What do I lose in that? Is it the case that all such fair divisions are economically inefficient? In the sense that here's a way to achieve fairness. It's the cheating way, but what I can do is take all the resources and not give it to anyone. It completely waste it away. It's very envy-free. Everyone is empty-handed. Empty-handed people do not envy each other. So that's certainly not what I'm doing. I'm always partitioning the entire set of goods among the agents and still able to achieve this. So very important sort of conceptual thread has been to understand the efficiency, allocation efficiency with this fairness guarantee. And this again a very important work by Kargianis, Kurokawa, Prokashia, Shah, and Mulinch, Prokashia, Shah, and Wang, that shows that, in fact, I mean, this is a very nice notion, even when you're looking at economic efficiency or allocation efficiency, in the sense that when you have additive valuations, so not monotone, but additive valuations, you can find partitions that are fair in the sense of EF1, and at the same time, Pareto efficient. I'm not going to define what Pareto efficiency is, but it's a very standard notion of economic efficiency. So, and that's a surprising result. You can get fairness without any loss in economic efficiency. The catch, again, as a computer scientist, is what about computation? And that's what we did in this joint work with Sanat Krishnamurthy and Rohit Pash. We showed that not only can you get EF1 and Pareto optimality, not only does there exist an allocation that's fair and efficient in these technical senses, but you can compute such an allocation in polynomials, in pseudo polynomials. And what I particularly like about this algorithm is the design template. It actually uses a construct from mathematical economics in the service of algorithm design. It uses this idea of Fisher market as a model in math econ 2 as an algorithm design paradigm. So this is, to my mind, a unique case where I'm importing things from economics to develop new algorithms. They often, and a lot of beautiful work has gone on at the interface of algorithms and computer science, but it's typically you look at an econ problem and try to develop algorithms for it. Here, the water flows in the reverse direction. You use a Fisher market model from math econ, use it to design an algorithm, pseudo polynomial one, to find these, get these two fairness and efficiency guarantees together. And let me stop early and part ways with an open problem. So this is a question that takes a lot of, spoils my sleep. So my parting gift to you is, you can treat it as a muse or a small dose of insomnia. I'll leave that decision to you. But here is a grand open problem in my field. Here's a problem that so I'm stuck in traffic, you know what I'm thinking. So if you go back to the definition of EF1, the order of quantification is important. And let me re-emphasize that. What is EF1? I'm saying pick any two agents. Now, once you have made that choice, there exists some good, a judiciously chosen good in the second agent's bundle, in J's bundle, this good G, such that if I remove it, the NV goes away. So in particular, I can pick a pair ij and then look at the good that I values the most in J's bundle, remove that and achieve this. So this is for all pairs ij, there exists a good G. But I can strengthen it, and I can strengthen it to obtain the legitimate heir to NV freeness, a much stronger guarantee, which is that I look at every pair of agents ij, and then I remove any good. For all goods, once I remove it from J's bundle, the NV goes away. So this is called EFX, NV free up to the removal of any good. So in other words, what I'm saying is that I might envy J, BI AI might be less than BI AJ, but if I look at any strict subset of AJ, the inequality reverses. So BI AI is greater than BI of any strict subset of AJ. This is called EFX. And the grand open problem is that, do they exist? We do not have counterexamples. Even with a lot of empirical work, like simulations, this and that, there is no counter. So what this is that, and this is open even for additive valuation. So here's a very simple question. You have n agents, you have a number of discrete goods. So the valuations are additive. That is, the value of any agent for any subset is just the value of the goods in that subset. So I can completely specify the input to you in a matrix. Rows are agents, columns are goods. Each numbers specify the value for the agent for that specific good. And the conjecture here is that there always exists a partition that's effectively balanced up to this nice edge. Look at AI, you look at AJ, remove any good, and the values go, it becomes balanced. So this is called the EFX conjecture. Very important problem in discrete fair division. It's my muse. I'm happy to share it with you. But there has been works on approximation and all from our group. I'll be happy to talk about it offline. But with that, let me thank you for your time and thanks again ACM India and Persist.
Hi, thank you for the wonderful talk. So I just wanted to understand one thing about this particular open problem that you're talking about.
Yes.
Do you assume that the value for the any good in J's bundle is equivalent for I as it is for J? Like, do I and J place equal value for all the goods in J's bundle?
So that's called the identical values assumption, and in which case it's easy. In which case this exists, but I'm not. I have individuals who value. So I do have vegetarians and non-vegetarians standing in the buffet line. So some will value non-veg dishes, whereas I'm not assuming. So that's why I keep writing VI to emphasize the fact that I'm looking at distinct individual values. But they are additive.
Right. And do you also assume that the bundles are finite sized?
So this is discrete, indivisible, fair division. Everything is finite.
Thank you.
Make all the right assumptions you want, and the question still stands.
Thank you.
Yeah, thanks for the nice talk. So you mentioned about the NV cycle free algorithm
Yes.
for doing EF1.
Right.
That can only give you certain kinds of NV free allocations. There are other EF1 allocations which an NV free cycle cannot give, can never give.
Yes.
So is there some work on that? I mean, if I want to sort of explore the space of NV free allocations.
Right. So there have been studies on like the number of such allocations, like the counting problem. But you're right. In particular, neither it's. So I can give you like a more technical answer and more. But like if you go back to, for example, this case of both the results, right, like that I was talking about in terms of economic efficiency. This result, for example, so this is EF1, and you're exactly right. It's not the case that will give us all NV3. There could be many, exponentially many EF1 allocations. Though, like the way we obtain it, for example, in the pseudo-poly is completely different. We use market approach. So that's one way of getting another class of EF1 allocation. The way that Kargianis et al. Do it is in fact, by looking at Nash social welfare. They say that, oh, look at an allocation that maximizes Nash social welfare, the object, the geometric mean, and that will, in the case of additive valuations, be again EF1. But yeah, like there is no sort of complete answer to the question of like, is there a method that generates all EF1? That's still open. It's open in that. There are different algorithms known. For additive valuations, for example, you can, in fact, just use round robin. That's a proof I wanted to do, and I'm thankful I decided against.
In some, yeah, I'm not aware of all the algorithms, but
Yes.
round robin or NV free cycle.
Yes.
So these algorithms seem to be maintaining an invariant at every step that whatever they have done so far is still EF1.
Yes, yes.
But an overall EF1 allocation doesn't need to have that invariant.
It does not. And that's one limit. And that's why EFX, for example, is a much more challenging problem. There are examples that show that if you follow this invariant style attack, if you try to maintain EFX and grow the allocation, that will fail to some specific examples. So the entire space of EF1 allocations is not, there's no single method that captures all. There's like you can still find interesting. I mean, I can tell you more interesting problems like beautiful connections. So say I wanted to impose additional constraints on AI, like matrodial constraints or cardinality constraints. And there it does. I mean, I mentioned briefly it has connections to matroid theory. That's one bridge. Right? So yeah, the good questions, but yeah, there's no sweeping answer to this.
Thanks for the nice talk. This is more from an application perspective of this, from the computer perspective. Like you have resources, CPU, memory, disk, right? And your agents are like applications which are demanding it, right? So is there a like study around like using these algorithms for doing fair distribution of these resources between applications, where there may be a relation between agents? Like if some agent is consuming something, then there is a related application to that which may have an impact of that. Are there such studies done around this particular application of these?
Yes and no. So yes, like there are this notion called dominant resource efficiency. It goes back to works from Berkeley that do it. The ECE or like network routing people use ideas like alpha fairness constructs. But at the same time, like what I would suggest is that the first part of the talk, it's worth actually studying those from this geometric mean perspective. So there are works, but I think it's still
more studies.
There's a lot more scope.
Okay, thank you.
And from my point of view, this idea of geometric mean is something worth studying. Yeah, I particularly like personally am interested in such like data-driven approaches or like users. So that will be certainly something worth exploring.
Thank you.
You were using this notion of geometric mean to capture collective social welfare and
Yes.
so on. But if you're using the geometric mean, there's one individual who has a very low value or the arm which has very low distribution, then essentially the rest of it doesn't matter, which means that the individual is holding the community hostage.
Right.
How does that translate to the original objective of community welfare? Because now you have a single individual saying the entire community.
So it's zero is maybe like the pathology of it, but in the sense you could have high, if the population size like you could still afford low values, like non-zero but low values and still is geometric mean could be pushed higher. So there was a critique I mentioned of egalitarian welfare where you look at the minimum. This is exactly that. So at least geometric mean tries to take one step away and does this balance. A more technical answer is there are some extreme like resource scarce environments where someone has to go empty-handed. Like again, one World Cup, two teams. Then the technical way around it is that it's called smoothing. I just trying to cover it, but what you do is you look at the value plus, but add a small number so that this product becomes non-zero. So just shift it by some small amount. And there's also work from our group that looks at subsidies and side payments to sort of alleviate that. But yeah. So this was like your critique is completely the reason why we moved away slightly from equality. It's also called Rawlsian welfare. We're looking at the worst of it.
So this proof carefully constructs this G, is it, for every pair, whereas it doesn't work to change the for all to there exists a for all.
Yes. So as was mentioned by Professor, the algorithm iteratively keeps it. So it picks an agent to give the next. So it's an iterative algorithm. You look at the next agent who can be given the good, and you judiciously pick the good such that this property is maintained. And interestingly, you can maintain. So it's a very natural iterative algorithm, and where you keep selecting the good that certifies EF1 full. What the challenge with EF1 among many challenge with EFX is that if you can pick a good, but your earlier decision might go wrong. So in fact, like if you look at this EF1 algorithm of Lipton et al. Previous slide, it in fact guarantees that you iteratively grow these bundles, keep adding, and you get EF1 with the last added. So yeah, it does that.
So for all
pairs, it's able to maintain.
No, so for all G, the proof doesn't work, you're saying, or
for all G, the proof for sure doesn't work. Yeah. I mean, you can construct examples where that specific algorithm actually fails. So the proof doesn't work and the algorithm as such doesn't work.
Okay. Second question is, what about EF2 or something? Of course, EF1, EF1 exists, EF2 is also, but maybe algorithmically you may find it faster.
Yeah, good question. So good that I actually have answered it. So I told you this next slide. This is pseudo-polling. If you allow me EF2, I can make it poly.
Hello, Siddharth. Okay, I have a question. It's about welfare. I'm here.
Yeah. Hi.
So you explained the Nash welfare scheme. So I understood how it's more egalitarian than the taking the arithmetic. My question is, what if if you want to, are there settings or maybe formulations where where you want to achieve more egalitarianism? So for instance, I see the Nash mean as taking the mean in the logarithmic scale. So can you take a mean over the super logarithmic scale or something like that? So are there both something like that? Just been explored.
So you can generalize this. These are called p-means. So if you remember that picture, where the two ends of the spectrum are the arithmetic and the geometric, the arithmetic mean and the minimum, and geometric mean sits in middle. What you can do is actually have this parametric form. So you look at the p-mean welfare, or the generalized p-means, which is that you raise every value to the pth power. You look at like a norm expression, but divided by 1 over t. So it's mean width of the p powers, and then you take, so it's almost like the norm, except you throw in 1 over t. And a major change is that you look at p that is less than 1. So when p is equal to 1, you get arithmetic mean. It's exactly that. When p goes to 0, you get limit. So when p tends to 0 and the limit, that is what you get. When p goes to minus infinity, this is what you get. So it's in fact an entire spectrum of means that have been studied. And again, so nice a question that we have studied it and we have algorithms.
So does
both hardness and approximation.
Does your result also hold in all these settings, or
it's a general result for any p mean. So starting from here to here, that this is infinite family of p means. You give me the p, there's the same algorithm, it will tell you what the allocation.
Thank
you. Okay, I think there's no more questions. We thank Siddharth again. Thank you. And I request Jayant to give a small token of appreciation. Okay, thank you again. And before you go away for lunch, Abhijat has certain important quick announcements. And after lunch again, we'll continue with award talks. The first talk, or two talks after lunch, is by students who have won doctoral dissertation award, ACM doctoral dissertation award, followed by a number of other talks. The other talk, while he's setting up, let me tell you about the ECR talks that are coming in the afternoon. These are by early career researchers, and this is one of the attractive features of ARCS, I would say, not necessarily very technical talks, but these are by people who have been around in the profession, academic or industry or startup for the last few years, and they want to share their experiences on what they thought it would be on the other side before, while they were doing PhD, and what it is after they have experienced it. So it'll be don't miss those talks as well. Okay. Over to Abhijat.
So this is the critical announcement for people who would want to claim reimbursements. This is the kind of a form that you will need to fill up. I just wanted to give you a quick brief about what is the thing that we need there. So apart from the basic details, we will need a copy, a photograph, scanned copy of this kind of a badge that has been there with you. Okay. And your tickets, soft copy of your tickets, and your bank details. The only thing that I really want to say to everyone is please fill in your bank account number very carefully. Start with a single quote and then put the number. If you ignore that, the initial zeros can be lost and that causes problems. That's a very earnest request from my side to all of you. Please take care when you fill in your bank details. You will find the bank details a little below. This is where you upload a scanned copy of this card. Your total claim amounts. And this is the point where you furnish your bank details. This is the field. Bank account number is the field that I'm talking about. Please help me do the job well. And that will be the rest I can take care of. We also have a QR code. That you can just point your mobile to, and this will take you to the form. Okay. All right. We'll also print copies of these and paste it at various places around around this venue. That's all. Thank you from my side. I can add that to the form. So links to the social media posts, right? Right. So no, for the moment I'll let go. Okay. Yeah. This QR code is there. Huh? I can share that link. I can mail that link also. So we can put it on the website. Yeah. On the annual event website, we can put it up. But that will be tomorrow. I'll put it up on the website after tomorrow. I mean, you get reimbursements because you have attended. Thank you.
Fine.
That is what I'm downloading.
that is at 2 p.m.
Recording stopped.
Hello.
I got it.
Yeah, hi, Yogendra. Are you there?
Yeah. Hi.
Oh, hi.
Am I audible?
Yeah,
Okay.
yeah, you're audible.
We can offer this. We can. Yes. Okay.
Everything is close.
Good afternoon, everyone. I hope everyone enjoyed their sumptuous lunch. So I welcome you all for this yet another enlightening session, which is ACM India Doctoral Dissertation Award. It is my pleasure to be the host of this session. I am Prerna Mukherjee. I am a faculty at School of Engineering, JNU. So today we have winners, two presenters of best works for this session, and shortly we are going to listen to their presentations. I would like to first of all congratulate to both of these winners for this very great achievement and this great award. So PhD thesis, or for that matter, any thesis, is always a great journey, and we have all sorts of mixed feelings and different kinds of experiences, which are definitely worth to be shared and to get inspired from. So before we begin the session, I would like to speak a bit about this dissertation. So the ACM India Doctoral Dissertation Award was incepted in the year 2011 by ACM India with approval from ACM Awards Committee. This award recognizes the best doctoral dissertation from degree awarding institutions based in India for each academic year, which starts from August 1 to June 30 every year, particularly in the current cycle. And this award is funded by TCS, which is the founding sponsor of the ACM India Doctoral Dissertation Award. It is we have a whole pool of great selection committee members, which is chaired by Dr. Somesh Jha, Professor Somesh Jha, University of Wisconsin, Madison, includes other universities like Columbia University, Johns Hopkins, Rutgers, etc. So we'll start the session. We have the first speaker for the session, who is Pranjal Datta. So Pranjal would be talking about his dissertation, which is titled as A Tale of Hardness, De-Randomization and Debordering in Complexity Theory. I'll just introduce Pranjal. He is currently a postdoc at School of Computing, NUS, working with Professor Devesh Agarwal. His broad research area is complexity theory. In particular, he works on algebraic complexity theory, geometric complexity, and distribution testing. He finished his PhD in computer science from CMI under the guidance of Professor Nitin Saxena. During his PhD, he was supported by the Google PhD Fellowship. He obtained his bachelor's and master's both in mathematics and computer science, both from CMI. So let's welcome the first speaker of the session with a huge round of applause, please.
Thank you. Thank you everyone for coming, and it was a nice lunch. So hopefully you'll not be sleeping and listening to some of the talks. So the title of the talk is Tale of Hardness, De-Randomization and Debordering in Complexity Theory, which is the title of my thesis. But I'll try to squeeze some of the parts of my thesis into a 20-minute talk. So it will probably be a micro story rather than a tale, but I'll try to convince you that some of the results are interesting and worth further investigation. Okay. So let me start with something called determinant versus permanent. So Nutan gave a talk yesterday on basics of algebraic complexity, where she introduced some of the basic stuff. And today morning, Neeraj also gave a nice talk on the application of algebraic complexity in machine learning. But what I'll do today in this talk will be a slightly different perspective, computational perspective on algebraic complexity. So let's start. So as we all know, P not equal to NP is basically the holy grail, the main question in computer science, which we'd like to solve. And so the question is basically whether verification is easier than finding a solution. And the conjecture says that yes, probability is true. You can verify easily, but finding the solution should be harder. And there have been some barrier results known. By barrier, it means that there are results where they say that, look, we have been trying to prove P not equal to NP via different proof systems and proof strategies, but many of them will not work. Even if they are proving some mild lower bounds, it will not lead to solving P not equal to NP. And one of the main interesting results were due to Rajvarv and Rudich back 30 years back, where they introduced what is called a natural proof. A natural proof is basically, you can think of, are all the proofs which is very natural in some sense. I'm not going into the definition. So they said that, okay, most of the lower bounds that we have been trying are natural and they will never lead to proof P not equal to. That was actually very heartbreaking situation that time because people merely knew other techniques which could actually lead to P not equal to. And so one of the techniques, one of the very few techniques which is known, which could potentially break that barrier is called the geometric complexity theory, which I work in, and I'll try to describe the basics, the very basic fundamentals of this program. And also, before going to other details, please feel free to interrupt and ask any question. Okay. So, so what is GCT? So, in 2001, Mulmul and Soni, they proposed this program, GCT1, and they said, look, we will try to understand some of the algebraic P not equal to NP questions, which is called the VP not equal to NP questions have been already defined before, or the determinant versus permanent question, which I'll define in this talk. So they said, look, study these problems, but study these problems in a slightly different way, which is called the algebraic approximations, or what they call it, border complexity. And they said that, look, if we can study and understand some basic properties of these two objects that we'll define in the next slide, first, they would probably lead to P not equal to NP, and second, that the proof strategy that we are giving is not natural. So it actually breaks the barrier. Good. So we would like to understand what is the determinant versus permanent question and what do you mean by algebraic approximations or border. Okay. So the main object will be a matrix. So here is a matrix where there are like n cross n. Okay. Yeah. So n cross n matrix where each entries are some variables xij. So now I'll just assume high school algebra and high school analysis, nothing more in this talk. Okay. So remember the usual determinant definition. It's basically you have an n cross n matrix and you are expanding it term by term, like one entry, another entry, and so on and so forth. So this will actually give some polynomial in n square variable in degree n. This is called the usual determinant. That's a basic high school determinant. And there is another polynomial called the permanent polynomial, which is almost similar to determinant, but without a plus minus. Because if you remember, when you are expanding determinant, there is a plus and there is a minus depending on the rows and columns. For the permanent, there is no minus. All things are positive. And you would be surprised to know that actually in this era of learning, so you want to actually learn it. So you have some distribution you want to understand, you want to learn, and you want to eventually understand how close they are or how good they are, the learning algorithms, right? And you would be, so most of the cases you can show that the distance, how good or bad this learned data or learned distributions are actually can be captured by permanent point. Okay, I'll not go into that, but if you like to discuss, I'll be happy to do after the talk. And just to give you an example, so this is a determinant of 2 cross 2, where there is this minus x11, x22, minus x12, x21, but the permanent there is no minus, all is plus. Okay. So what is the determinant versus permanent question? So to do that, let's just call it linear polynomial. I call L a linear polynomial where the degree is 1, okay, at most 1. For example, this 2xx1, 2x11 plus 5x32 plus 4. So constants are allowed like 4, but I'm not allowing any degree 2 or degree 3 and so on, just 1 in each variable. Okay. What is the permanent versus determinant question? Is this. I want to write the permanent polynomial, which I defined already, as determinant of some matrix where the entries are linear polynomials. L11, L12, LIS, these are all linear polynomials. So I have a polynomial permanent and I want to write determinant as a matrix, big matrix, where each entries are linear polynomials, like, as I said, like 2x11 plus blah, blah, like that. And the question is, what is the dimension? What is the minimum S that requires to write this permanent? That's all we are asking. Okay. And Valiant's conjecture basically says that S has to be really large. There is no way you can write permanent as a small determinant. Your S, the dimension of the matrix has to be really large. That is basically called the algebraic mean equivalent. So you could ask, and this is actually also the VV not equal to VNP question in which Nutan and Nidad also talked about. So what is the scenario and why we are studying this? One of the implications is this: P not equal to NP implies this conjecture, and this conjecture actually implies P not equal to NP in some other model, which is called the BSS model. So somehow this variance conjecture is squeezed between two P not equal to NP questions. That is why this is important. And but you could ask me the following question: that look, this seems to be an easier question, but why? I mean, variance conjecture may not actually lead to P not equal to NP. So why even studying this, right? So one of the things would be at least solve the easier question than before solving the P not equal to NP questions. But there are some more motivations which I already talked about, just the breaking the barrier and so on and so forth, which I'll come in the next slide. That why this question is very fundamentally important. Okay. So till now I have been talking about lower bounds, but let me talk about some algorithmic questions, which is slightly different than what I'm talking about, but these questions are related. So what is the PIT question? Now I am saying the same question. I have a determinant of a matrix. I want to test whether that polynomial determinant of A, where again the matrix, entries are linear polynomials, I want to check whether determinant of A is zero or not. What could happen is that when you are expanding this n cross n when you are calculating, maybe things are getting cancelled. You don't know, but you cannot actually hope to exactly calculate everything, because there are like 2 to the n many things. So it will take a lot of time. You would ideally like to solve it very, very fast. The question is, can you deterministically solve this question? This is called the PIT question. And what is known is that there is a very efficient randomized algorithm. If you use randomness, then you can solve this problem very easily. What you do is basically very basic. You basically have a polynomial and you randomly evaluate it to a point. Like basically you have some finite points, you basically pick randomly and evaluate it. If it is non-zero, the actual polynomial is non-zero. If it is zero, the actual polynomial is zero. But this requires randomness. This is basically this why this is in BPP. The question is, can we de-randomize? So can we remove the randomness from this? So this also tries to solve, there is a famous conjecture of BPP equal to P, where basically it says that all the problems that we can efficiently solve using randomness, can we actually de-randomize it? Meaning, can we remove the randomness with slight blow up of time complexity? Maybe I'm solving a problem in 1 hour with randomness, maybe in 10 hours I want to solve that problem without randomness, but can we always do? And it turns out that there are some special cases where this can be de-randomized, so you can actually remove the randomness. And what I was talking in the previous slide is that this question of efficient algorithm, this PIT is actually almost equivalent to solving determinant versus permanent. So previously I was talking about some lower bound question. This initially seemed to be an extremely different question, but suddenly this algorithm versus lower bound, there is a connection, and they are very strong. And also de-randomizing PIT has many, many algorithmic applications. For example, in graph theory, there are primary testing, and there are coding theory, and many, many different applications of this PIT. Okay. So now I'll talk about one of our first results. So I was talking about linear polynomials, right? Degree 1 polynomial. But instead of degree 1, let's just also allow constant degree polynomials. For example, this is a degree 2 polynomial, because x1 squared, x32 squared, there are the degree 2. So this is a degree 2 polynomial or quadratic polynomial. Let's just use the same in the same model. So you have a determinant and you want to use this, instead of linear polynomials, you want to use quadratic polynomials. So for example, if you look at this determinant, this is a very specific determinant where, let's say, Fij's are constant degree polynomials. You look at the very specific determinant where there is this diagonal and upper diagonal, only this, there is F2S in this. So this way you can actually calculate the product plus product. So F11 dot dot F1S plus F21 dot dot F2S. You can ask the same question that can we actually do PIT for this model? This seems to be a very, very specific question, right? Because initially I was talking about very generic determinants, but now I'm talking about very specific structure of that. The question is, can we do PIT for this? And more generally, can we do, instead of sum of two products, can I do for constant many products? And this was open for a long time. And 3 years back, we actually solved it. We gave a deterministic algorithm in n to the log n time, so quasi-polynomial time. We could not solve it in polynomial time, but we almost did it. So we removed the randomness for this specific model. Okay, so this is the PIT result. I have not talked about approximation yet. The question, as I started with, can we do better using approximation? And what do you mean by that? So let's say initially I was allowing, let's say 2x11 plus 3x22 plus blah, blah, blah. But now introduce a parameter epsilon and think of this as some parameter, which we will talk about later. But now, for now, epsilon is just a parameter. For example, the coefficients are of the form 1 by epsilon or 2 plus epsilon and so on and so forth. So these are linear polynomials in x11 and x21 and so on and so forth. But the coefficients are only in epsilon or 1 by epsilon. Okay. So now I ask the same question that I started with, but now I am allowing a limit. So what I'm saying is, can I write permanent as determinant of a matrix in the limiting sense? What do we mean? That can I write permanent the polynomial as determinant of this S cross S matrix, but these are linear entries, but the coefficients I'm allowing some epsilon and so on. So forth, now I'm taking the limit. So the question is, can approximation do better in? Maybe it does, maybe it does. But the question is, can it? And this is actually the Mulmule-Sohny conjecture that I first talked about the GCT program. This basically says that, look, even with limit also, even if you allow approximation, there is no way you can do better. So forget about without limit, even with limit also you cannot do better. That's the Mulmule-Sohny conjecture, or the geometric p-notable empty question. And as probably you understand that this conjecture is actually much stronger than Valiant's conjecture. Because Valiant saying that write it without limit. Mulmule-Sohny saying that please write it with limit. So if you cannot write without limit, there is no way that you can write it with limit. So this implies the Valiant's conjecture. So GCD, the program that I talked about, this resolves around these questions only. And how does it break the barrier that I talked about? So these two polynomials that I've been talking about, determinant and permanent, they have nice symmetries. I'll not define what are the symmetries and for at least determinant and permanent, but they have some nice symmetries. And most of the polynomials do not have nice symmetry. So a natural proof actually should work for many polynomials, but it says that it cannot be natural because otherwise most of the polynomials must have nice symmetries, which it does not. So that's why this actually breaks the barrier, and so probably this way you can solve this question. So this is the last which I called sorry. So yeah, so I have talked about border or GCT. I have talked about the PIT. Now I'll just quickly go to the debordering, what we mean by that. So Kumar, 3-4 years back, he showed a very interesting result. He said that, look, so if you remember, I was saying that f11 dot f1s plus sum of two products, right? So Kumar showed that any polynomial f can be written as limit of such polynomial. Even forget about constant degree, linear polynomials are enough. So any polynomial f can be written as limit of L11 dot L1s plus L21 dot L2s, where Li's are linear polynomials, but your f has to be large. Okay, so in terms of determinant, let me write it this way. So I have a very specific determinant, and any polynomial f can be written in this limiting in the limiting sense. And I also should mention that without limit, you can never write it as sum of two products. Okay, so limit actually is really important. Okay, so this has connections to matrix multiplication algorithm and so on and so forth. And the question was, can we write f without limit? Like with limit we can write, but without limit can we? And we actually showed that we can actually write. This was another result in my thesis where we showed that, okay, the matrix. So if without limit also we can write it as a small determinant, but with poly is time. How much time to Okay, so I'll just finish. And one can show that the same result holds when the fanning is, instead of 2, I can, if I allow k many, like constant, like 3, 4, and so on. Okay, so let me not go into the lower bound. So I don't have any time, right? Is it? Okay, so let me finish the, this is the last slide. Okay. Yeah, so the conclusion is that, as I started with, can I do PI? So as we showed the quasi-polynomial time PIT for the sum of product of constant degree polynomials. Can we do it in polynomial time? The second question is, can we understand the limit where I allow the Fij's to be constant degree? We could also only solve sum of products where Lij's are degree 1 polynomials, linear polynomials. We don't even understand what happens when the degree is 2. So that's it. That's what I want to say. Yeah, thank you.
Yeah, thank you so much, Pranjal, for that enlightening talk. And I'm sure there must be many questions popping up in your mind, but because of paucity of time, we need to move ahead with the second speaker who is online with us. You can ask your questions from Pranjal offline. So the second speaker is Jokendra Nath Kundu. He would be talking on the doctoral dissertation titled as Self-Supervised Domain Adaptation Framework for Computer Vision Tasks. So I'll just quickly introduce Jogendra. So he's currently working as a research scientist at Reality Labs Research Meta, where he is involved in the development of eye tracking technologies for augmented reality and virtual reality applications. Prior to that, he completed his PhD at IISc Bangalore, where he was advised by Professor Venkatesh Babu in the Vision and AI Lab. His research primarily focused on developing deep learning frameworks that improve the transferability of computer vision models in the absence of manual annotations. So he'll be speaking more about in his talk. Over to you, Yogendra. Yogendra, can you hear
Yeah,
us?
yeah. So thank you for the introduction. So hello everyone. I would like to begin by expressing my gratitude to SM India for recognizing my thesis as the runner-up for the SM India Dissertation Award. Yeah, so the recognition serves as a significant motivation for me to continue advancing my research in this direction. So today I'll provide a brief overview of my PhD work conducted at the Indian Institute of Science, which is titled as Self-Supervised Domain Adaptation Framework for Computer Vision Tasks. I don't probably need to tell how successful deep learning has been for various applications. Here I'll be focusing mostly on computer vision applications because that's the primary research area that I focused on. We know that computer vision deep learning has got a long point where we can detect different objects pretty accurately in various scenarios. So we can detect objects that are real people and also objects of in cartoon scenarios. As long as we have training data, we can train models to do this as per our requirement. There has been a few challenges along the way, and the one that I would like to focus on is dataset bias. So dataset bias occurs when you have a specific dataset. For instance, you are training a computer vision model to detect pedestrians for self-driving car. You have collected some data, labeled the pedestrians using bounding boxes, and trained your deep learning model. It performs exceptionally well on the held out test set, which is derived from the same data set. However, when you deploy the same model on your car in a different environment, the results may not be as expected. For instance, the environment could be snowy with people with heavy coats, and which is a stark contrast from the training data set collected in different geographic locations. So visually, the new data set that the model is expected to level looks significantly different from the training data. This phenomena is also we refer to as dataset bias, and it can lead to issues such as missed detections or generally lower accuracy. Domain shift can occur in a variety of scenarios. I would argue that it's a phenomena that accompanies on every data set you collect. So let's consider a few examples to illustrate this point. One instance I have previously mentioned is that when you gather the data set on one city and aim to test it on a different city, let's say for semantic segmentation. Another scenario could be when you compile a data set from the web and then intend to deploy your model on a robot that captures images from its environment. In this case, factors such as angle, background, and lighting can significantly differ the leading domain adaptation. A particular common issue arises when we train models in a simulated environment and then aim to transfer them to real world scenarios. This is also referred to as sim to real domain shift and is prevalent challenge in the field of robotics. Okay, so can't we collect more annotations to solve this problem? Often it is not practical to cover the visual diversity. For instance, to train a generic road scene segmentation model, one has to gather samples from different geographic regions, and city architectures varies quite a lot. So given the dynamic nature of the world and the immense visual diversity, constantly collecting new data and re-annotating it is not scalable. So therefore, we need to explore other strategies that can handle the datasets in a more efficient manner. So now I'll dive deep into the identifying challenges that are specific to the vision tasks. So broader vision tasks can be categorized into non-dense prediction tasks and dense prediction tasks. General ML classification and regression fall under non-dense prediction tasks. So non-dense prediction tasks can be of two types, image like, for example, depth estimation and semantic segmentation, or non-image like such as 3D human pose estimation. Here the 3D human pose estimation, though is a regression task, there is an underlying kinematic 3D structure, thus it is categorized as structure prediction task. So a crucial question that arises is in this context is why does task type matter? The answer lies in the need to reduce the risk of failure post-deployment. To achieve this, we need to impose additional constraints on the output space to reflect the natural prior distribution. Let us consider the example of pixel-level semantic segmentation. In this task, the model is required to assign a class level to each pixel in the image. However, without proper constraints, the model's predictions may end up violating our common sense prior knowledge. For instance, the model might predict car flying in the sky or grass on the road. These predictions, while technically plausible within the model's output space, are unrealistic in real world. Similarly, in case of 3D human pose estimation, the model is tasked with predicting the 3D coordinates of the key points in the human body. Here, the solution space must be constrained to ensure that the model's predictions adhere to the structural plausibility limits. For example, the model should not predict human pose where the arm and legs is bent in an impossible direction. So general domain adaptation approaches, which are primarily designed for image classification tasks, do not extend well for these dense prediction-based problems. This is because image classification involves predicting single class level for entire image, which is much simpler output space compared to the pixel level or 3D structural level predictions required in case of dense prediction tasks. In our work, we address this challenge by using generative models like adversarial autoencoders to impose prior enforcing constraints. So I'll dive deep into three of such selected works. In the first part, I'll discuss about one of our work, which is titled UM-Adapt. It's basically focused on domain adaptation for dense prediction tasks like semantic segmentation and depth estimation in a multitask setting. So here I explain the problem setting for multitask adaptation. So we have access to a source domain data containing images with the corresponding task output, which is typically extracted from a synthetic graphical environment. Whereas the target domain constitutes unpaired images sampled from natural deployed environment. The objective is to improve the performance in the target domain by adapting the knowledge from the source trained model. In this setup, we consider three related tasks such as depth estimation, semantic segmentation, and surface normal estimation. We formalize a novel idea to leverage cross-task coherency. So we introduce task transfer networks, where individual networks are trained to output representation of a particular task from a combined representation of rest of the tasks as input. For instance, the network on the top, depicted as nseg, takes output representation depth and normal to predict the other output representation, that is segmentation. This innovative approach allows us to leverage prior enforcing common sense knowledge, acting as a bridge between different tasks. Note that in this framework, we obtain two predictions for each individual tasks. Predictions that are output of task decoders regarded as direct predictions, whereas the predictions at the output of task transfer networks are regarded as indirect predictions. To update the base model parameter, we employ two loss terms for each task, one at the direct prediction and the other at the indirect prediction. Such a setup does not allow a single task to dominate the training process, since the least performing task would exhibit high discrepancy and hence will be given more importance in further iterations. For adaptation, we make use of cross-task distillation. So let's look one such loss terms. Here, the energy term is computed as the discrepancy between the direct prediction and the indirect prediction of the same output. In an adversarial paradigm, NSEG is trained to maximize the energy for the target while minimizing it for the source. And conversely, parameters of the target-specific encoder are updated to minimize this energy for the target samples. This adversarial training strategy ensures that as training progresses, the model fails to distinguish whether the input is coming from a source domain or target domain distribution. So the key takeaways of this work include the use of synthetic data to learn cross-task coherency based prior enforcing mechanism, an innovative way to use cross-task distillation as an adaptation strategy, and the ability to generalize or adapt to multiple tasks at once. This work represents a significant step forward in the field of multitask adaptation, demonstrating the power of leveraging cross-task coherency and distillation for domain adaptation. So moving on towards better deployment, we developed learning techniques for privacy-oriented source-free domain adaptation. So conventional domain adaptation techniques assume simultaneous access to both source and target domain. So generally, the adaptation algorithms are designed to read samples from both source and target in concurrent fashion in order to minimize the feature-level domain discrepancy. However, in many practical scenarios, the source or the vendor and the target or the client may not able to share their data with each other. This is often due to privacy concerns or regulations that protect sensitive information. So despite these restrictions, the vendor can still share a model that has been trained on the source data with the client. Now the client is faced with a new challenge. They need to perform source-free target adaptation. This means they must utilize the source trained model without having access to the original source data to develop a model that is specifically tailored for the target data scenarios. So to address this practical domain adaptation scenario, we introduce a two-step approach called generalize then adapt. This approach involves specialized strategies for both vendor and client with the ultimate goal of improving the final adaptation. In the first step, the vendor aims to generalize. This involves training a source model that is not just effective for the specific source data, but also generic enough to be applicable to a wide range of unknown future clients. In the second step, the client aims to adapt once the client receives the generalized model from the vendor, and they aim to perform the target adaptation. The goal here is to leverage the shared source model to develop an effective target-specific model. So by combining these two steps, the generalize then adapt approach provides a practical solution for domain adaptation, particularly for the source-free setting. Now we'll describe the vendor-side approach. Based on our analytic insights, we propose source-only multi-augmentation network named as SOMAN. SOMAN is a multi-head framework. The global head is trained according to ERM, that is using data from all the domains. And the kth live-on-out head is trained using data from all the domains except the kth domain. In the paper, we explain the reasoning behind such a framework, and I'll skip the details. We propose a method to select the most suitable head for the target dataset. This is done by choosing the head denoted by K prime that exhibits the lowest average self-entropy from the target data. This approach ensures that the model we use for the target dataset, one that is most certain about the predictions, thereby increasing the likelihood of accurate results. Okay, so note that we do not have access to target labels in this setting. Once we have identified the optimal head K prime, we combine it with CPI, that's a conditional prior enforcing autoencoder, to extract reliable pseudolabels for the target dataset. This is achieved through a process known as confidence thresholding. So here CPI is equipped to infuse the common sense knowledge of how an output segmentation map generally looks like. That is, ensuring that car pixels are on the road and not flying in the sky, thereby reducing the failure modes and facilitating a constrained optimization framework. Next, we use the extracted pseudolabels to perform self-training to obtain the inference stage model Note that only a few selected weights are updated during the target adaptation process. So here I illustrate qualitative results of our work. The proposed vendor side and the client side modifications enable source feed on adaptation with superior deployment performance against the state of the arts. So moving on, we applied some of these concepts for more complex 3D vision tasks, such as 3D human pose estimation. Existing networks often exhibit unpredictable behavior when they encounter unfamiliar out-of-distribution data with no mechanism in place to disregard such samples. This can lead to inaccurate predictions and reduce model performance. To address this issue, we propose the implementation of self-adaptive pose estimation model equipped with the capability to estimate uncertainty. The model would not only make pose predictions, but also provide a measure of confidence or uncertainty associated with each prediction. So the pose predictions are generated by such systems should be accompanied with the uncertainty measure acting as a barometer of confidence, as illustrated on the right. It is important to note that for the second image, the uncertainty is at its peak for non-human samples, and it is at its minimum for samples where the full body is visible. This indicates that the model is more confident in its predictions for familiar in distribution, that is full body human samples, and less confident for unfamiliar out of distribution data, that is non-human samples. This uncertainty estimation capability can greatly enhance the reliability and interpretability of models' predictions. So in literature, the pose estimation architectures employ one of the following two design configurations. Localization-based representations employ fully convolutional architectures where the final pose is realized via heatmap-based spatial PDF. Such model-free designs do not allow to inculcate structural articulations or bone length priors. So structural articulation refers to a way different parts of the body move in relation to each other, while the bone length priors refer to the fixed proportion between different parts of the body. These are important constraints for the output space prior knowledge that can help to improve the accuracy and realism of pose estimation. On the other hand, regression-based representations employ fully connected layers to directly regress some form of 3D human pose. One can easily inculcate joint connectivity and bone length prior via model-based design with integrated forward kinematics. However, there is no provision to obtain joint level uncertainty as it sees the pose as a whole. So following this, the pose uncertainty can be quantified as a disagreement in pose predictions obtained through the two output heads subscribing towards two diverse design configurations. The pose uncertainty denoted as U of I measures the L1 distance between the pose predictions from the two heads represented as Q hat and Q tilde. This is visually represented in the figure. So in essence, this approach treats the difference in predictions from the two heads as a measure of uncertainty. If the two heads agree closely on the pose prediction, the uncertainty is low. Conversely, if the two heads produce significantly different pose predictions, the uncertainty is high. This provides a simple yet effective way to quantify uncertainty in pose estimation. Now, how do we train such model? The adaptation process accesses three different data sets. First, a labeled source dataset DS. Second, a dataset of background images DB to approximate an extreme out of distribution scenario. And third, unlabeled target domain samples DT. Following this, the adaptation process can be visualized through the pose uncertainty histograms. In the pre-adaptation stage, our goal is to enforce the desired behavior by maximizing the uncertainty U for background images that are representing out of distribution data, while minimizing it for the source data representing in distribution data. So this ensures that the model is confident about its predictions for the source data and acknowledges its uncertainty for the out of distribution background images. Upon encountering the unlabeled target, the adaptation process seeks to reduce the target uncertainty alongside a progressive self-training and a set of reliable pseudo levels. So note that the histogram of target uncertainties slide towards the source, implying the model now treats the target as in-domain samples. So following this, we develop a similar framework to quantify uncertainty at joint level. And this advancement provides a solid foundation to extend our adaptation process to work effectively on in-the-wild target domains. So this is particularly useful in scenarios where there may be external occlusions or truncated frame scenarios as shown in the video. So on the right, we present an illustration of a result where the size of the bubble indicates the level of uncertainty at each joint, similar to the parameter concept discussed earlier. So larger bubble size represents joints with higher uncertainty, while smaller bubble indicates joints where the model is more confident in its prediction. This visual representation provides an intuitive understanding of the model's confidence level at each joint. So in conclusion, I would like to summarize the key strategies I have explored in my thesis to tackle the domain set problem. So firstly, I have leveraged synthetic supervision. Synthetic supervision offers a wealth of labeled source data and output space. It provides its beneficials for developing generative prior enforcing mechanisms. However, it is important to note that synthetic supervision is not immune to domain shift. Secondly, I have explored the use of unlabeled visual data. In this context, we have investigated methods to utilize unlabeled data from the target environment through self-supervised learning strategies. This approach allows us to learn useful representations from the target data, even in the absence of labels. Lastly, I have enabled unsupervised domain adaptation. Under this strategy, we have delved into innovative learning techniques that can minimize the discrepancy between the labeled source and the unlabeled target. These techniques are specifically tailored to the computer vision tasks, as I discussed. So these strategies represent the core of my thesis and provide a comprehensive approach to tackle the domain set problem for a wide range of computer vision tasks. So here are all the publications that are part of the thesis but are not discussed in this talk. So please feel free to go over these if you have interest, learn more about this topic. The papers offer a more comprehensive understanding of the subject matter and could potentially spark new ideas or interesting research questions. With this, I would like to express my gratitude to everyone who has played a role, whether directly or indirectly, in my PhD journey. A special mention goes to my advisor, Professor Venkatesh Babu, for his invaluable guidance. As I look ahead, I'm excited about embarking on a stimulating research career at Reality Lab Research Meta. Thank you all.
Thank you, Jogendra, for that great talk. And definitely it finds a myriad of applications, whether it is autonomous navigation, CV in sports, etc. So ACM India Council is also felicitating you guys uh, with a token of appreciation. May I call Pranjal on stage, please? So with 14 trees foundation, they have planted trees on your names, and you can actually track the growth of these trees. So, Jogendra, you have to accept your token of appreciation.
Yeah.
Line mode only. Okay.
Yeah. Thank you so
Thank you so
much.
much. Thank you so much for, and we'll just end the session. And I hope these inspiring talks would be motivating all the new PhD students, and they'll be always contesting for such kind of award ceremony. Thank you.
Okay, so hi everyone. Up next, we have a very exciting session. It's called ECR series, and ECR stands for Early Career Researchers. So here we invite young and very accomplished researchers who are early in their life and from various walks. to share their research as well as life experiences with you. So today we have four of them, two from academia, one from industry, and the last one from startup space, just so you have varieties of experiences. It covers all aspects. And yeah, I hope you get yourself enlightened with these talks. And with these four talks, this will also mark the logical sort of conclusion of our 2-day long technical program. And after that, we still have some more things, but we'll announce them later. So let's start with Manas. You're going to introduce.
Thank you. Okay, let me introduce the first speaker, Dr. Manas Thakur. He is a faculty member in the Department of Computer Science and Engineering at IIT Bombay. His research interests include program analysis, compiler optimization, programming languages, and software engineering. He holds PhD and master's degree in computer science and engineering from IIT Madras, and his thesis title, Precise and Efficient Analysis of Java Programs, won an Institute Research Award and the IBM-based Thesis Award in 2019 and 20. And prior to joining IIT Bombay, he was at IIT Mandi for 3 years, wherein he received the Teaching Honor Roll Award in 2021. Dr. Thakur's research group at IIT Bombay is named COMPEL. So we welcome the first speaker, and over to you.
Good afternoon. Pita and Karthik have given me the challenge of waking you up after lunch, and I have taken it very happily. So I hope you will help me out. All right. Let's. So the first. This is probably the first talk about. We have listened a lot of talks about different applications. This is probably a talk about core computer science per se. And computer science started when people started writing programs. I mean, at least computers came into existence and people started using them to write applications once we started with programs. And hence, let's have the question of the symposium. I hope all of you write programs. Which programs are the fastest? If I were to ask you just this general question, what would you say? How many of you say C? How many of you say C++? You have to raise your hand. Java? Anybody says Python? Yeah, you should go back and learn about interpreters and compilers if you say Python. But see, nobody really says Java. C programs are the fastest, is it? Let us have a demo to prove you wrong. Okay. So let's say I have this language for very faithfully reproduced a program in 4 different programming languages. I have a C program. Basically, I'm taking some user input. Don't forget the computation. I have 3 nested for loops. Each loop is executed the number of times I have taken the command line argument as. So you have 3-level nested for loops like matrix multiplication, some random computation. The same code is reproduced in C++. Here we have objects. I have Java code for the same computation. I don't write Python programs, so I asked a student of mine to write an equivalent Python program for the same as well. And then I have a script. I'll just run the 4 programs with some number of iterations applied. If I supply 10, each loop will run 10 times. So the computation would, inside computation would be 10 times, 10 times, 10 times. Okay. Let's just run this a couple of times and see. Just a sanity check. If I run it with the input value 100, it's running. I'll get some answers that will print how much time did each version took. Python program 0.9 seconds, C 0.6. Java was the fastest, but fine. Maybe it's a one-off case. It's just an input size of 100. Let me change it. And since all of you agreed Python programs are probably the slowest among this set of 4 languages, let me just comment out to save time. Okay, let us now make it a bit larger. Let's make it 500. You know, my laptop is not very powerful. Even if you run it on a
without the Zoom call going on, it will still take nearly half of the times that you see on the screen. So, well, there seems to be some magic going on. Final one. After that, we'll continue with the talk. So, let's see. The C program still runs. Can I walk back till the time C program finishes? Yes, 5 seconds. C++, something similar. And then you would see what happens for Java 1.7. What is going on here? Java programs seem to be the fastest. Who told C programs are fast? They're even slower than C++ sometimes. All right, this is just about this program, just to make a point over here, which we'll come to later. But keep this point in mind. So what happens? Why are Java programs fast? If you still had memories from some of your older textbooks or something that, okay, Java programs are interpreted, they are very slow, that changed from last 15, that has changed in the last 15 to 20 years. When you compile Java code and generate class files, these platform independent class files that you can run on any machine, you have not only an interpreter sitting inside the Java virtual machine, but also few compilers. Okay, that's my research area. So you have something called as just-in-time compilation going on when you execute a Java program inside a VM. If you have code that executes frequently, I have a loop that I am iterating over a large number of times. Why to interpret it line by line? I should compile it, optimize the code, and run that. That's how it goes. Okay? So this is just-in-time compilation for you. This compiler 1 and compiler 2 that you see in the diagram, this figure represents Oracle's OpenJDK virtual machine that probably most of us use. And those two compilers sitting inside the VM are called just-in-time compilers. So what happens when you run Java programs? Well, it's not only about Java. A lot of object-oriented programming languages per se follow this model. When you run a Java program from the main method, right, from the first statement, you actually start interpreting the bytecode. You start interpreting the bytecode, and then you jump over. You find out this piece of code is getting executed frequently. You jump over to a compiler. When there are multiple levels of compilation here, 1, 2, 3, 4, where each subsequent level is more powerful in terms of the optimizations done over the program than the previous level. And your program is essentially traveling across, or different parts of your program are traveling across these different phases as your program executes inside the VM. Okay. There are some grayed out parts over here, and this is a chota demo. Okay. If you print some extra information about the program, you can see some numbers on in the third column. 3, 3, 3, sometimes 4, 3, 4, 3. It actually tells what part of the method foo is being executed from what level of compiled code. Okay, so as I told you, there are multiple levels of compilation, and those are visible. You can see them. You can understand what part of your program is at what level of compilation while executing your code. Okay. Now, in the hotspot VM, the VM that as I said, the Java virtual machine that most of us use, you basically, as I said, start off by interpretation of bytecodes. Then while you execute your program, you also keep recording. Okay, if I see a method call, let me increment the counter. Method foo is called one time. If I call foo somewhere else later, let me increment that counter and make it 2. I see a loop. Every time I iterate over the loop, let me increment the counter. Okay, the loop got executed by one more time. And as you keep incrementing these counts, if you reach a certain threshold, you decide, okay, this piece of code is hot. Hot means frequently executed. You insert it into the compilation queue. There are 2 threads waiting there, one thread for each compiler, that are waiting for code to be fed. Give me code that I can compile. As soon as you insert something into the queue, in parallel, your program has not paused the execution. Your program is still executed by the interpreter. In parallel, that thread creates a new compiled version of your code for the machine on which you are executing the program and gives you a performant binary. Now you will switch over to that performant binary. Okay? This is a very dynamic system, and this is how Java programs are executed. Entry points of methods are changed dynamically. Whenever you call foo, you were going here. Now you have the compiled code available loaded in the memory at a certain address. You will change the entry point such that next time the method is called, you jump to that address instead of interpreting bytecode over here. Okay. Similarly, you may replace loops that are hot on the stack with compiled code. Okay. Then you also see some more stuff there. The highlight, the gray one is with full profiling. Well, fine. I can compile and count how many times a method is executed, how many times a loop is iterated. Can I count more interesting things? If I can profile a program, I can profile even more interesting stuff, isn't it? So now, sorry. So now there is something called as speculative optimizations that are performed inside Java virtual machines, which is completely absent, not possible in C compiler, for example. Basically, you speculate, you make a guess based on the live runtime profile of a program. For example, I can guess if every time I choose a condition, I can count, okay, 10,000 times, the previous 10,000 times, always the if branch was taken, the then branch was taken, rather the condition was true. So I can just assume that always the if branch is going to, the then branch is going to be taken, and I can remove the else branch. I can optimize code further from that point. Okay, so there are optimizations like this that are done by VMs. Let's take one more example. All of us like seeing code. Yes. So let's say I have this piece of code. There is a method foo which does some computation. It takes two parameters A and O. There is a method bar which is called inside foo, and there are three implementations of bar. This is an object-oriented program. So which bar is called depends on the type of the object pointed to by O. Okay. Now I can, if let us say somebody tells me most of the times this method is called variable A's value is 10. If I make that assumption, I can propagate the constant 10. B would become 10 plus 10 is 20. I can just say in C equals 20 times O dot bar. Now if somebody tells me about the second argument, that okay, most of the times O's type is Y. What can I do? I can inline the method bar of class Y and replace the call to that method by the return value 2. Finally, I can perform one more round of constant propagation, and my whole method, which had some addition, some multiplication, some method calls, some assignment, some variables, everything just got replaced with return 40. I got optimized code, right? This code will run probably faster. It will take fewer resources than the previous original method 2. Right? And this is the binary the JIT compiler will generate, which gives you performance. Now, of course, you might say, if I generated a binary under certain assumptions, what if the next time I call foo, I pass in 20 instead of 10 as the first argument? Can you execute the binary that you generated with the previous assumption anymore? No. So you have to invalidate the code that you compiled under a certain assumption. So we compile and create a specialized binary under certain assumptions. What if the assumptions fail in a subsequent run? We should have some mechanism to fall back, to repair the program while you are executing the program live, right? So when a profile guided assumption fails, you invalidate the compiled method and you have to fall back to some safe path. Well, can you give me an example of a safe path? You had an interpreter and compilers. If compiled code is wrong, is there an option? The interpreter, some of you are moving your lips at least, I can read it. So you can fall back to the interpreter. The interpreter still has the complete bytecode of the method too. If the assumption was wrong, you can fall back to either a lower level of compiler or interpreter and resume execution. Okay? So this is how programs execute in a JVM. You have these several speculative optimizations. You have this interesting engineering that may move your method from one state to another. In use, not entrant, zombie. These are technical words. Compilers people are the most funny people in the world in computer science. Believe me. They use interesting words inside the code they write. So a method can be zombie. If it is zombie, it means that, okay, that method has not, the compiled version has not been called for a long time. I can throw it away when I do garbage collection later. I can reduce the amount of memory consumption inside my VM. So now let me ask, well, if some of you were thinking, will we talk non-technical or technical stuff, we'll move quickly. But before we move to some advices for PhD students and so on, question of the symposium. Again, the question is, which programs are the fastest? How many of you say C? How many of you say Java? Wrong. Everybody is wrong. It's the compiler that makes programs fast. I can write a better C compiler and make those programs fast. I can write a good Python compiler and improve the performance of Python. Remember that at least from my talk. Okay. So this is my research area. All of us write programs. All of us read programs. All of us debug programs, and compilers process programs. They take programs as input they produce something that's performant, they optimize the code, they can take advantage of the runtime in case of virtual machine like systems, and they can actually improve on various parameters, not only the performance in terms of speed, but also the memory consumed by your program, the power dissipated by the program. They can actually help you get the green Earth goal. People are working on it. It's an active research. Okay. So when I started, I am from a small town of Madhya Pradesh. I did a direct PhD at IIT Madras, and when I chose compilers as an area, everybody used to say, "Oh, dead area. What will you do? No publications possible." There is a small research area in compilers called pointer analysis. People worked on pointer analysis from 1970s to 2000. In 2001, there was a paper that said, do we still have anything left to do in pointer analysis? That author claimed yes. I wrote a similar paper in 2020, and I asked the same question, and the answer is still yes. In every conference related to programming languages, there are 4 or 5 pointer analysis papers every year. So the idea is even one small branch of compilers is not dead. It's a very active research area. If you write Lightning programs, do not be afraid of working with programs. Okay, so after finishing my PhD, we did some work with Java, R, and so on. I moved to IIT Mandi, where I taught new courses. IIT Mandi is an IIT in the Himalayas. You can see my office was in the top left corner over there. And I offered some new courses over there. I became a popular teacher in some sense. I got some awards there and so on. And then finally, right now, I am back to the central part of the country. I'm at IIT Bombay, where again, this time I am offering a new course on code optimization for all languages. PhD students who are doing very soon. As you can see, there are few takeaways from this journey, from this short journey that I told you in the previous slide. One is, do not be afraid of taking your decisions. If you like doing something, what I have learned in the last 10 years from the time I started my PhD, do not be afraid of choosing your own path. If you do not know, let's say it's for a PhD and you do not know what should you do, you do not know which area you're interested in, you can try an FSY research program. You can try stuff. It's not like you have to just decide on the day you graduate. Okay. Secondly, there is no shortcut to hard work. My first paper, in my area, if you get 3 good papers, your PhD is done. In your whole lifetime, you get maybe 40, 50 papers. That's much less. I mean, each paper's value is more than papers in some other areas. But my first paper I submitted at the end of 3 years of my PhD, and it got accepted at the end of 5.5 years of my PhD. It took 2.5 years to get my first paper accepted. Well, of course, I was doing some other work as well in parallel. It wasn't like I could not graduate on time. I finished in 6 years. So what I had to remember was, well, no, my guide was very particular. No, you should not submit to conferences that are low grade. You have to target A star. I kept on surviving and so on. And what I learned at the end is there's no shortcut to hard work. I got into IITs as a faculty member, so that patience was worth, right? So that's another thing that you should remember from my life story, my short life story till now. If luck works, well and good. I had a colleague whose paper got rejected in a conference. He submitted the same paper in a journal, he got best paper award. Oh, sorry, vice versa. In a journal, it got rejected. In the conference, it got the best paper award. Sometimes luck may just work. If it doesn't, also you have learned something on the way. You know at least what may happen. You can tell it to your future students, right? Enjoy the process. Secondly, ends are just an event. Don't look for the day of graduation from the day you start. It's not a 5-year, 6-year journey. If you start a PhD, it's a lifelong. It's just the first step of a lifelong research career, as we say, right? So do not look at the end. There is no end. Once you start doing research, it goes on till the end of your life. And finally, if things are not working out, remember, humans are extremely capable. Life has no limits. Play with these binary computers, but don't forget that life is puzzle. That's something I like to say. Okay, and finally, if you want to remember from the technical content of my talk, compilers and programming languages are a very active, vibrant, and interesting research area for nerds, for theorists, for the practitioner in you, for the engineer, for the scientist, everybody. You would like it. If you like working with programs, please consider joining my research group or any other group that works on compilers and programs. Thank you.
It was really amazing talk. Okay, so I'm sure that we'll be remembering both the technical and the philosophical as mentioned. Due to time constraint, we'll be taking questions offline. So, starting Okay, let me introduce the next speaker, Dr. Diksha Bhartiya. She is an entrepreneur and founder of Genomics Solutions, a young startup that aims to provide bioinformatics data analysis services. Dr. Bhartiya completed her PhD from the Institute of Genomics and Integrative Biology, Delhi, and she has the research experience over a decade in genome informatics and has expertise in analyzing and interpreting next generation sequencing datasets. So welcome, let us welcome the speaker and before this thing gets better, I think I can start my talk because this talk is meant for early career research people and to motivate young PhD students about through our journey. And thank you for the introduction, and thank you Karthik and Arpita for inviting me. I am thinking myself as an outlier in this conference because I am nowhere from the computing space, though I come from biocomputing area. So basically, I will be talking about the applications, mostly the applications of all the algorithms, the theories that you are building in the biologic field, and especially how you can use that all this information for patient care. I have done my master's and PhD in the field called bioinformatics, where we used to analyze, we actually analyze a large high throughput biological data sets, especially genomic data sets. So when I was talking about this genomics during lunch, a student asked me, okay, what is exactly a genome? So I realized that I have to start from there. That okay, if I have to talk to an audience where people don't know anything about genome or genes, then I think I should start from there. So on top of it, we are working on the mutations in the genomes. So since yesterday, I'm very sick here, and I was having this joke everywhere around that because I come from Delhi, I think my genome is mutated, and I can no longer bear clean air. And since I landed here, I'm having fever and cold. So sorry for my hoarse voice. But when I say mutations, then you should also understand that all of us, so the genome that we have in the cells, there are 3 billion base pairs in our genome. So human beings are made of, sorry, thank you for that. So, what? So our genome consists of 3 billion base pairs. And if change in one single base pair of those 3 billion letters of the DNA that we have can cause a very severe disease such as cancer. And if we can accurately identify that mutation or the change in those 3 billion letters, we can not just help in diagnosing that disease, but also provide way for future treatment. And this entire process is called genome testing, wherein we use that information that what particular letter in the DNA has changed in a patient, and how can we use that particular information to do that analysis. And since I've started to giving you the perspective, let me introduce my startup called Genomiki. Genomiki is actually the Hindi word for genomics, and we started in late 2021, right during my postdoc. So I did my PhD at IGIB, there's an institute in Delhi, CSR Institute. After my PhD, I thought that, okay, I'm nowhere less than publishing high quality articles, and I'll definitely get a Nobel Prize. And I landed up in a government job in ICMR, and I realized that, okay, I need to do something else. This is not where I belong. And after spending around 3.5 years as a bioinformatics scientist in an ICMR institute, working extensively though on cancer genomics, I wanted to get far more exposure, and I went for postdoc at Karolinska Institute, Stockholm, and where I realized the power of data, especially genomics data coming in, not just in research, because we were coming from research community, we realized that a lot of data is coming in research. Genomics was coming in healthcare. There were these genomic tests available for various disorders, not just to identify or diagnose certain diseases, but also in preventive screening. For example, if we know that if we have a particular mutation which can be responsible for a disease at a later stage of time, that can be screened, that can also be screened, can be used as screening test. We can use it for diagnostics. We can also use them for therapeutics, because if we know that there's a mutation in the gene which is making so there's a very simple theory, maybe you have learned it in your school, that gene get transcribed into RNA, DNA gets transcribed into RNA gets translated into protein. So if there's a problem in the gene, the protein gets a problem. Either the protein is not formed properly, different amino acid is formed, or there's some certain problem. If we can replace that particular protein using various therapies, or if we can provide a gene therapy, that the mutation, the disease can be cured to some certain extent. So basically, all that can be part of gene therapies. So with Genomics, we aimed at building such solutions, which were genome informatics solutions, to design and develop, identify these mutations, and to look for various therapeutic approaches. So my talk today is about empowering medical decisions using various smart genome informatics solutions, so that we can start moving towards precision medicine. And to do that, we are making cloud-based for analyzing and reporting genome testing data. So very simply, let me take you through the life cycle of a genomic test. When a doctor prescribes a genomic test to a patient, when a patient goes with a certain symptom, the patient sample is taken either in the form of blood or in the form of tissue for specific cancers, and a lab experiments gets done. And to excite you more, a lot of data, GBs of complicated data, gets generated as a part of those sequencing experiments, which required efficient algorithms, efficient training to predict or identify those mutations, and trained bioinformaticians, genetic counselors. And I think this crowd definitely understands that there is a lack of many such skilled people, especially in our country and actually across the world as well, to identify the mutations and report the findings. Now, this is actually, I summed up everything in here. And if we actually look at the diagnostic reports, so somebody was asking, why did you take this startup journey? So when I was doing my postdoc in Stockholm, some of my friends had sent me certain data sets, the patient data, and to look into that data, because the reports that were provided to them were not matching or were not effective enough. When I reanalyzed the data, I realized that analysis was not done properly. So basically, the report that was given to the patients were wrong. So wrong reporting was being done in patients, which has not just has many other psychological or traumatic experiences for the patient, but also it's not good in the terms of medical community. And this leads to wrong decisions in terms of precision medicine as well. And the accuracy of report is not good because they are using manual approaches. Yeah, because in the next slide, I'll show that what exactly data comes up, how we can analyze the data, exactly we do at the end. So it's a and when we do this, go through this pipeline, we have to take care of accuracy or quality checks at each and every step. So, and when things are done manually, definitely there are certain problems that leads to certain errors. So that's why the reporting was very much prone to errors, and because it was done manually, the turnaround times still are very high in many labs. It ranges to weeks, where we are able to do it in a few hours at this point of time. So to solve these issues, and also by 2025, over 100 million genomes will get sequenced, and 20 million GBs of just the raw data will get generated, which is in itself is a huge problem, because how are we going to analyze, interpret, make sense of this data, and also to manage and report the entire amount of data? So with all these problems, we realized that we need to come up with smart solutions, and we started making these cloud-enabled solutions. So let me take you through what happens when a when a sequencing is done. So the first is called NGS. NGS stands for next generation sequencing. It's just a simple process wherein an experiment is done to get the high throughput data from either your blood or your tissue. And when you do that, there are 3 levels of analysis, which includes a primary analysis, a secondary analysis, and a tertiary analysis. So, and after the tertiary analysis, what you get is a list of mutations that a person may have, and every other individual, we all are evolving. So we may have thousands of mutations in us, but what is that particular single mutation that will be responsible for that particular disease? To identify that, we have to do a lot of annotations and filtering and prioritization, use those steps. And finally, at the end, what we get are the actionable insights that which particular mutation is responsible for this particular disorder. So I'm giving you actually the, as I said in the very beginning, that I'm giving you the idea of the applications wherein you can deploy your own algorithms to and take through all these, steps and identify, make classifiers to actually predict which particular variant can be very important, and how we can look for actionable insights in these from using this particular information. So using all this information, we were looking for variants in the, as I said, 3 billion base pairs. But actually what happens is, if I look at the size of genome, it's 3 billion base pairs, which is exactly like the size of this apple that is shown in the picture. And when we look at the protein coding genes, or the genes which are responsible to or which might affect at least 85 to 90% of disorders, are just 20 to 25,000 genes, which are actually the size of this particular slice that is over there. So only, or in other terms, we have the information, or we have, right, till date, we have the knowledge to analyze or interpret or identify variants in that 1% part of human genome. We still are not very much sure that what happens in the rest 98, 99% of the human genome, which was, when I was in my master's or PhD, was called as the junk DNA. Now we know it's not the junk DNA, it's called, there are other names like non-coding part of the DNA or non-coding genome, but we still don't know how to make sense of that part. So still today, all of us, like all the genomic labs, are trying to make sense of that 1% part of the genome. And when we talk about cancer, and also because when we are, sequencing the entire apple, it costs, thousands of dollars, and if we try to sequence or, do the testing of the smaller part, it is a bit cost effective. And since we are giving these tests to patients, we also have to take care of the costings as well. So, and when we talk about cancer, we even don't look at that one. We look only for around maximum till 100 or 200 genes, which is like another 1% of that 1%. So that is the only information right now that we have out of the entire genomics after being studied in last 2 decades. But still, what we have achieved is, genomics as a community, that how these genes can affect, how the variations or mutations in these genes can affect or cause a particular disorder, and can we use this information to provide treatment modalities. Now, yeah. So when we get the data from a next generation sequencing or sequencing experiment for that matter, what we essentially get is these, what we ought to have mentioned in the A segment, small segments, segments of stretches of reads, which is, stretches of bases, which is like ATGC bases of small stretches. These stretches range from 100 nucleotides, 100 nucleotides or 100 letters, 200 letters, or even more. Some of them are in MBs, but yeah, these are small stretches. And as shown in B, these stretches are supposed to be mapped to the reference genome. Now, Human Genome Project, which was completed in 2003, actually gave us a standard reference genome, which can be used as a reference set for all the humans of the world. Of course, there are certain drawbacks to that, because at that point of time, Indian genome was not there, and we could not add Indian information over there. Of course, so if we keep aside all the drawbacks, we still have a reference standard set of human reference genome, which is used to map the small stretches of sequence or the nucleotides that we get after the sequencing to the reference genome, so that we can finally, so that what we finally get, as in mentioned in the C. Yeah. So what we actually get is, once we map all these reads to the reference genome, all these reads as in the stretches of nucleotides on the reference genome, what we actually get is the information of where there is a difference in the nucleotides in the patient or the sample genome that we have as compared to the reference. And when we see, it's a very simple algorithm. So when we see, when there is a difference in the ATGC of the reference and in the patient as compared to the reference, we know that there is a mutation. And we right away don't call it a mutation, because then we have to score it according on the basis of the number of reads that are actually there. So we have to, there are certain scoring methods. I don't have to explain it to this audience. You know much better than me how to do this scoring make these scoring algorithms. But there are scoring algorithms which define that, okay, for the particular mutation that we are seeing is actually there, it's a noise or there's an error over there. And then we compare it. If there is a patient sample, we also have a normal sample, so normal patient. So we compare it with the normal patient, and we identify that those mutations might already be there in the normal. So the that mutation might be common in the population, but might not be having any particular disease-causing effect. But there might be certain mutations which will be specifically there in the tumor sample or the patient sample, which we then finally screen out from that data, and then we identify, okay, we prioritize that these are the variants which are different or specifically present in the patient info data, and are these variants, any of these variants, responsible for a particular disorder. So there can be different types of disorders. There can be monogenic, where the disorder might be dependent on one particular gene, polygenic for many genes, and so on and so forth. So basically, what we at the end of all this exercise get is the information of those variants which might be there in the patient sample and which might be responsible or causal factors for a particular disorder. And once we get those variants, we call this step as called variant calling, we actually filter to prioritize and identify a causal variance based on the available literature, available information, and many other prediction algorithms as well, so that we can identify this is a deleterious or this is a problem causing or disease causing variant. Now, all this information, where actually we use this information is used to identify or design precision medicine for a particular patient. So that we can tailor the medications on the basis of the genetic profile of an individual. So on the basis of genetic profile, we know that this is a patient with this particular disorder. We know that are these disorders inherited as in is the disorder or these variants, if these variants have been passed the family, I mean through the parents. There are parental screening also done, carrier screening is also done. We are also working on patients wherein we are identifying such inherited variants in the parents who in the couples who are planning their children. So we do this is called carrier screening for those individuals who might be either having consanguineous marriages and who might have history of miscarriages, where carrier screening is done on the basis of all this information to identify those mutations. Because what happens is, for us for any mutation to express or to show any effect on any individual, there should be 2 copies of those allele. This is called, we all have biallele. 2 copies of each allele should be there, and 1 copy will come from mother and the other copy will come from father. So if those 2 copies are there, then the mutation is going to cause any effect. So we also do this screening. This is called carrier screening for individuals who are planning for the next, child, and use all this information that whether there is an inherited disorder, how we can use this information in precision oncology, how we can identify patients with certain disorder, cancer patient with disorders, and use all this information to provide them tailored medications. And I think I've covered all these things. So and all this so that we can enhance the efficacy of the treatment. And I am reiterating most of these things. So yeah, and now what this was mostly about the field, and now what we are also doing is we do have a lot of information. We have worked with a lot of pediatric doctors. Our core field area of research is maternal and child care, wherein we are working on pediatric samples, rare inherited disorders which are there in kids. We are working on those children. Then we are also working on children having solid tumors, whether those solid tumors are inherited, what is the inheritance pattern. So we are also screening the parents and the kids for that. And if are they also acquiring these mutations in such a small period of time. The broader idea or the the vision is to develop newborn screening panels for these kids using this particular information. And herein, we are also including a lot of pharmacogenomic information. Now, when I say pharmacogenomics, what exactly it is? So now I've been talking about mutation. There is one concept called mutation. There is one concept that, okay, there are certain drugs that can be applied for that particular disorder, which like for that particular mutation, targeting that particular mutation. But does that drug will that drug work on me, or will that drug work on you? Because there have been studies which show that there are specific drugs which work according to the genetic profile of a particular individual. So, and this particular field, which is called pharmacogenomics, basically tailored medications on the basis of the genetic profile, can we use this genetic profile of the patient to identify these causal variants and optimize the selection and efficacy of the drug therapy. So now, so our first part wherein we are identifying or making the diagnostic reports is kind of done, and we are having clients for that. We are working on the second aim to identify the optimization of and selection of the drug efficacy using various pharmacogenomics data. And we are trying to build AI-enabled models for that. And as I have told to Karthik, we are a bioinformatics company, and we will definitely look for collaborations from people like you to help us develop such modules so that we can collaboratively build solutions for our society. Now, this was the kind of cloud-based platform that we started with. So this is actually the solution that we talk about, wherein the raw data from the users, which actually include the raw data, the various genome testing data, and our users are the hospitals, diagnostic labs, various doctors, will go through the pipelines, that the algorithm that we have made, and will provide various detailed information about the genomic biomarkers, the pharmacogenomic results, and various other the customizations will be provided on the using for that particular data. So these are the different solutions that we have right now. So the first solution is called OnCare, where we are working on targeted cancer panels, which are also known as onco panels, and providing the genetic information, basically the actionable insights which can be used by doctors to provide therapy recommendations. The second is Anuvanshiki, and as the name suggests, we are looking for inherited disorders. We are working on inherited disorders here and identifying the specific mutations related to hereditary disorders. And then we are also working on various customized solutions in this particular area. These are the different screenshots of our platform, which is currently under development, but yeah, we provide a secure dashboard to a hospital, and wherein they upload the raw data set that they get from the sequencing company, and then the final report is provided to them through their dashboard. And these are the different informations, the variant information, various other information that are provided to them, which is required by a doctor to identify, analyze, interpret, and finally report the results to a particular patient. These are the different types of information is provided in our reports. In the first column, as you see here, what we provide is the actual genomic alteration present in the patient. EGFR is a very well-known actionable marker. It's a gene, actually. It's a gene. And what amino acid changed to what amino acid at what particular position. So L changed to R at 858 position. This is the type of accuracy we have to provide in the report. And are there any, and then what are the FDA approved therapies that can be used for this particular if that particular mutation is there, and what are the different clinical trials that are ongoing for this particular if can be provided or ongoing for this particular mutation. And then different details of those therapies are there, that of this mutation is there, that what is the frequency, what is the scorings, and what is the classification level, and we follow a lot of guidelines provided by various guidelines programs. Now we have been working with a lot of research and diagnostic labs of the country, and we collaborated with them to work on various samples. The sample size is not very big, but yes, we are still in the stage of making more collaboration so that we can increase the sample size and report the validations and accuracy and efficacy maybe in my next talk whenever I'm here. These are the different clients that we have been working with. We have, apart from these solutions, we have been also providing various dedicated genome informatics services. So these were the solutions that we were making, especially on the patient data sets. And then we were also working on some research projects with some research institutes. And these were the different people who we have delivered certain projects. Last but not the least, I would like to introduce my team. Sunil is a scientific advisor and was the founder of Indian Centogene, and now with us. And then Saurabh and Padmini are my, both hands who are taking care of all the entire bioinformatics. And then we have a lot of consultants and other advisors who are with us as a part of our team. And this is it from my side. And before ending, as speaker before me, Manas, was talking about his experience, I would like to share. I don't have slides for that, but I can, speak up if I have time. Can you have some time up? She is going like this, time is up. But I'll take just 5 minutes. So, okay, so actually, though I have spent a long time in academia, almost 15, 17 years, published in various, studied in various Indian or international labs, published high quality papers, and, roamed across the world. But what I realized is that if you don't, use your skill or your, knowledge to build something for your community or society, this was the trigger point for me that if I could continue working in the same academic system throughout my career, but if I had that knowledge or power to build something for the society, I think I can make a small change. And if I can motivate any one of you to start working on your, building small things, not just for yourself, but for your community, for your society, for patients, or for general, community, it will be really helpful. Because we are fortunate enough to reach at this stage, to have that family who supported us to study, to have that community who supported our careers, to have that knowledge that has brought us here. We were fortunate enough to do that. But there are people out there who don't have that, a privilege. So if we have that privilege to stand and talk to such an audience, we can actually motivate people to, motivate people to build things and solutions. Not just there are different types of solutions, and to take that plunge out of their careers to start building for the nation. That's something that I would like to end my talk with. Thank you for your time and attention. I'm open for questions. And if you want to reach out to me, please follow the QR code. By the way, I'm looking for a CTO. So, okay. Thank you so much. So I think since we don't have more time, so we can take offline questions, but it was really an amazing topic. Can I request the speakers to come to the stage? we have now for 15 minutes break, and then we again start the session.
Yeah, hello everyone. So we now have a panel discussion. Hi everyone. We are now going to start our panel discussion, which is on collaborative academic and industry research in India, past, present, and future. So I'm going to be the moderator, and I'm Renuka Sindagatta from IBM Research India. And I'm a research manager there. I also look at some of the university collaborations. So be I'll probably be able to drive the session. And we have a wonderful set of panel members who have a good experience of industry and academia. So I'll introduce the speakers, and I would request each panel member to come and take their seat on the stage. So we have Preeti Ranjan Panda, who is a professor at Computer Science and Engineering at IIT Delhi. And Professor did his BTech in Computer Science and Engineering from IIT Madras and his MS and PhD degrees from University of California, Irvine. His research interests are on various areas. I'll just pick up a few: embedded systems design, system specification and synthesis, memory architectures and optimizations, and others. He's a recipient of the IBM Faculty Award, the IESA Techno Mentor Award, and a Department of Science and Technology Young Scientist Award. Professor has previously worked at TI, Texas Instruments, Bangalore, Advanced Technology Group at Synopsys, Mountain View, and has been a visiting scholar at Stanford University. Welcome. Thank you. Next, we have Bhanu Modali, who is the Chief Architect, Supply Chain IT at Dell Technologies. So as a Chief Architect, Bhanu is forging future-ready solutions at the nexus of business functionality, technological ingenuity, and sustainable advocacy. Has been in Dell for over 17 years and has had a comprehensive IT background spanning 25 years. Plays a pivotal role in building a resilient supply chain, spearheads innovation pillar within Dell for the Asia Pacific, Japan, China CIO Council, organizes and drives forums centered around architecture and technology. Welcome. We next have your very own Shubhankar Mishra, who is here, Reader F at the School of Computer Sciences, NISER. He did his BTech from NIT Roorkela and PhD from University of Florida. Research interests are in machine learning with special interest in security and privacy in machine learning, graph neural networks, 3D modeling, and robotics. And prior to this, he was an assistant professor at IIT Roorkee and Oak Ridge National Laboratory. And we also have Srivatsan Kondinyan, product manager at Microsoft Research. He received his PhD in electrical engineering at Stanford University. His research interests are machine learning, computer vision, and natural language processing. And prior to this, he worked at NVIDIA as a software architect. Welcome, Shiva. So let's start. I think is this working? Okay. So as we start this session, what I'll do is maybe we'll start with opening remarks from each one of the panel members, where what I would think is we could just talk about your experiences on the collaborations between industry and academia that you have had through your years of experience. And you can share what you think it has been, how has it helped you over the years and so on. So mostly on your experience. We'll start with.
we are going in this order. Thank you, Ranika. Maybe just a couple of comments to start off with. We are in the ACM forum here, so I'll limit myself to what we see in the industry collaborations in the academic space with respect to computing and computer science engineering. I should say I witnessed much of that early on as we were in the early stages of our research careers, and it was very, very hard to get PhD students. The research ecosystem in academia was nowhere as thriving as it is today in the country. But even in those early days, there was a lot of impetus from the industry, primarily headed by the multinationals that were present here with respect to reaching out to academia and telling us, let's start off on something. We know the hurdles are there, but I think we were privileged in terms of having that experience very early on. The numbers were small, but the quality of those interactions were always very high and played an important role in a cumulative role in where we stand today. So I should acknowledge that a lot of important problem statements got formed because of our partnerships with the industry. Moving to today, I should point out there's at least one other, so that has continued over the years. It has blossomed into an excellent relationship, but there are at least some other forces at work today that have added to the already nice partnerships, academia industry partnerships that we had, which is the early phase, I would say, was led by the multinationals in India because there wasn't a strong product and R&D such capabilities in the computing industry in India itself. Some of that has also begun to change, and the government's initiative in making research, more fundamental research in the universities, in the government institutions being eligible for CSR donation has made a tremendous impact I can see in terms of computing research being funded from not just from CSR funds, not just from the computing industry, but all over, from banking industry, from non-engineering industry, and so on. Uh, these are significant relationships that are being built as we speak today. And in fact, I'm glad to say that some of that is not even from computing industries, because CSR, there is a certain arm's length that you are supposed to have, but still people are happy to support the educational institutions in terms of their research. This is an absolutely new trend only over the last 5 years, but we see that it is significant and everybody is participating, not just the multinational companies. A lot of Indian institutions, a lot of non-computing related organizations, they too are pitching in. So I would say this is a new trend, and it is a great time to be in this space of academia industry partnership.
Yeah. So yeah, I agree to this point. Like, it's a great time to be in. First of all, like, if you see last few years, at least my personal interactions with academia, we have seen significant change in the way industry is also approaching to the academia and academia approaching to the industry. There's a lot of exchange in thought process. There's a lot of exchange in knowledge, what's happening on the industry and what's happening in the academia. Specifically, we had few sessions where faculty are coming into our campuses and trying to understand the life cycle processes of what we do. And then how do we productize these ideas that are coming out of this academia and other things and all. So once the faculty are getting exposed to it, we also have collaborations directly with students where we are going and giving a, sessions on what's happening within the business and other things. So even in the industry perspective, if you see, if I compare, like, pre-COVID, the kind of applications we were developing, the kind of challenges that we had are very different than today what we are in with the advent of these technologies, new technologies coming in and other things. There's a lot of new requirements that we have to be executing, which are more research oriented, and then you transform that into an idea and then do it. So that's a significant shift that we are seeing. Hence, there is a lot of fund flow even from those perspectives. Like, how do you pump more money into the analysis and then, do a research? And that is where it leads to some kind of a partnerships with this. I'm sure, this is going to explode in coming few years with many other companies. I know a few companies are already with research, tied up with research, but I think that is where it is driving to.
Hello. So from my end, I think I have had industry collaboration only for past 3 years. And my first project was from a public, like DST funded. I think after that, I have had only industry funded projects. So I think the portion of getting industry funding has increased as a whole. There is some advantages to like public funding and some advantage to industry. But generally, my thought process, if you're trying to solve some grand problem or a grand challenge, everybody has to be included. And probably trying to solve that small problem, we need, even if that is a very small problem, we still need industry and academia. So those are where we fit in. And major all interactions with the industry has been to making sure that expectations meet. So that has been a challenge, but overall, I think as the years have gone by, I think both have taken a step forward rather than a step back to make sure that we have the right expectations and then we have moved. And I think it has been easier rather than difficult with industry. It might have gone the other way with the public funding, but with industry that has been easier. So my overall look for industry and academia collaboration has been good.
So I think, can you hear me? Okay, so I think a lot of thoughts I have about industry and academia collaboration has been shared by some of the panelists already. But I'll just add that it's so critically important for those of you who are working in the machine learning space to have that relationship with industry, right? Because in my experience, especially in the field of machine learning, I found that a lot of creative ideas are developed in academia, but unfortunately, academia does not have the infrastructure, the compute infrastructure to scale those ideas. Right? As an example, when I was a graduate student at Stanford, I was part of a group that developed flash attention. It's a critical component of transformer architectures. And you'll find that without flash attention, LLMs, the deployment of LLMs is extremely challenging. But when my research group developed that idea, we didn't think we could get access to compute infrastructure to actually make that idea have an impact on the real world. However, by partnering with Google, Amazon, Microsoft, and many other big tech companies, right? We got access to GPUs as well as CPUs to scale the idea and show that it has relevance to the real world. So what I'm trying to say is that, again, in my experience, I've found that academic scientists come up with extremely creative ideas, but in this day and age, you need the deep pockets of big tech companies to actually help you scale those ideas to have an impact on the real world.
Yeah, thanks. I think the key important points that raised was there are lots of synergies, right? Where you're saying you really need both of them to work together, but there are also challenges, right? I mean, if you look at it, typically industry has product deadlines. They always work on timelines. They always work on something that has to be done in 6 months, right? Otherwise, it doesn't help them unless they are really coming to you for a far-reaching research. Whereas academics are more self-motivated, self-driven. They have their own deadlines. You want to write a paper, you will write. If you can decide whether you want to push it by another 3 months, right? It's that. So how have you worked? I mean, what do you think in your experiences which are the biggest challenges, which are the biggest synergies, and how have you worked through them? Maybe those would be helpful for us.
Yes, this is a conceptually easy thing to say, but the execution does get difficult. As we all know, there is the initial legal issue that is there, and that itself tends to delay things. The start of the execution is often delayed because words are not acceptable on both the sides. However, in spite of all these challenges, of course, the relationships have evolved, which means that obviously we are finding the ways around these initial challenges. Legal lease is one of them. We will get to some, when we talk about the different modes of collaboration, I will point to some of the successful ones that we have seen. But anyway, in terms of the execution and the timelines and so on, it is true that the rate at which implementation progress happens, an industry person might want to keep close tabs on, and in academia, we would like that part of it to be, the exploration part of it is very valuable to us. So in some sense, there is a conflict there, particularly in the early stages where you want the freedom to try out 20 different things, and then, but from the other side, somebody is monitoring, and they say, you know, say, helpful hints are given with respect to the need to focus and make a deeper progress instead. This is a usual give and take, and it's perhaps important that both sides of this they are seen in a natural way to be influencing, and a partnership in that sense. It's not fully flexible, but still the ones that are successful, I've seen, are those where flexibility is still exercised from the academic point of view, but the industry person is always there to give feedback about what has worked in the past, what has not worked, which the early feedback in terms of which are the promising directions based on prior experience and so on. The academic may not have that kind of an experience. So I would say these are places where compromises are made, but these are useful compromises, important compromises, just to make sure that we make progress along the lines.
So you could go ahead.
It's just that if I go last all the time, then all my comments are already shared. So, so what I was going to say is just to add to your thought, right? I think, you know, as you pointed out, a lot of industrial research labs, right? I mean, they are given a little bit of freedom to explore, but oftentimes they're operating on deadlines, right? And so they're too preoccupied to identify collaborations with academia. That's certainly true at Microsoft Research in Bangalore, and I imagine that's true at other labs as well, right? The reason I bring that up is because what I'm trying to say is the burden actually falls on the academics to identify areas of overlap with industrial labs, right? And so before approaching a lab, I think it's important for academia to have done their research and to identify potential areas of collaboration and then to approach them, right? Otherwise, there's a tendency for industrial labs to think that, well, if they're speaking to me, right, they're likely approaching me for funding or approaching me for compute resources. So at the outset, I think you should make it very clear that if you're approaching an industrial lab, you know, you should make it apparent that you've done your research and that you've identified specific research groups and specific scientists that you'd like to collaborate with. So that that notion of you working with them only for their funding and only for their compute infrastructure is kind of eliminated from the very beginning.
Yeah, that's a good point. Yeah, I completely agree that if it's more specific, you would understand what the request is, and right. Otherwise, you might say, okay, this is another funding. Right. Okay, so maybe Shivankar.
Hi. So just to spin up a bit, the biggest strength that we have as academia is basically our students who collaborate in that particular region. And like industry has a set of timeline and probably a problem definitely to be solved. The best is basically students because they're absolutely brilliant young minds who have no fear of failure. The other alternative is they have attention span of they change their attention as fast as I change slides. So the moment you can keep them monotone till the end of the problem, you have lost them. So if the exploration is not kept intact, that expectation of that students keep on exploring things, if it becomes a monotone idea that this problem has to be solved, that is where we lose students per se. So the best asset becomes the biggest liability also. So I don't know currently where to have that thing. As again, expectations have to be made from both the sides. Somewhere we tackle the exploration still stays and timeline still stays. So that is, I think, my biggest hurdle in making sure things work out in industry projects.
So you're saying students, how do you motivate students to pursue that the same problem? Go ahead, Anand. Yeah.
Yeah, so few of the benefits at least we see is like, again, as we said, like, young minds. So they think very differently when the problem statements are given, unless, we get into their thought process and start polluting into this, our own processes and other things. And also, that's one good thing. The kind of challenges that we face on the industry side is more like to collaborate more, like, we have to go through these legal kind of things and all. So that is one of the things that slowly I think that is changing. But that is one thing that we have, and then corporate policies is another thing that we have. And also, when students are approaching us from the uh, company, like, the number of SMEs that we have in specific functional areas are always limited. They are getting overburdened when, some internships happens for a longer periods of time. And definitely, shorter internships are not much of great this thing. Minimum 6 months or more is what we are looking at. But then that is where, is getting involved. So these are the areas where probably where I would say more from industry that they have to invest in, so that, this collaboration would be more fruitful, overall.
So I just want to add to your comment, right? I found that the PhD students we work with at Microsoft Research, when they begin to work with us, they're hyperactive, and they have a tendency to want to be involved with everything. But as soon as we anchor their research problem to real world impact, to say a Microsoft product, I found that it motivates them tremendously, and all of a sudden it increases their attention span by quite a bit, right? So in that sense, right, that's one huge benefit of working with industry. I understand that when you're working in academia, you're very much in an exploratory mindset. It's an open-ended problem, but the collaboration with industry brings that kind of the real world element to the problem, and that helps students a lot. And looking back, I wish I had worked with industry more and I was a PhD student, because I think that would have also motivated me a lot more to kind of stick to one or two problems as opposed to having worked on 4 or 5. Yeah.
And now, since we are at that, maybe I'll continue on that question. So you mentioned internship. You mentioned the students coming for internship. It's definitely one way industry and academia collaborate. What are the different types of collaboration that you look at Microsoft Research? And maybe you can talk about a few and say which ones have worked the best.
Right.
Is internship the only ones? Is it like at the faculty level, the institute level?
A great question. So we have several different programs. This is not just Microsoft Research in Bangalore, but Microsoft Research worldwide. So locations in Australia, Beijing, the US, of course. And so the program that's perhaps the most popular is referred to as the Research Fellows Program. How many of you here have heard of the RF program at Microsoft Research? Okay, and how many of you here have been in RF with Microsoft? Okay, no RFs. So the way the RF program works is that between your undergraduate and master's or PhD program, you spend 2 full years as a full-time employee with Microsoft Research. It's a contract position, but it's guaranteed for 2 years, and your only responsibility is to do research in an area that interests you, right? And the hope is that when you graduate from the program and go on to a master's or a PhD program, that you continue to collaborate with us in some capacity, that you identify a research area at your home institution that overlaps with an area that overlaps with some ongoing project with Microsoft Research, right? So that's one type of collaboration that happens. Of course, we have an internship program. The internship program doesn't really have a, it's kind of, I would call it like an open enrollment internship program. So the way that works is, as a PhD student, say you look through our webpage, you identify 2 or 3 researchers that you believe would be really interested in your work, you would simply reach out to them. You would see how the conversation goes. They'll also have a chance to see they'll have a chance to assess your research. And then it's really up to the researcher to see whether or not they want to take you on as an intern, right? And in that case, right, in some cases, your PhD research is so aligned with what the researcher is interested in that you can simply continue your PhD research at MSR. However, if it ends up being the case that, okay, your PhD work is not too relevant, but your skill sets are very important to us, then, and if it's okay with you, you might just end up working on a different research problem with MSR. And outside of all this, right, we actually have something referred to as it's called an external research program. The idea there is you apply to a PhD program and you apply to this program with Microsoft. And should you be admitted both by Microsoft as well as the PhD program, you would identify a researcher at Microsoft to serve as an advisor. Likewise, you would identify a mentor at your institute as well. And the mentor and the advisor, both at Microsoft as well as the institute, they would work together to kind of guide your PhD program. So several different ways you could kind of insert yourself and work with industrial labs. I'm sure these programs are not unique to Microsoft Research, but yeah, so as you can see, right, you can either do it right before you start your PhD program, while you're applying to a PhD program, and even if you're already in a PhD program.
Okay, Shivan, could I come to you? What have your experiences been? What are the types of collaborations you've been involved in with industry? Again, here, do you see any difference? And you also mentioned you work with the government, right? So maybe you could talk about the different types of collaboration you've had.
So in the government research, basically funded research, you have I think they follow our research timeline majorly. But in industry funding, okay, here's the project, hard collaboration. You have 1 year, complete the deadline. So really that hard collaboration is really a little bit tricky factor for us. Okay? So if we could start with something called a soft collaboration, I call it, I don't know. So maybe start building up the problem in 1 or 2 years. You don't give a very high fund, but at least judge for like 1 or 2 years in the initial years of PhD maybe, but not a hard fund. But by the time we value what we want from academia and what industry values from us, and maybe we reach a problem at the end of 2 years. But that's saying that we have a possibility of collaboration rather than saying that, okay, here is a project, 1 year, do it. Instead of that, rather a soft collaboration would probably help us in that. I think industry would move. The other one, I have a suggestion to the public as well, but in private also. So it went through a project that I got through, and I went through a project I did not get through. Basically, we do not receive any feedbacks on the project that we submit. I know for publicly funded, there is a lot of other questions to be asked, but in industry also, we don't get feedback. If we don't get feedback, we don't improve. We don't know what was missing. Because the next time I apply at a particular industry fund, I don't know what was missing. So at the same time, when I got this project and that project, those were written differently. Both of them, I got why, I don't know. I did not get why, I don't know. So that really feedback, if that can come from industry, that'd be wonderful. I think as a whole, India will increase both academia and industry. I think both will prosper.
Yeah, and Banu, maybe you can also talk about the types of collaboration you see between industry and academia in the context of Dell.
Yeah, Dell has a lot of collaborations with universities, but in the research areas, it is still nascent, I would say. But what we have been doing is to get the exchange of thought processes, we have been having a longer term hackathons. It's not really a quicker 2-day hackathons or kind of things at all. It's more like a 2-month hackathons, like where we give the problem statements and then they think through in the academia and then get back. That's one kind of engagement that we have. The other engagement that we have been having is also the employees from here, going to the industry, to the academia, and then spend some time with the faculty and then the students, and in a regular fashion, in a quarter, like, these many hours, like, you go and spend kind of time at all. So that some kind of cross-pollination is happening. The reason is it's glad to see, like, where few companies are very advanced in the research associations, but I'm happy to see this kind of things happening in the next level of companies that are evolving over. That's a pretty good sign is what I would say.
So, since you've been collaborating with industries for many years, so maybe you could also give your experiences on types of collaboration, and also maybe, I think the broad range of collaborations with various industries.
Yeah, I should point out in this forum at least one collaboration platform on which we have had quite some experience, a very positive experience, but it isn't a new one. But it's an old idea from US that was imported here. This is what is called a semiconductor research forum. Focus is okay on the semiconductor industry, but nevertheless, it's a large industry. All the computing systems industry is also part of that industry. IBM, Intel, pretty much every major company with a hardware, but otherwise a systems background, they are part of that forum. The way it works is the pool resources every year, certain number of companies. In India, that number is sometimes between 5 and 10. In the US, it is a bigger number. But the companies get together, pool some resources, and essentially call for research proposals along the lines that they are interested in. But the interest is usually pretty vast with respect to what research areas are covered. Almost everybody is covered in computing and electronics. But through such a forum and research that is sponsored through that forum, I've seen that academics have got very significant inputs regarding the nature of the work, the nature of the proposals, the kind of progress, sometimes data that is relevant for validation. A lot of monitoring and help in various ways happens through a platform of that nature. And we have seen that in every project that we have done, liaisons sign up from different companies giving very different perspectives on the nature of the research. Again, the value there really is in the intellectual contribution rather than the funding. There is funding there, of course, which is nice. It has the kind of flexibility that we would like from industrial funding. But even more than that, it is the ideas, the feedback that constantly we receive. That kind of a forum I would say has, so even though it's decades old in US, but here it has been operational for more than 5 years, 6 years or so. And I see that a number of institutions, particularly young faculty members, so when they've started off on their careers, they have been supported by these SRC projects. I think it has already played an important role in shaping up the academia India industry platform in the country, an important type of collaboration, and in addition to the individual collaborations that we have had.
So, like as Shivatsan, you were saying, now the resources, the data is hugely dominated by the industry, right? In terms of compute and in terms of the real data. So one thing I wanted to check was, what do you think is going to be the future of these industry and academic collaboration? Is it going to be highly dominated by the industry? Like, more and more, do you see it going there, or will there be some form of, do you think industries are going to make it more and more open? Or in general, what I'm trying to look at is, where do you see this landscape of collaboration heading towards?
So I think if you leave it to the industrial research labs, right, they have researchers, they have compute resources, they have data. And so they'll just try to push ahead, and they'll just try to, develop ideas that contribute to their bottom line and to their products. And so as academics, right, I think it's critically important for us to stay in touch with industry, especially in this day and age with the machine learning and LLM revolution, right? We have a lot of freedom to come up with creative ideas, as I was saying earlier. And so we want to make sure it has a real world impact. And in that sense, right, we, over the next few years, I think the case is going to be that we have to be proactive about working with industry, right? So it might be a one-way traffic in the short term. And then hopefully, in say 10, 20 years, right, then a balance is struck between, them working with us versus us working with them. But in the short term, given the way machine learning is involved and given how compute heavy it has become, I think as academics, we have to really make an effort to engage industry and to make sure that they're interested in our work.
you notice this when you were working in semiconductors a few years back? I'm sure. Did you have such kind of experience?
Yeah, this is certainly a new trend, what we are seeing today, that industry is actually leading in certain of the disciplines, like the ones that was mentioned. The ML progress, a lot of it requires so many resources that academia is hopeless in certain disciplines, though. But I would say the overall field of research is very large. If you leave out some of the depths, there is a breadth that needs to be covered. And industry is certainly, even though equipment-wise, they are all up there. In terms of manpower resource-wise, it is not as though they can afford a very large number of people. So there is a trade-off over there. Industry also beginning to invest a lot more into more fundamental research in the academia. It does tell us that the space out there, is populated by certain lines that can only be done with the close collaboration with between the academia and the industry. And there are also other lines that that are more visionary in nature, more futuristic, that the industry is still investing into and is interested in the research outcomes of, which are very much in the academia domain. So that has been there in the past. It continues. I would say, yeah, we're not too worried about it.
Yeah. Or should we open up for questions?
We can open.
Yeah. So we'll open up for questions. I would say, if you have any questions related to, as a student, if you have any questions on how industry, how you have to look for collaborations, either through your projects and so on, you can ask the panel.
Just one question. I'm from industry persistent systems, basically. So one experience which I have is like when we were working with industrial IoT domain, basically, and we realized like it requires a lot of multidisciplinary knowledge, right, which includes mechanical engineering knowledge and maybe chemical or other kind of stuff, right, which an IT industry may not always preserve because they are primarily recruiting CS guys and other things, right? So this is one area where I found like academic institutes could be of much help in incubating some new ideas or doing some research with industry around it. I just want to know, like from your side, how has been your experience from this multidisciplinary dimension, which advantage which academia has as compared to some of the IT industry segments. So just any experience you want to share around it?
So it's interesting you bring that up. Again, my comments are specific to Microsoft. I'm sure they may or may not translate to other labs. But at Microsoft, we definitely appreciate the value of multidisciplinary efforts. As an example, right, we've started an entire group called AI for Science. And this group doesn't have any computer scientists, right? It comprises of chemists, physicists, mechanical engineers, some electrical engineers as well. And all of them are collectively working together to solve basic research problems in fields like chemistry, physics, biology, so on and so forth. So it's interesting you bring that up. Microsoft, until recently, did not see value in those efforts. But over the past 2 to 3 years, small groups are being formed with non-traditional Microsoft scientists, right? AKA not computer scientists. And they're doing tremendous work, right, to advance their respective fields.
Sure, thank you.
I'm Balakrishnan. So actually, the thing is, over the period when the value chain at which the Indian industry was working was rather low, things have, of course, changed. But how would you presently put, because of that, the research in academia being sponsored by industry was also less because you're not really looking at top-end work in India. Things have changed over the time. But today, how would you place yourself in terms of the work that's being done by Indian industry, which could be attractive for research or PhD programs in academic institutions? how would you place them vis-a-vis other countries or other geographies?
I don't mean to hog the stage here, but it's interesting you bring that question up because just a few days ago, we had an internal meeting at Microsoft talking about recruiting PhDs from the US versus PhDs from India. And almost all of us agreed that over the past 5 years, PhDs from India are on par with PhDs from the US. That wasn't the case 5, 10 years ago, right? So to address your question directly, I think right now the research ecosystem in India is so mature and so thriving that when we recruit candidates to be researchers or to have other roles in the lab, we treat PhDs from the US on the same level as PhDs from India. Certainly from all the top institutions that are present today, like the IITs, NITs, IAC, right? All of them are publishing, the students from those institutes are publishing in top venues, top conferences, top journals. So um, in this day and age, it's amazing to see the Indian research ecosystem have come this far.
Yeah, just to add to that, right? A lot of engineering presence is in India, and then we have some PhDs from a consultant firm working with us on certain areas to solve some of the supply chain problems and beyond. Now there is a discussion like, why when the larger engineering presence is in India, how can we have more such kind of activities, working with PhD students here to do that, because the time zone is an advantage and also a lot of subject matter expertise. Again, the domain knowledge is pretty important for us. So that how do we apply that? Because it's all about applied research, especially from my perspective in our organization.
So just to add to that, because he said AI for science, so we are under Department of Atomic Energy. And yesterday we had discussions for this Chintan 2047 thing. And we also had AI for science. We just had a center for AI for sciences. And there was only one computer science in there. Rest of the 25 faculties are from physics, chemistry, bio, and earth and sciences. I think it's going, the interdisciplinary is the way. Yes.
And there's a staggering number, actually. I heard a few weeks ago that in 2006, the number of PhDs in computer science in India, the number of PhDs that were awarded on an annual basis in India was around 40 to 60. In this year alone, I believe it's on the order of like 1,500 or 1,600 PhDs being conferred. So again, adds to the fact that the research ecosystem in India has come a long way in the past decade and a half.
Hello, sir. My name is Abhishek. I want to get your perspective on this general question from student side that, like as student, when we are applying for internships in academia, so I'm currently pursuing PhD. So one way is that somehow the collaboration is coming from the supervisor side. If that is not possible, the other obvious way is that there are like we can count few good labs in India. So there are a few of them. So we start applying for them using their website, and that is, in my experience, really difficult to get noticed from that side. So, like, I just want to know your views that maybe that is the correct way. There are other ways, or there may be some specific recommendations for applying in that case.
So, when you're applying, again, this is very specific to our lab. We have plenty of research internship positions. When you apply through the website, I agree that it tends to be a black hole, right? Because I think that for a single internship position, I think we get about 3,000 applications, right? It's a ridiculous number. And you can imagine that we don't have the time to sift through all those applications. And so we rely on the researchers actually to identify candidates that have emailed them with interest, right? To help us shortlist the candidates that we should actually speak to and potentially interview and ultimately select. So, I think an unfortunate secret is that, yes, we have a formal application process. Yes, there are 3,000 applications, but it's kind of crazy to expect that we're actually going to go through all those applications, right? So to improve your chances, I would very much encourage you to email individual researchers, inform them that you've applied, encourage them to pick up your application, request a meeting with them, right? If you show that interest, if you show the eagerness, I think it'll be really appreciated. We will definitely take a note of it, and that significantly improves your chances as opposed to applying and just waiting, right? That, it's way too, the landscape is so competitive for that strategy to work.
Yeah, and one more thing you need to do is if you really know who, most of these industry, their bios are there, right? If you really know what you're working on and it overlaps with another researcher, no harm, trying to send them an email and talk about it even before the internship. You don't need to wait for the internship application. You can just start looking at discussing about what you want to do. And later on, that researcher would know you, right? Would have noticed saying this, oh, this person is working in that area. So it might work.
And avoid sending form emails, right? Like make sure your emails are very specific and very targeted, right? Because researchers have, a lot on their plate, definitely in academia and certainly also in industrial research labs, right? So you really need to be specific. It needs to be brief as well, right? Otherwise, the chances of your email getting ignored are quite high. So you want it to be brief, you want it to be specific, and you want to quickly get their interest. Otherwise, you know, you run the risk of potentially your email just kind of, being glossed over. So.
So these were some opportunities you all told us about how we can come from PhD collaborations and all. Can you please put some light on how we can come from masters?
So there are few initiatives, at least from Dell perspective, that I can call out. One is like, we are planning to have a 1-year complete internship program while, you spend some years at university, but one complete year being on-prem and then doing the internship over there. So that is one thing that we are seriously pursuing as we speak. So I think that becomes more, we have come a long way. Now we are also doing actually a third year and fourth year for are probably within the 2 years also, we are just trying to see the complete year how you can spend more time over there. So I think that is one of the efforts that I could see, and I could I'm just leading some of that effort.
So I know a lot of the comments I shared about doing internships have been specific to PhDs, but actually we have a really nice program called, or a really nice role called Research Software Engineers. And it specifically targets those who have completed their master's. Hopefully they've done some research with their master's degree. And if they have a little bit of software engineering background as well, we specifically recruit those candidates to be research software engineers, right? So they work hand in hand with the PhD researchers to take their raw work and to actually make it, a self-contained product. So that's one opportunity, again, specific to our lab that's meant for master's students with interest in research, without a PhD, but with a good software engineering background as well.
So that was the job preference, right? I meant like internship when we are completing 1 year of masters, then how can we look forward to be an intern or look for industrial exposure as an intern in research field after completing like 6 months or 1 year of masters?
That's a bit of a challenge in our case, because when we take on a research intern, we need to see that they are at least, you can be a master's student, but there needs to be some indication that they will eventually go on to a PhD. So that's kind of how we have structured the internship program. It's meant to really, improve the skill sets of those who are looking to do a PhD. But by no means is that is it like a binding agreement, right? All we need to see is that you intend to do your PhD. It doesn't necessarily mean that you have to be in a PhD program. Yeah. And we understand your interest could change, right? You could have interned with us, you didn't enjoy the experience, and you decide not to do a PhD, right? No harm done. But at least as you enter the PhD program, we need to see that you're very excited about research and very, very much looking forward to doing the PhD.
think then we are anyway out of time. So thanks everyone. I hope this was useful. Thanks to all the panel members.
Okay, now we have another two ECR talks. So let me introduce Dr. Shikhar Patranabish. He is a staff research scientist at IBM Research India. His research interests are in theoretical and applied cryptography with recent focus on quantum safe cryptography and privacy preserving analytics. Prior to joining IBM, he was a staff researcher at Visa Research USA and a postdoctoral researcher at ETH Zurich, Switzerland. He received his BTech and PhD from IIT Kharagpur. He is a young associate of the Indian National Academy of Engineering, an ACM Indian eminent speaker, and a recipient of the President of India Gold Medal from IIT Kharagpur. His research has appeared in top conferences and journals in security and cryptography and has been recognized by an IACR-based early career paper award at Asia Crypt, an IBM PhD fellowship, and Qualcomm Research Innovation Fellowship. So let us welcome the speaker. And yes.
Am I audible? Am I audible? Okay. Yeah, I think this is probably easier. Yeah, thank you for the introduction, and thanks a lot for inviting me to give this talk. I want to start with a little bit of a disclaimer. So there are two words here that I think are buzzwords nowadays, crypto and quantum. I just want to start with a disclaimer that this is not a talk about cryptocurrency, and this is not a talk about quantum computing. It could be misleading sometimes. Yeah, I'm going to talk about cryptography, and sort of the plan is I'll try to give an overview of the work that's happening in IBM research broadly across crypto and security. Then I'm going to talk a little bit about my own work, which is sort of captured in this title, which is cryptoplexity or cryptography complexity. I think we have had a number of really fascinating talks on complexity, but perhaps looking at different kinds of complexity. So I'll try to sort of paint a picture of crypto complexity. And then I'll try to end with a couple of slides just on my research journey, which I think is the norm for these kind of talks. So let's see. Okay. Right. Okay, so I think most of you have probably heard about cryptography today. I don't know if that would have been the case 5 to 10 years back when I was starting out with my PhD, but with all the applications of cryptography that we see in real-world applications, I think all of you are familiar with cryptography. And it has really evolved over the years, starting from like the 1970s and 1980s when it sort of became an important branch of theoretical computer science. to the post 2000s, where we see an explosion, right, of applications of cryptography in sort of real world applications. But this comes with its own challenges, right? Because when you want to design secure cryptographic systems, you have to go all the way from designing it in theory to actually implementing it and then protecting it against what are sometimes called as, these implementation level attacks, right? Because cryptographic vulnerabilities could be there could be many, many surfaces for your vulnerabilities, right? Attackers could be, targeting your assumptions, targeting your designs, targeting, flaws in your implementations. And this leads to an unfortunate scenario because this means that we rarely sleep well, right? So if I screw up in the talk, you know why? Because I rarely sleep well. But this is really a fascinating challenge in some sense because when you work across the entire spectrum of theoretical to applied crypto, you sort of see this whole range of things that you have to do to actually get a cryptographic system to work in practice. Okay, and that's something that I enjoy doing. So with that background, I'll probably just give a brief outline of what I want to talk about today. So as I said, I want to talk a little bit about the cryptography and security, the breadth of work that's happening across IBM Research and in IBM Research India, which I'm part of. I'll then sort of talk about the main technical aspects of this talk, which is this cryptoplexity stuff, and I'll finish with some what I call as observations of a traveling cryptographer, okay, which are some personal insights that I've gained over the years. So I'll start with the first part. So IBM Research has a huge presence globally, and we have around 200 researchers who are working in various aspects of crypto security and privacy. So on this slide, I'm not sure if it's visible at the back, but on this slide I've highlighted the centers which have people who are actually working in crypto, and then there are other centers where people work on other aspects of security, which could be system security, OS security, compilers, etc., right? So I'm based out of Bangalore. So we have a significant crypto presence in Bangalore, in Zurich, in Yorktown, in Dublin, and there are various centers. The kind of work that's happening, in IBM Research, as you can see in this slide, it's like a huge breadth of things, ranging all the way from threat management to cloud infrastructure, securing data and AI, crypto foundations, and decentralized trust. And obviously, if I start talking about all of these, we'll be here. I'll miss my flight, and you'll be here for a long, long time. So, in the interest of time, what I'll focus on for today is just this vertical, which is something that I have been working on, which is crypto foundations and more specifically crypto agility and quantum safe crypto. Okay, and this is something that we are working on at IBM Research India in collaboration with researchers from Zurich, Haifa, and Yorktown. So I'll start with a little bit of background because I've sort of mentioned quantum safe and what does that mean. I think many of you are probably aware of the significant advances that we have had in quantum computing. There's the possibility, the realistic possibility now that we'll have scalable quantum computing within the next 10 to 15 years. Okay, and that's great news. That's revolutionary, but that's not good news for cryptographers. Okay, that's more sleep lost, right? Because what happens is that once you have scalable quantum computing, then the landscape of cryptography, right? So as cryptographers, we have built this, massive looking buildings, right? While relying on essentially the hardness of solving certain computational problems, okay? But what happens with scalable quantum computing is that some of these problems now become solvable, okay? Because you sort of drop what we can call this like a Q bomb, right? So you just drop the quantum bomb. You have a computer that's able to run Shor's algorithm, and then a lot of the beautiful crypto that you have built is just gone, right? It's gone. Now, of course, you might think, okay, but then quantum computers are a long way away, right? Why worry about it now? Okay. The reason why you need to worry about it now is because if the attacker, right, if your adversary, right, has the sufficient motivation and resources, right, to actually do something bad, then they can sort of harvest all of the stuff that you're doing now, right? So they can store all of the encrypted traffic, right? All of the messages that you're sending over WhatsApp, which are claimed to be end-to-end encrypted, for example, or all of the digital signatures that you're doing to authenticate yourself, right? When you're logging into some service, they can sort of harvest all of that, keep it, and later, when the quantum computer becomes feasible, go back and recover all of it or forge all of it, okay, depending on what they're doing, okay? So even though scalable quantum computing may be further away, right? The longer you use quantum unsafe crypto, the more vulnerable you are, okay? And that vulnerability is now and today. It's a present threat, okay? So what that means is that we essentially need to switch as quickly as possible to using alternatives that are not broken by quantum computers, okay? And that leads to essentially two challenges, which I'll summarize in this one slide. The first being crypto agility, which is, you may have, for example, we have clients who are running like, huge workloads, right, on IBM's cloud platform. Do they even know where in their workloads crypto is getting used and whether or not it is vulnerable to quantum computers, okay? So this is the first challenge. Even before you start thinking about all the fancy quantum safe stuff, the first challenge is identification, okay? Do you have an end-to-end assessment of your crypto assets, okay? So this is what we call as crypto agility and vulnerability assessment, where you essentially want to help clients with visibility into the vulnerabilities of their crypto, okay? And this is sort of the short-term goal that we are working on, because this is something that is very, very important, right? Even before we talk about shifting towards, quantum safe crypto. And then, of course, in the longer term, we want to prepare the ground essentially for a wide breadth of things that are currently quantum unsafe, okay? So for example, if you have heard about things like, self-sovereign digital identity, if you have heard about verifiable credentials, if you have heard about Web 3.0, right? If you have heard about decentralization, a lot of that is enabled by fascinating crypto constructs, which are unfortunately all quantum broken, okay? So what we want to do is we essentially want to be in a position that by the time, or maybe well before quantum computing becomes scalable, we are actually equipped with quantum safe versions of these things, okay? So this is sort of a one-slide summary of what we are looking at. And this is where I'll sort of finish the summary of what we're doing at IBM Research. Are there any questions at this point? Okay. If not, then I'll move ahead and I'll try to sort of spend the next few minutes giving a very sort of high-level overview of some of the work that I have been doing in the space of quantum safe crypto and some relations that it actually has with cryptography complexity. Okay. And I'll sort of start by going back to sort of the fundamental motivation of crypto in the first place, right? So why do we need cryptography, right? And I think the most fundamental motivation for that, I don't know, since ancient Rome probably, right, has been that you want to have secure communication over insecure channels, okay? So Alice and Bob want to communicate with each other, and they don't want like an eavesdropping adversary to be able to see what they are communicating with each other, right? But they want to be able to do it over insecure channels, okay? And fundamentally, the world of cryptography can be broken into two parts. There's the symmetric key world and the public key world. In the symmetric key world, there's this additional power that the parties have in the sense that they actually have this sort of costly but secure channel, okay, over which they can maybe sort of transmit short messages, okay, and maybe they can use this to exchange like a small key, and then after that they can just use that key to go on and communicate over insecure channels, okay. I think the colors are maybe not that clear here, but the secure channel is the one at the top. And then in the public key world, they don't have this, okay? So now the challenge becomes tougher because now you have to enable secure communication between Alice and Bob, but now you don't have the luxury of this secure channel, okay? So it turns out that over the past sort of 40, 45 years, what cryptographers have observed is that the symmetric key crypto world is much easier to build. It consists of really simple structures. And really, it turns out that they are very often quantum safe, okay? So this is sort of fascinating. On the other hand, in the public key world, this is completely different. Okay? Public key crypto is much more difficult to build. Okay, it has very, very complex, very specific structures that you see manifested in that world, and many of them turn out to be quantum broken. Okay, which is the whole point of this talk. Okay. So one of the things that I've been really interested in or fascinated by is the structural gap between the two worlds. And the question is that can you have like a systematic framework that explains this, okay? So this is true, okay? This has been there for the past 40 years or so, but can you come up with, an explanation for this, okay? Now, of course, you might ask, why do we need an explanation? And I'll try to motivate that. The way we have been sort of building public key cryptography, and this is partly the reason why we are in trouble, is that we have sort of tried to build it from as many different assumptions as possible, okay? And this is fine, because you might say, okay, tomorrow if you break assumption 1, I can still fall back on assumption 2, okay? And that's okay, right? But the problem is that in the process, we have developed many, many different techniques for doing things. And it almost seems like every time you want to switch assumptions, you start from scratch, okay? So this is a problem in quantum safe crypto, because when you want to sort of move towards quantum safe crypto, it seems like, okay, so I had like a bunch of crypto, in purple and green, right? That was very nice, and now it's suddenly broken, right? And now I have this problem where I have to build everything from this blue assumption, right? Ignore the details. The details are, you can just focus on the colors. But there are these n advanced crypto systems that I have to build, okay? And now I have to sort of start building all of them from scratch, okay? So maybe I knew in the 1980s how to do something from maybe the purple assumption. Now in the 21st century, I have to again start building it from scratch, okay? So in some sense, you are reinventing the crypto wheel every time your assumptions break, okay? And this is not a great state of affairs, okay? So this is where we have been doing some work over the past 5 years or so, where we have sort of been trying to make sense of this crypto jungle in some sense by having a much more systematic framework that sits between assumptions and your target primitives, okay, or applications, okay? And this framework essentially consists of simple symmetric key crypto, which gives you some basic, hardness properties. And on top of that, you can have some very simple algebraic structures, which actually somehow explains what you need on top of symmetric key crypto to actually get these public key primitives, okay? Now, the advantage here is that you can have your assumptions on the left, you can have your primitives on the right, but really, it's this framework in the middle which makes things simplified. Because you can use this framework to build all your advanced crypto systems, and then you can sort of take your assumptions and build this framework in the middle, okay? So in some sense, you sort of get rid of all those nasty looking crisscross arrows, right? And it becomes very simple and very uniform, okay? Now I want to talk about two implications of this. One, which has a complexity theoretic flavor. I'll not have, of course, time to go into the details. So I'll keep it very high level. And then one for quantum safe crypto, which I really find very, very interesting. The first one is the following, right? So, cryptographers, we like to play around with structure and hardness, okay? So in some sense, this framework gives you this play tool, right? Where what you can do is you can take your favorite symmetric key crypto assumptions, and you can take your favorite algebraic structure, and you can start playing around with them, okay? And what happens as a result is you sort of start seeing that with different assumptions and different kinds of structure, you end up having some magic, right? And you actually start realizing all these advanced crypto systems, okay? So all of these advanced crypto systems that have been built from n different assumptions, you can actually have a very unified picture where you can explain them in terms of algebraic structure, okay? Of course, this is very high level and abstract, and I thought I'll keep maybe one slide for the cryptographers in the audience, where you can ignore all of the details, right? Because none of this is probably legible to anybody in any case. But what I want to sort of highlight here is that what I'm talking about in this slide is 40 years of cryptography, okay? And I can explain this all, right? We can explain this all in terms of structure and hardness, right? The more structure you have, the richer your primitives become, right? And in varying your hardness, you essentially get various kinds of primitives, okay? And the ones that are sort of inside these blue boxes are what you need, what enable all of these nice things that you do, right? Right? So for example, when you do privacy preserving analytics, when you do collaborative analytics, when you do simple things like sending a WhatsApp message, okay? These are the primitives that you need, okay? And now you can explain all of that in terms of structure and hardness, okay? So that's one aspect of it. And the reason why I say there's a complexity theoretic aspect to this is because you can now relate these primitives. You can have sort of a complexity theoretic hierarchy where you can rank these primitives based on the amount of structure needed to build them, okay? So that's one way of viewing things. And the other aspect, of course, is sort of more related to quantum safe crypto and is perhaps more relevant to the motivation I gave, which is that now with this sort of framework in the middle, when you want to sort of have quantum safe realizations of various primitives, instead of building n different primitives, you can just think of building this framework in the middle, okay? So you essentially reduce realizing so many different things to just realizing the right structure and hardness combination, okay? And that's a much nicer thing to have, because then you can just focus on that, and you can sort of, burn through all the math and try to figure out some assumptions that you think are plausibly quantum safe and will give you the right structure plus hardness combination, okay? And in some sense, therefore, you avoid reinventing the crypto wheel, and which was the motivation, okay? And here I will just sort of conclude the technical part with this one slide, which again is perhaps more relevant for the crypto folks, which is that in some sense, this framework allows us to examine various kinds of cryptography through a unified lens, okay? So cryptography that looks very different. If you are familiar with maybe Diffie-Hellman, right? And then, some of the crypto folks in the audience perhaps know about, lattices, for example, right? They look very different, but when you put them in this lens, you realize that they are essentially the same lens, okay? It's the same structure plus hardness lens. And then the other advantage is that now you can start taking new plausible assumptions, right? Instead of putting all your eggs in one basket, if you want to diversify your assumptions, then you can plug in new assumptions into this framework, and it supports that, okay? And we did that, for example, with isogenies of elliptica, okay? So I decided to keep it at a high level because of lack of time. I don't really have time to go into the details, but I'll be happy to chat about it offline, or you can take a look at some of the work that some of the papers that we have had in the past few years. So I'll probably end by sharing some observations I had. Arpita and Karthik insisted that these should be there. I have to say this is the first time I'm presenting slides like this. So I'm in uncharted territory, and I don't even know if I have the right set, experience to be able to say these things. But I thought there might be some things that perhaps would be helpful to young researchers, PhDs, early career postdocs. So my experience, has been very sort of diverse because, so first of all, I have sort of moved around quite a bit. Okay, so I started out as an undergrad and a PhD at IIT Kharagpur. I did a postdoc at ETH Zurich. I did quite a few internships during my PhD. In fact, I spent around 40% of my PhD away from my institute. Okay. And the entire body of work that I presented here today, for example, was done without my advisor. So I've actually had the wonderful experience and guidance of many, many people who are way smarter than me, and but they cared about teaching me, right? And I think that's something that I've taken away. I think some of these things were told by the other speakers as well, and I don't want to repeat them. Couple of things I want to highlight is that I think when you choose a problem, right, to work on, you should really care about that problem, okay? Don't choose your problems because that's the area where it's easy to publish. Don't choose your problems because your friend wants to work on that problem, okay? Or don't even choose a problem that, your advisor told you is good to work on, or purely that's the reason why you're working on it, okay? You should care about the problem that you're working on. And the other thing that I want to say is that collaboration is great, okay? So I love collaborating with people. In fact, a lot of the times the collaborations mean more to me than the work, okay? So you build wonderful relationships working together. It's very easy to forge, friendships, and it's a wonderful feeling to be part of a community. And that's what I think research has given, okay? And I'll sort of end with a few things that some of you may be going through. And if you are, then you're not alone, okay? All of us have gone through these things. All of us have had, failures, rejections, difficult choices to make. I myself gave up, a corporate job when I joined PhD. And I think there are some healthy practices that get you through this, right? And I always encourage people to talk about your research. In fact, somebody, I think, Moinakda was mentioning to me that there's a fear that if you talk about your research, your ideas will get stolen. They don't get stolen, they get refined, okay? So talk about your research with people, know what others are working on, embrace your rejections, be open to different choices, and at the end of the day, take ownership of what you're doing and roll with it, okay? So that's all I have to say. Thank you.
Thank you so much for the nice talk. Maybe we can take a couple of questions. Okay. Fine. If you don't have any question, let us thank the speaker again.
Thank you so much. Thank you.
So I and Shikhar share a lot of research interest, and I have seen him grow from his student days to what he is now. So I want to thank.
Okay, let me introduce the next speaker, Dr. Jyoti Vaduranga. So she is an assistant professor at the Department of Computer Science and Engineering at IIT Hyderabad. Her research interests are compilers, program analysis, and high performance computing. Prior to joining IIT Hyderabad, she was a postdoctoral researcher at Microsoft Research Lab Bangalore, and she received her PhD and MTech from IIT Madras, supported by the TCS PhD Fellowship. She also received a Google Research Explorer CSR Award in 2021 and several distinguished paper award and a reviewer award and Institute Research Award for her PhD thesis. She also served as Program Vice Chair for HIPC 2022, as Artifact Evaluation Chair as SAS 2020, and Program Committee member at multiple top conferences and channels. So let us welcome the speaker and
Hello, can you hear me? Yeah. Hello, everyone. Um, I would like to thank SK Marks for giving me this opportunity to talk here. And also, I would like to thank Karthik and Arpita for inviting me to talk at this platform. Right? So what I'll do is I plan my talk like this. Like I'll briefly introduce some of the research projects that are happening in my research group at IIT Hyderabad. Then I'll share some kind of PhD journey and applications in academia and so on. Okay. Yep. So the broadly, I work on compiler optimizations, program analysis, and high performance computing. If you see the first one, this is one project that's going on in our group is global compiler optimizations on CPU, GPU, heterogeneous programs, and we tackle synchronization optimizations in CPU, GPU, heterogeneous programs, and other communication related issues, and all we'll try to optimize in this. And the other one is the large scale parallelization algorithms. So usually this will like billion scale ANN search on GPUs and other algorithms on GPUs. The main motivation is about getting the higher throughput on GPUs. And the other track that's going on is you all know what's an LLM and all. I don't need to introduce that. So the idea here is we use LLM based embeddings for downstream tasks which are more what you say, more semantic in nature about to argue about semantic properties of the programs. And this is in collaboration with defense organization, mostly with Indian Navy and DRDO, is code compliance checking for safety critical systems. Right? Yeah. So what I'll do is like I'll pick one problem from each track, briefly introduce the problem to you. So please feel free to, I know I'm just giving you the problem statement, not exactly telling you how we are solving it, But please feel free to come to me, like if you want to know more about the project or anything related, any other details related to that. Taking a while to reflect. Okay. So I'll just briefly introduce what is a GPU architecture, just to understand the problem statement as well. So usually you have, this is the setup when I say about heterogeneous programs, this is the setup you have. You have a CPU and a GPU. And the program, similar to how a CPU has the host memory, you have the GPU with the device memory. And for example, any program that has to execute will have the pattern like this. So like you have some data on CPU like this data structures, allocations, and so on. So the first step is whatever the data that you want to compute on GPU, you just transfer it to GPU. And the computation happens in the kernel. That's the kernel executes on GPU. And you have some results. The results are copied back to CPU again, right? So you have the data transferred to GPU, computation on GPU, and copy back the results to CPU. That's the setup. So and don't worry about the complexity of the code. Like usually in this area, you see like we deal with programs, and the way to explain the problem is also through programs, right? And these programs are the ones that occur in the real world benchmarks. Like for example, this is from Polybench. So don't worry about the complexity. I'll just highlight few things, just focus on only those parts of the program. For example, if you see there is line number 9, okay, it is using like it's a kernel call, and it has two parameters. It uses on two data structures, which is x1 and then y1. And it's clearly visible that it's not dependent on x2 and y2, because it's neither reading from that array or writing to that array. So it's completely independent of that. There's no dependency there. And similarly, the line number 9 and 10, there's no dependency because it's completely working on x2 and y2, and it works on x1 and y1. Okay. So same thing applies to line number 13. It is independent of line number 10 because this is working on x2 and y2. This works on x1. So, but what happens when you run this code is, although we know that some parts of the code are independent of these data transfers, they have to wait because all these memory transfer calls are actually synchronous in nature. They're actually blocking calls, right? So even the kernels which are independent of these data transfers have to wait because of the synchronous nature, right? So the natural question that arises is, how can I improve this performance of this code? Is so is by, you see some change from the previous slide to here is you can see some stream identifiers, and you can see the actual memory copy calls and now mem copy async calls, right? So this is some programming construct that the CUDA gives so that you can convert these synchronous calls to asynchronous calls and then schedule them on different streams, okay? But of course, in order to now, how did I come up with these numbers? Right, the stream numbers. I have S1, S2, and then I'm using various other streams here and so on. How do I deal with that? It's by actually tracking the data dependencies. And we know that it is very hard to track these manually, all these data dependencies and control flow in the program. And the idea in this work is to have an automatic compiler optimization technique that takes the original code and transforms the memcopy calls into memcopy asyncs and then schedule them into various streams such that you'll have a highly performant code. And the optimization looks like this. Before optimization, I have like this, a kernel 1, kernel 2 waits on these data transfers. And after optimization, what happens is you can see overlap. Do you see the difference? Do you see the difference? Do you think it improves the performance? Why? Because there's overlapping work, right? The kernel 1 overlaps with kernel 2, and then data transfers happen in an overlapping fashion to the kernels. So the other problem that we are working on is approximate nearest neighbor search, and also scaling this billion scale approximate nearest neighbor search on GPUs. And k nearest neighbor search is a well-known problem. Like for example, you have billion points, and if you give a query vector, the idea is to find the k nearest neighbors to that query point. So, and what is meant by nearest? You can take Euclidean distance here, for example. And what happens is if I give billion scale and I ask you to find 10 nearest neighbors to that query point, we know that it cannot scale and we cannot do it in an exhaustive fashion. The common practice is to do it in approximate nearest neighbor search. And usually the vectors that we deal with when we say billion scale points, these points actually come from word embeddings or document embeddings in various domains like computer vision, documentation retrieval, and so on, right? And the challenge here is like when you're scaling this problem on GPUs, so usually the data itself, like if I say I have billion scale points and the dimension of each point is let's say 100 dimensions, right? Or 120 dimensions. The data size itself will be like, for example, you can see it as 128 GB, like 384 GB or 140 GB. And any idea? So how many of you worked on GPUs? What's a GPU? You know what is a GPU? So what can be the maximum, like in the GPUs you have seen so far, what's the maximum global memory size that can have? 80 GB, right? Very good. So now the question is, like when I have the data of this size, right? When I have the data of 140 or 384 GB, and let's say if I'm storing this data in a graph and then trying to parse the graph or traverse the graph to find the nearest neighbors, I also have to store the graph data structure, right? And the graph data structure, for example, if I take the state-of-the-art graph data structures for this problem, this can be either 260 GB or it can go up to 112 GB and so on based on what graph I choose. So now the question boils down to if I'm neither able to keep the data nor the graph on GPU, how am I going to solve this billion scale approximate nearest neighbor search on GPU? Because I'm very sure that I can get high throughput because I have lots of cores on GPU and I can run them in parallel, right? So please think about it. So this is what we are solving. And I'll show you one solution, but you can think and you can come up with your own solutions. The idea is like, as I told you, neither the graph nor the points are on GPU, but I have to search on GPU. That's the problem. So the way we do is this graph is on CPU and we take the compressed vectors of the original vectors and the compressed vectors are on GPU, right? So what we do is we traverse the graph on GPU using approximate distances, not the actual distances, approximate distances, and this compressed data is much, much smaller than the original data. And you communicate, the communication happens from CPU to GPU to get the neighbor information, the graph information, and so on, right? So this is a very clever approach where it uses all the resources, the PCI Express bus, CPU, GPU, and all to get the highest throughput. So I'm giving some various problems. I'm not, you're following? Good. So this is some third track. I don't want to go into details of this and then overwhelm with you too many problems. So this particular track, what we're working on is you have these large language models, which is similar to word to vec, we have code to vec. That means given code, you get the embeddings of that. And the closer embeddings, the distance between two embeddings also mean that the code snippets are similar to each other, right? Or same meaning, same meaning. So the question is how to use these embeddings for the more semantic oriented program analysis or any software engineering task. So although there are the lot of papers that are coming up in this space, and our group, what we interest is in more semantic oriented tasks, like for example, bug detection or bug fixing, code optimization, which are harder to do. Can we achieve such tasks through LLMs? If yes, what kind of modifications in these models or input representation, what is exactly required? That is something we are exploring. Clear? You got gist of some problems, right? They're happening. So these are some of, I think, you can get a flavor of what's happening in this area through some of these problems. I'm going to shift to a completely different thing. As Shikhar, the previous speaker, was saying, I'm going to talk about my own journey in PhD, and this is something not we usually keep on a slide, and it's even first time for me. And the disclaimer here is, I'm just going to share some experiences and what I learned. You don't need to agree upon anything what I'm going to speak, okay? This is just what happened to me, what I learned. It's just an opinion, so no, not an advice. Please use your own intellect or whatever to make your decisions. So this is my journey, like as the also introduced, I started with MTech at IIT Madras and converted to PhD after 1 year. I did my postdoc at Microsoft Research Lab for almost 1.5 years, and then I joined IIT Hyderabad. So why do you want to do PhD? What do you want to get out of PhD? So, I mean, maybe when we start our intention, maybe like I want a PhD thesis or a PhD degree at the end, right? But actually what PhD is really not about that. It's just a byproduct of PhD. And this is my thesis title. But what exactly is the really outcome of PhD is the training process itself, right? So we get trained such that we are capable of conducting independent research, right? That's a skill set that we are gaining over the 5 years. And the papers and publications just a byproduct of what we're going through. And the main important point is after you do PhD, you are joining small set of experts in that niche area or small area, right? So you are knowing more and more about lesser things as you go up. So this is, I think, the important part of having a PhD degree. So I kept it as different stages of what I want to share different things. So first thing is like when I converted from MTech to PhD, I had to do research on whether I am actually suitable for research. This is what I really want to do or not. So I used to go and talk to various seniors and so on, like asking whether what is research and what's PhD and so on. But during this process, I never questioned them what area I have to do research on. I never asked because that's very clear. I think that is something that before you start, I think you should be excited about an area of research. That is something I think is the driving force for those many years. Otherwise, I think I don't think one can sustain those many years on working on similar problems. Yeah? And the second part is since I convert, maybe because I converted from MTech to PhD, like I was expecting my advisor to give me some problem statement so I can start working on that. So when I started, actually, I was actually going to meetings every week, but I expect him to give, maybe I'm reading papers, but I expect him to give me problem statement. After 2 months, I understand that I understood. Maybe I realized a little late, but it has to come like you discuss something and you have to formulate and it's your thought process and he's of course there for discussions. So this is something that maybe it's not a learning experience for many, it's obvious for you, but this is something I had to realize after 2 months that I have to find my problem statement. It's not the advisor will come and say you work on this problem, right? So it's that's something maybe basic for all of many of you, but this is something I learned after spending 2 months in my PhD, that don't wait for the advisor to push you. We have to find the, also we have to look for problems to work on. And the stage where like once you have the papers, the obvious thing that happens is initially, I think most of you will start with rejection, paper rejection, unless and until you're very lucky to get the first paper accepted on first submission. So of course, you're working for many years on a particular paper and you have to work without rewards even after that. So one thing I observe, like over thing, it's really people say, okay, they're not having perseverance, and you see rarely people quit PhD. I mean, this is a small set of people who quit PhD and go, but the major set of people is once they see rejections, actually there's a lot of what you say, the productivity goes down a lot. That is something, this lack of interest after rejection, that's the huge quantity of people that goes through, like. And after we see a rejection, it's not that okay, I read you now, it got rejected in an A-star conference and let me submit to an A conference. It doesn't work like that. You still have to submit to the same level of conference venues. The reason is the quality is the important thing. It's not the number of papers. So there's no compromise on that. Okay. So this is something I just want to say that usually I think this was also brought in Dr. Geeta's talk is treating your own work as baby, right? So I got this advice like you treat your work as baby. The reason they give that advice is so you take care of the paper end to end and you're very particular about details of the paper and so on. But what I say is when actually the thing that it doesn't really work like that is when you see a rejection. How do you feel? It's like something happened to your baby and it's not, you don't want to take it to your heart so much, right? But if you're treating it as your baby, that's what happens. So what I tell to my students is don't treat your paper as your baby. You treat it as someone else's baby. And, and you're just yourself as a nanny. So that means you still have to do your work to the best, right? You still have to do your work to the best. It's not that I miss details, but at the end of the day, the paper is rejected. I am not rejected. The paper is rejected, right? It's very important for me. I mean, it's not the philosophical statement that I'm making here. So one thing that I want to say here is it actually kills the productivity. If you're too attached to something, you don't perform well. That is, I mean, that's my observation as I'm telling you. These are statements I don't want to advise anybody. I'm not sure even I'm eligible to that, but just my experience, right? So the other one that worked for me is like a Hello parent is also called a Hello advisor. That means when we have like paper rejections or feedback or any challenges, so I don't know, somehow I used to feel very comfortable talking to other mentors of my lab than my advisor. It's not that he's actually very open and friendly, but somehow I used to get more insights when I talk these to others and get their opinion, how I'm going, and all these things. So I think it's very important to share, like when you're stuck or when you're not productive, you're not able to focus after rejections. It's better to discuss with various people that you meet, right? And this is something I gained a lot. Again, the reason is that you save time. When you talk to people, learn from them, you save time. That's the whole point. It's not that we have to finish a PhD in 3 years, or that's not the focus, but we should spend time on quality things. So, and the other one that I want to bring in, many do not focus on this. Breadth in PhD is first 2 years, like our attitude, like for example, my advisor works on couple of projects. In my first 1 or 2 years, I used to be like, he discusses in lab talks and all, several other projects come up along with my own related work. I'll be like, whatever other projects that come up, I'll be like, no, I'm not, I don't want to listen to, I mean, I'm not interested in anything else. Like, first get my PhD degree, right? That will be my attitude, at least that was my attitude. So, but what I realized, once you get 1 or 2 papers, then we start getting interest in various things. And during PhD itself, of course, in postdoc and all, you start exploring newer areas. But there are ways in PhD itself you can do that, and that I did. And I'll also show you some what are the outcomes of doing that. One is people go for internship. So when you go for internship, you actually have one more dimension added to you, because it will be a bit different from your PhD, and you get also papers in that, and your breadth automatically increases. The other one, like for example, if you see my first 2 projects that I was telling about, anything about related to GPUs, all that happened during my lab discussions with students of my other mentors of my lab, right? So we don't know these small discussions in the lab and all. It'll increase your breadth and you'll get excited about their problem, and it'll take you a long way actually. I mean, even with, like for example, I was interacting with one professor who came for teaching Gyan course at IIT Madras, and that resulted in a paper after that and so on. So it will help you in the long way. This is something very important. And this is, of course, I think just kept it because maybe because of women students, I want to emphasize one thing is, so usually the number of, we can't compare anything actually, but I kept 2 examples, which is where we end up comparing. One thing is the number of papers, amount of work or anything. You cannot compare across areas. For example, for in our area, you have to spend 1 year solid to actually start writing the paper, 1.5 years, because you have to build the infrastructure, everything. So that may not be applicable to other areas. They may have start getting immediately once they start the research, they may start getting papers. Same thing, someone might have to write a proof. Maybe I may not need for most of the works. So they have different kinds of things, and we cannot really compare how many papers and all these things. It doesn't really work. It makes no sense, right? Comparing apples and oranges. So the other one that I want to say is it also applies to our background. Like for example, when I was doing my PhD, like I never used to stay after 5 or 6. The reason is I have to pick my kid from daycare, and then the daycare closes by 6 and I have to go back. But having said that, many of my lab mates used to stay till 11, 12. So now I can't compare myself with others saying, oh, I can't work more and all. So it doesn't really work. And what is the way to go? What works for me is you just do whatever best that you can do given your setup, and understanding these differences and accepting them. Again, it's not that we have to accept because we want to be noble, all that is not there for others. We have to accept because we want to be productive. It saves our time. And I'm saying it as a pause is apart from PhD. So usually the way we are grown up, at least I was grown up, is you always study, get good marks and all that. And to be very honest, even to start, I started to have new habits during my PhD. And I had to start that after taking a course. After taking a 3-credit course, the course name is Happiness, Habits, and Success. I had to take a course to understand I have to do some sports or some other activities. So the reason is I was like, look, okay, you study and then you go and sleep. Then that more I was. But after attending the course, I got motivated, got into different things. I started playing badminton and so on. Actually, the one thing is it helped me, and the takeaway is actually it will not kill your time. It will increase your productivity again. So you'll that I cannot say how. I cannot even prove. You have to try it and see for yourself. And I kept service because you can also help others. That's also one kind of thing. I was student head at IIT Madras for MITR, which is a student counseling thing, which has nothing to do with my PhD or anything. But these things somehow, I don't know, it'll relax or whatever. It actually helps. So please try and see. So this is the last stage of PhD. Is once you finish your 5+ years, and we have to give justification to every person in the university, right? It's to our DC members, HOD, and then even director, everyone, right? This is happens on one hand. What happens on the other hand? Who is happy when we cross 5+ years in PhD? Any guess? Is anyone happy on earth when we cross 5+ years in PhD? You see this message? Do you see any this kind of messages anywhere? Where do you see? Any guess? Any guess, please? I'm curious. LinkedIn, yes. I was, for example, I opened LinkedIn and it says you congratulate so and so for spending 6 years at IIT Madras. If I say congrats, they'll just slap me. I'm like, go on. It's already. So this is very funny. Like LinkedIn actually asks us to congratulate people who cross several years at an institute, assuming that's actually a job, not a PhD. So this is jokes apart. Jokes apart. There's an important point I want to make here. Is it actually really doesn't matter how many years you spend in your PhD. Actually, it only the through. I mean, we have to meet all these people and so on. I served in FSC, which is Faculty Selection Committee at IIT Hyderabad for almost 3 years now. So when we get applications, we usually don't see how many years they spend in PhD, unless and it's like 15 years and all, which usually don't happen. But it's all about the papers, right? Publications, the quality of work that you do in PhD. I don't remember even my colleagues checking that when we do group discussions and all about the applications. No one, we don't check about number of years they spend in PhD. So please don't worry about that. It's something that I want to share here. And the third one that no one talks about during PhD is recommendation letters. The moment we finish PhD, we need recommendation letters, right? Definitely your advisor is one who writes. The other people who do postdoc and all, of course, you have collaborators or you collaborate with someone you get. But I have seen my PhD lab mates and all also getting recommendation letters from the professors with whom they did the TA work, right? So TA work and all this doing sincerely also helps in the long run, right? You don't know, and also interacting in general with professors and be doing good TA work and all, it will help you in lot many other ways. Like for example, when you're going for an faculty interview talk, some of your college professor can be in the external panel, right? So it's not that we have to impress them. In general, we have to be good and doing everything good, right? Enjoy everything. And of course, I mean, this I think many others, like for example, Shikhar was also talking, the previous speaker, about networking and collaboration. So giving talks is very, very important. And you may also receive like offer letters once you give a talk. Very good talk at, and I mean, I experienced that. I don't want to bring out which college I got the offer letter from. But once you give very good talks, technical talks, you get actually, I mean, that takes you a long way. I mean, people actually care for talks. And I mean, serving on committees, right? Like serving on technical committees. Usually people think that we have to start that after getting well established and all. It can happen even from PhD. The one way you can be on technical committees is the artifact evaluations who work on systems. I think they can relate this. I do not know about other areas. And also attending summer school, you're already doing that, and being volunteers. So it's good to network so that it will give you many opportunities. I have only few more slides. I'll just wind it up. See, the next part, of course, right? After PhD is not that you have to immediately do postdoc. It depends on what you want to do in the long run. So the main idea for the postdoc is to gain breadth, right, in your research. And of course, you want to increase your number of collaborators. And of course, it's like a trial thing. Like I want to do research and I want to test the independent research capabilities so I can do postdoc. And where you do and all, it depends on what's your background and your family agrees and so on. So there's no hard here. Both have, actually, we also, the previous panel already covers this. What are the pros and cons? Whatever works best, that's the answer. And same thing for faculty career, where I have to join and all. It also depends on and where your family also wants to get settled and so on. So it really doesn't matter whether you're joining old and new IITs. There are pros and cons in both. And this is one point that I want to emphasize is actually people say when you join academia, you lose free. I mean, when you join industry, you lose freedom to do other problems of your interest, but that usually don't happen. I didn't experience that. Yeah, usually the life in academician has multiple things, and one thing that I take away is you never get bored. Okay, this ends my almost my talk. And one thing I want to say is, I mean, this was also end of Manas's talk, is you just enjoy the process. Like, the key thing is to be productive and not waste time is what I think. So we also have at IIT Hyderabad, like we have JRF and PhD positions, and there's also postdoc positions that are there, which they pay 70,000 per month, right? If you're interested, you can please apply for these positions. Thank you.
Thank you so much. And it was great to hear your experience at David will be happy. Yeah.
Hello.
I don't know if you can tell. I'm definitely not faculty because I'm not used to spotlight. But thank you, everybody. Thank you for coming today. We have a quick presentation on behalf of Klaksha University. I'm Radhika. I support faculty recruitment from the Vice Chancellor's office. I'll quickly introduce our delegation. Today we have Professor Rudra Pratap, who's the founding Vice Chancellor of Klaksha University, and he was previously the Deputy Director at Indian Institute of Science. We also have Professor Balakrishnan. He's the advisor for faculty affairs and career advancement and was previously the deputy director at IIT Delhi. I know we're all hungry. So without further ado, I'll invite Professor Rudra Pratap to take over the stage.
Hi, good evening. Good evening. Thank you for coming to this session. We take this opportunity to just tell you a little bit about this absolutely new university. New university that we have, Klaksha University, and it's also sort of a remarkable initiative, which is not easy to do. It's a collective philanthropy organization set up with collective philanthropy of lots of people. So we want to just tell you about that. And obviously, we are looking for faculty members, and that's why we invited you here. So we want to very clearly tell you that what kind of faculty members we are looking for and what kind of opportunities there are. So first, a little bit about the university. The university started with this idea of three pillars, reimagining tech education, fostering technology, innovation, and entrepreneurship, and addressing grand challenges through research. So the idea here is that tech education, as you know, has been riding on the chassis of World War II throughout the world, okay? But 21st century is very different and it should change. So the idea is that how do you reinvent technology education? How do you reimagine what should be the tech education for 21st century? So that was the first one. Second one, everybody knows it's a buzzword everywhere. But how to integrate that into curriculum is what we are trying to do. And third one, when we do research, unlike most places where research is left to just faculty to think about, what they can individually do, what we do is we nudge them to work on much bigger problems, which are the so-called grand challenges of the world today, including, of course, our country. So whether it's energy, water, health, food, agriculture, those are the things. Now, we have 100 plus founders and donors, from several countries. So far, we have more than $100 million in commitment. So this is a fantastic group of people. These are almost all of them first-gen successful entrepreneurs. Therefore, what they bring to the table is not just an amazing zeal, but also success in the tech world. And we have the advantage of using their expertise in everything that we do. So this is an amazing bunch, and they are all involved in the university's crafting its future, right? Professor Shankar Sastry from UC Berkeley, he was dean for 12 years, dean of engineering. But more than that, Shankar is a father figure in academic world. you can't possibly go to any engineering school or worth its name in United States or Europe where people don't know Shankar. So Shankar is a legendary figure, and he has been, he's the founding chancellor for us. It's always great to talk to Shankar and, brainstorm with him about things that we do. We also have an academic advisory board, which is very, very erudite academic advisory board, a lot of academic leaders from around the world. And it's not, the best thing is that this is not for just showing on the website and stuff like that. They spend enormous amount of time just scratching their heads about what 21st century education should be like. Because all of us, all in academics, are driven by that dream that, hey, the education got to change radically to cater to the needs of the modern times. So they all spend quite a bit of time. As a matter of fact, Rajesh Gupta from, third column, last but one row, he just spent his sabbatical semester with us last semester, and he's coming back again. So these folks have been giving us a lot of guidance, and with their help, we have been recruiting faculty members. This is a sampler of faculty that we already have. So we are looking for slightly different kind of faculty. What kind of faculty we are looking for? We are looking for people who really are very, very driven from inside, and they want to change the world of academics. Okay. On one hand, by doing different things in instruction and teaching and pedagogy, and on the other hand, with their research. So both of these things, we are looking for people who are really, really driven. Personally, I like to look for faculty members who have fire in their belly. So that's my requirement. Of course, I mean, you have to have PhD and all that stuff, but these are the partnerships right now which are in place. Again, even for partnerships, given that we have that kind of advisory board and that kind of Bala and Shankar and Professor Uday Desai, all these folks with us, signing up with any university as an MOU is fairly easy for us, but we don't do that. We look for very definite sort of interface with these universities, certain areas in which we want to work with them. So we do our homework, and then only we get partnerships going. So where is Plaksha? Now, Plaksha, well, Plaksha is located in Mohali, 10 minutes from the airport, very convenient location. Many of you might know NISER Mohali or ISB Mohali. They're very close, 10 minutes from us in our neighborhood. And by the way, the name Plaksha itself is very, very special. It's the name of the tree from which river Saraswati is supposed to have originated. Okay, so it's basically the place from where knowledge flows. That's the idea, right? That's the idea of the name. So in brief, these are the numbers. If you would like to take a look at 36 full-time faculty right now, 20 visiting faculty, 363 students. That includes 3 batches of undergraduates. We started in 21, 3 batches of undergraduates, 1 batch of, we have 1 year master's program in what we call Tech Leaders Fellowship Program that is co-designed and co-run with UC Berkeley, and 2 cohorts of PhD students. So we started all of these programs. 154 executives, meaning admin staff, 19 research fellows. So you can see BTech students, first year, second year, etc. Now, we are truly reimagining tech education. So the first pillar I showed you, of all three pillars, we are committed to all three. Now I'll show you a little bit of example about the first pillar. So these are the four majors we have for undergraduates right now. Okay, CSN AI, robotics and cyber physical systems, biosystems engineering, data science, economics, and business. These are the four majors. We give BTech degrees in all four. Next. So just a glimpse of what reimagining tech education is. So this curriculum, this is the first 3 semesters of teaching, and we call it freshmore curriculum, freshman and sophomore combined, freshmore curriculum. This is common to all 4 majors. So this is the common curriculum, and we are going to rename this as freshmore college so that students are admitted to freshmore college, and at the end of 3 semesters, they get to decide what major they want to choose. Okay, so it's not about coming in with a major, but choosing your major, taking some informed decision. Now, these are the courses, what you see in first semester 1, semester 2, semester 3, and I think most of you will recognize that these courses are freshly minted courses. Most of these courses are freshly minted courses. This is not how engineering curriculum, traditional engineering curriculum looks like. So we have done a lot of homework, talked to lots of academic leaders, and then come up with ideas about this. Just to, for the audience here, the computing core or the digital core is what you see here in second or 1, 2, 3, 4, fourth column, third column. Fundamentals of computational thinking, programming and data structures, intro to data science. And this year we split the first course and we introduced introduction to AI in there. So this is supposed to prepare all students for digital base, right? And computing base. That's the idea, that everybody got to have that. And we certainly think that machine learning and AI do not belong just to computer science, but of course, these are techniques that have wide applications, and therefore, as techniques, they should learn this. And similarly, you see foundations of physical world, that's the condensed version of physics 1, physics 2, or whatever that we used to do in engineering, chemistry 1, chemistry 2, all of that. What are the foundations of physical world? What are the physical laws that goes in there? And nature's machines is the introduction to the world of biology or biosystems engineering. Okay, so this is how this is designed. A very special thing there is Innovation Lab and Grand Challenge Studio that goes through all 8 semesters. It's project-based learning for students, but it's 8 semesters long. So students can do, students who are interested in entrepreneurship, they might take up something, and by the time they finish their 3rd year, they might even have a startup or incubation idea. Those who are interested in research can take up problems of research, work with our research centers, with our faculty. By the time they are in their 4th year, they might be able to even write a research paper. That's the idea, right? So whatever drives you, that gets a lot of attention through this project-based learning, and that's what goes in ILGC. These are our research centers. So faculty members have primary affiliation in one of these research centers, wherever they find, their calling. And naturally, all of these are interdisciplinary areas. You necessarily have to work with other colleagues on big problems, bring your expertise, work with their expertise to solve a much bigger problem than you would do just by yourself. So that's the idea, and there are lots of core labs that support these research centers. And as we go along, obviously, there will be more research centers coming up. So I'm at this point, I just gave you a brief intro to Plaksha. But there are lots of questions that you might think, obviously, on your own. You are also, most of you who are thinking about academic career, we all have to think about what education should be for 21st century, for coming decades. What kind of education our kids, our young in this country, they should get? There are lots of questions there. Okay, there are lots of questions, and one of the things that we are deliberately pursuing is how do we personalize education for students? How do we make sure that a student is not a mere roll number, but actually an individual, a living entity that everybody realizes? So that journey is on, and AI is going to be our friend in that journey. At this point, I'm just going to invite my colleague, Professor Balakrishnan, to talk to you about the opportunities for new faculty members. What kind of faculty members we have, what kind of facilities we have, how do we encourage them for academic career? Yeah.
Thanks. So I think, so basically what RP talked about is about a very interesting startup. So it's an education startup. So anybody who is joining the university at a very early stage, and especially a startup like this, has an opportunity to create something new. Okay. Of course, along with other colleagues. So if you think that whatever education you went through, whatever courses you went through, the teaching pedagogy, if you have ideas that you could have been done differently to be more effective, so come and try it out at Plaksha. So that's a place that, because at this point, things are very open, things are all under sort of still incubating in some sense. So one of the things is that, of course, programs and research centers from scratch already we talked about. So we do want to create groups, and we want to create interdisciplinary groups, and already that was look at grand challenges. And so you necessarily have to work with other people. So one of the interesting thing about this place is already RP mentioned it, so that NISER is close by, ISP is close by. So these are also, so we already talking to PGI Chandigarh in terms of medical research. So whatever is not there in the institution, you can reach out to other institutions which are in the neighborhood. Build, collaborations, build research collaborations, as well as look at problems and solve them. Because even though we may be a technology institution, it's very important that science is very important. It's very important that the type of problems, let's say we talk about medical research. So the type of data which PGI has, very few institutions in this country will have that type of a data. And that's so important to do any research. Institutional culture. So this is again something work in progress. So when you have a new institution, it also builds a culture of its own. And so the idea essentially is, can we create that culture which is very inclusive? Also look at, things which are modern, as well as we are able to take benefit of partnerships, which are both local as well as global partnerships. Okay, this is again a very sort of elaborate slide, but primarily, so I've been also be attending some of the talks today, and also I know this program. So I think a large number of you, definitely the type of research you are doing, you will fit into Plaksha in some way or the other. So if some of the areas are listed, so computer science, artificial intelligence, machine learning, data science, applied maths and statistics. But these are not the only areas. We are also looking for people in other areas, but these are definitely areas of interest for us. So if you have interest in any of these, you can reach out to us. And yeah. So the very flexible career track. So we have a tenure track system. So that means they're very similar to, you join after a PhD or you can join after a postdoc. That depends upon you. And there is at a certain point in time you join as an assistant professor. So roughly around 6 years time, you can actually get into, if you're a fresh PhD, but of course, if you're coming with some experience, then it will be shorter. Then you can get a tenure, show enough, build enough credentials in terms of both teaching as well as in research. So that's very important for you to understand that some of you may be coming from institutions where the focus is only on research. So Plaksha is actually, we expect that you spend half your time on teaching and half your time on research. Provide enough facilities and enough resources, but that's also very important that you are open to spending a lot of time and also working with. Some of this research could also come through your interaction with the undergraduate students. Already it was mentioned that we have this ILGC program, and we all know that today the youngsters are also, if given the opportunity, can contribute a lot to research. So that's again a model that we want to. So some of you are still doing your PhD. I'm sure most of you are still in your PhD program. So we also have opportunities at various levels, of course, as a postdoc, but also if you have, let's say, a semester to spare at any stage, you submitted your thesis, or you have exceeded the time in which your fellowship is, today not sort of available to you, please write to us. We have positions at various levels as teaching fellows, which can provide you both the research opportunity as well as participation in our teaching program. So we are quite open to looking at resumes where PhD is still not complete, but you would like to join us for shorter period or longer period. As we're also looking at joint industry appointments. So if your industry is open to looking at such an appointment, you want to go to an industry, we can also help talk to. Some cases we are talking to industry folks for whether they would ready to, some of you would prefer to join an industry for other reasons, though your heart and mind may be in academia. So this may also be a good opportunity to look at. We are very flexible in terms of, again, as I told you, being a startup, we don't have all policies in place. The policies are being made as the opportunities are coming and people are coming. So we can work out a solution which might suit you and suit us. Okay, so that's possible. Yeah, so we also have a joint postdoc with Indian Institute of Science, which has been just now signed. So where there is an opportunity for you to spend time at both Indian Institute of Science as well as at Plaksha. So that's a new program that we have started. So some of you are interested in such a program, please reach out to us and we can put you in touch. And this can also be, if you are looking at such a postdoc opportunity. So there's some, So this is sponsored by Plaksha. So the research will happen at ISC as well as you can have opportunity to participate in teaching at Plaksha, which can help you in your next, let's say, if you want to go into academics, that will help you, that will give you more experience of teaching, which is typically not available in just a postdoc program. We are very flexible and liberal about, our compensation packages. So we understand we are a new institution and we do have to attract talented people. So our offers could be anywhere 40 to 70% higher than offer for an equivalent position in the top public institutions in this country. So we are looking at that type of, and of course, other type of things like consulting. If somebody is working with industry, we have very attractive consultancy schemes, which, in terms of very low overheads for the institution. For young faculty, we also promote mentorship programs, nationally or internationally. We allow them to identify a mentor. So because we understand that our research ecosystem is still small. You might need some regeneration in terms of spending your summer in another research lab. So the Plaksha actually supports their faculty members, young faculty members, to actually go and spend time 2 months, whether in India or abroad, if that person is ready to host you at our cost. Okay, so that's again another possibility that we have. For example, for our PhD students, again, we have a 1-year international internship program available. The PhD students can actually spend. So it's not like a joint PhD or anything. It's any place where there is work going on which could be of interest to the student, they can actually go and spend. High degree of freedom, flexibility, and autonomy to define curriculum and pedagogy. So that's something that. So we are also open to looking at all things, even special consideration for, what we call as two-body problems, if both spouses are well educated and looking for opportunities, so we are ready to look at those. And support, professional support is going to be much better at Plaksha because that's the way that the executives that we talked about, the way they are hired and their career is looked after is very different from a typical public institution. Yeah, so that's what we wanted to talk to you about, but we are open to taking any feedback or questions from any.
So in short, there is a lot of opportunity here for creative minds. And as Bala said, very flexible. That's part of the design of the university. So, if you can dream of something, there is very high likelihood that you can do it there. So with that, we are going to open this up for questions, comments, anything that you might have. Please, anybody has any questions, we'll be happy to take it up.
Okay, maybe we start with asking you a question. So how many of you are looking for an academic career?
That is a fair, yeah,
okay.
That's good. That's good.
So how many of you are going to graduate in the next 1 year?
Oh, that's a good number.
Okay, good. So we are at the right audience.
That's right.
So please, any one of you have, looking for an academic career and you are likely to graduate soon, you can just stand up and, ask anything that you like. Want to know about Plaksha?
Yeah, please. Okay, so there is a lot of experimentation, as you know, around the world, right, for new pedagogy. People talk about flipped classrooms. People talk about, just when Chat GPT came, for example, right, there was all this brouhaha about, ban Chat GPT or do. We went in completely opposite direction. The day it came, we said, embrace it, use it in the classroom. So our faculty members immediately started working on how to use it more effectively, right? So the gentleman who is teaching data structures, Siddharth, he started experimenting with getting students to write small codes first by themselves, then ask ChatGPT to write the code, then compare the two codes, and then see, whether ChatGPT was better or you were better, and learn from this exercise. So there is also in math, for example, there are projects in math, and you necessarily have to do computing. Okay, after every lecture, there is computational assignment, and there are projects which are based on gaming. So these are all experiments in pedagogy, right? So there is a center for innovation in engineering education. Their entire job is to also look at whatever experiments we are doing and whatever experiments the world is doing, how is it being evaluated, right? Evaluate the efficacy of whatever you are doing and tweak continuously to come up with the right thing, right? So these are the very first semester when we started, we set up a teaching studio. So the idea is that if you want to do something, right, in the class, and you would like to rehearse, you would like to see it in action, go there. It's an absolutely state-of-the-art teaching studio with all kinds of audio, video equipment. You can record, you can watch yourself, you can take a colleague, you can call me, and watch with some senior colleague, ask for, opinions, criticism, whatever, right? So all of this kind of stuff is what we do in our innovations in pedagogy. This is a lot, and it goes every semester. We have at the end of the year, we have like 5-day long workshop on these issues. What is working? What is not working? What are the best things that somebody else has done? How do you learn from that? Is it worth implementing here? Not worth implementing? All of that. Yeah.
So I will give you one more example. So I was talking to a colleague of ours who taught this course on cell and molecular biology for the third year undergraduate students. And the final exam was, of course, he built on it. So paper reading, technical paper reading, how do we read, how do we sort of comment on it. And the major exam for him was that all of them read a science paper and then actually critiqued it as part of the major exam. So these are all, obviously driven by, like when he said that fire in the belly, so it's all driven by faculty members. It's not like somebody told him he has to do that. This is what sort of he decided to do it. And he feels that at the end of it, the students are much better prepared and much more interested in the subject. See, one of the challenges in education all over is a typical 50-minute lecture that we are all used to. For hundreds of years, perhaps it has gone in. It's very difficult to get an attention of a 18-year-old, 19-year-old, 20-year-old to sit and listen to, you're deriving something on the blackboard. So all of this has become a challenge, not just, anywhere, all over the world, this is the same challenge. So one needs to address it. So still the learning is important, but how do we address it is something that each one has to come up.
And the funny thing is that, look, we all have been on the other side. We all have been students, right? When we were students, how many of us can raise their hand and say that, yes, in that 50-minute lecture, I had all the 50 minutes focused on what was going on in the class? Nonsense. It doesn't happen. The moment you come on this side, you expect that to happen. So this is not being honest, right? We're not being honest. And I think that working on that issue, that, okay, what you were like when you were sitting there, what you were doing, and what can you do to get the attention of students, I think that's the kind of work we like to encourage.
Especially when we are students, there are no mobiles, there are no internet, there are no social media. So all of
Right,
it was still not
right.
there. Okay, even then it was difficult.
Attention was much better, but even then, yeah. Yeah, please. About admission process. Okay, so the admission process is a rather long process. So we do not take any exam of our own, and we don't intend to. God forbid, if we are pushed into doing it. What we do is the application process is a long application with lots of details. You have to write essays. The student has to write essays. And we have checks and balances that whether the student is writing the essay or the parent or the chat GPT who is writing essay, we can figure that out. There are people in the admissions office who read it thoroughly. We take the score of any national and international standard exam, okay, into consideration. So whether you have taken JEE or you have taken NEET or whatever, right, SAT, you submit your scores. That is not one thing alone is used for screening. It's a composite score. Your 9th, 10th, 11th grade marks, because you are applying in 12th, your marks are not there with you yet. Those are also taken into consideration, right? And then there is an innovation challenge which is given 1 hour online, 1-to-1. And typically the innovation challenge is designed from the essay you have written, just to see how clued in you were when you wrote the essay, okay? Obviously, for innovation challenge, there is no right or wrong answer. It's just you are looking at, the approach that the student has or the real enthusiasm that the student has. And then ultimately, there is a one-on-one interview, okay? There is somebody from admissions office or a faculty member or 2 people who interview the candidate. So it's a long process, but at the end of it, we create a merit list which is completely need blind. Okay, So that is not based on what tuition fee you can pay or not pay. It's not based on that. We make the merit list and then we offer admission. And once we offer admission, then we start looking at which student needs, help, financial aid, financial help. So we have, almost 30% or 33% of students, almost 1/3, on absolutely full scholarship, where even food and hostel, everything is covered, right? So we have, inclusivity is one of the things that we have as a philosophy. So we do not want to ever, deny an opportunity to a deserving candidate, irrespective of what kind of background they're coming from. So that's how the admission process. It's long, but it's worth it.
Some of the founders that you found in that list, they support this. How is the education get supported is through the founders giving scholarships to the students.
There are lots of scholarships available, and that number is increasing. Fortunately for us, the number of philanthropists in this country is increasing as the wealth of the country is increasing. So that's a good thing for education. Any other? Yeah, please. Yeah, so we do provide obviously startup grant for faculty members, and it does depend on what they want to do and how they want to do it. So they have to submit a basic proposal, which is like 2 pages proposal. Based on that, we provide startup grant, which can be anywhere, between 25 lakhs to, 50 lakhs. But if they need more than that, then it goes to one of the centers, because centers get support. So depending on where your requirements are, right, you pool support from other sources, because you are not going to be using. We strongly encourage faculty members to have joint labs, shared labs, so that resources can be optimized and pulled together and used effectively. And GPUs and all, those are also, central resources, right? Because you have to have an HPC cluster to help or to provide that kind of compute power to all faculty members. Anything else from anybody? You have any questions? No?
If there are enough people who may want to meet us at a smaller number of people in a smaller group, so we can also do that tomorrow morning. But if there are people can raise their hands, and if there is an interest to discuss further, or otherwise, of course, the website is there and emails are there, and we are welcome to reach out to us.
And yeah, if you are interested, what you can do, what I would suggest is just write to us. We will invite you to the campus. Come to the campus, see it for yourself, and talk to other faculty members, talk to students, talk to whomever you want. That is one thing which we are very particular about. It's a very open campus, welcoming campus. Even when founders come, even when anybody comes, we never have told ever to any student or any faculty that Mr. or, this Professor XY is coming, please, be at your best behavior or say these things. None of that. We are very confident of what we are doing, where we are headed. We are very confident of our mission. We want more people to join the mission. That's why we are here to talk to you. So if it sounds like, a commercial break to you, so be it. but we are onto this mission to change tech education for India and for the world, and you are most welcome to join that mission. Thank you.
So I'm here tomorrow throughout, so you can, find me and talk to me.
I think we're done with the time as well. Should I tell people to move to dinner? Okay, so dinner's where I think it is near the poster presentation area. So you can stop by and talk to Professor Pratap and Professor Bala.